Galileo died in 1642. That very same year of 1642, Isaac Newton was born. Born on Christmas Day, born to a mother whose husband had died just a few months earlier. Isaac Newton would take the ideas that Galileo had started to pull together, and he would bring them to fruition. Galileo had really recognized the 5 important threads that I've been talking about: astronomy, algebra, geometry, mechanics, and the mathematics of motion. And throughout the 17th century, various scientists would move these forward. And it would be at the very end of the 17th century that Sir Isaac Newton, as he eventually would become, would take these threads and weave them into a masterpiece that would solve the problem of celestial motion, that would solve the problem of why it is we can be on an earth that is traveling through the heavens at such incredible speeds without being aware of it. And this great work that Isaac Newton wrote is his Mathematical Principles of Natural Philosophy. The title itself is a reference to Descartes' book, Principles of Philosophy, and Newton is a bit more modest than Descartes was. Rather than laying out the foundations of all human knowledge, he only proposes to lay out the mathematical principles of what was then called natural philosophy, the natural world, or the world of our immediate experience, the world of nature. And he took the tools that had been developed and really perfected them in this book that I will refer to from now on more simply as Newton's Principia. The Principia almost didn't get written. At the time that Newton began it in 1684, he really wasn't interested in questions of celestial mechanics, in questions of physics. At this point in his career, he had moved on. He was trying to understand chemistry. He was also doing work in theology. But in 1684, Edmund Halley made a visit to Newton, and he raised the question, why is it that the planets travel in elliptical orbits? At this point, the astronomical observations were clear enough that it was obvious that Kepler's laws, that Kepler's statement that the planets move in elliptical orbits really had to be true. That agreed too closely to the observed data not to be true. But the question was still out there, why is it that the planets travel in elliptical orbits? And Newton said to Halley, well, yes, I can explain why that is true, and in fact I worked it out several years earlier, which, as we now know, he had done before. He tried to find the work that he'd done. He couldn't find it. He promised Halley that he would work it up, and over the next several months he did work it up into a book that is now referred to as De Motu. It was only ever a manuscript. And Newton realized, though, that as he put this together, that there was a bigger story that needed to be told. There was a lot more investigation, a lot more pulling together of these threads of science and mathematics. And so he began work on the more ambitious work of the Principia. It would take him 3 years to write it. It was completed in 1687. And not only was this a work that almost was not written, it's a work that almost was not published, because the natural publisher for this book was the Royal Society in London. This was a collection of the leading scientists in England at that time. It had been founded only a few years earlier, and it was trying to publish important scientific books. But it had just finished publishing A History of Fishes. And being a history of fishes, it had a lot of plates, a lot of pictures within it. This is a very expensive publication, and the Royal Society had expended all of its funds publishing A History of Fishes and had not yet begun to collect any income from that. And so there was no money to publish the Principia. Fortunately, at this point, Halley stepped forward again, and Halley personally put up the money that was needed in order to publish the Principia. And the Principia is an incredible work because it begins by explaining inertia. And exactly what that means, people at that time had a pretty good idea of what inertia was, but it was Newton who was the first person to clearly state inertia as we currently understand it, which is the tendency of a body that is at rest to stay at rest, but also the tendency of a body that is moving at a uniform velocity to maintain that uniform velocity, to keep moving in the same direction at the same speed. We also find in this book the first very clear statement of the relationship between force and acceleration, which is the rate at which velocity changes, and the very clear statement that force is directly proportional to the acceleration or change in velocity. So that if we double the force, we're going to double the rate at which the velocity changes. And this would turn out to be foundational to Newton's understanding of celestial mechanics. In this book, Newton's Principia, we also find calculus being used for the very first time. It shows Newton's great mastery of the ideas of calculus. To look at Newton's Principia, it doesn't look like he's using calculus because he's not using our modern terminology, our modern notation. That would come later. That would be a product of Leibniz, who I'll talk about in the next lecture. But Newton was a master of the tools and ideas of calculus. And if Newton is described as one of the fathers of calculus, it's because he understood it so thoroughly. The book itself is couched in the language of Euclidean geometry. Geometry is found throughout it, in very sophisticated geometry. It uses Apollonius's conics in a very fundamental way. There also is all of the full understanding of algebra that's contained within the Principia. There is the mechanics of inertia, of force, and there is this mathematics of motion. And of course, there is astronomy. The entire third book is devoted to looking at actual astronomical phenomena and explaining them, showing how the model that Newton had managed to build actually explains these phenomena. Newton is quite known for stating, "If I have seen a little further, it is by standing on the shoulders of giants." That's not a statement that was original to Newton, but it certainly is very true of him because he was building on the work of many earlier scientists, work of Napier, of Galileo, of Fermat and Descartes, but also many other scientists who followed Fermat and Descartes. And I want to take some time to talk about their contributions, because they are absolutely essential to understanding where Newton fits into this picture. The first of the people I want to talk about is John Wallis. Wallis was born in 1616. He would die in 1703. He's someone who was very much caught up in the English Civil War of the mid-17th century. In fact, he worked for the parliamentarians as a code breaker. And in 1647, he picked up a copy of Oughtred's Clavis Mathematicae, the mathematical key. It had been written in 1631, was a treatise on algebra that would be very influential. This is the book from which Newton himself would learn his algebra. And Wallis read this book on algebra and became fascinated with mathematics and the power of algebra. And 2 years after he started learning algebra, he became a professor of mathematics at Oxford University. I think that's probably one of the first cases in history of someone who 2 years after they learn algebra actually become a professor of mathematics. In 1649, he took over the Savilian chair of geometry in Oxford. 6 years later, in 1655, he published Arithmetica Infinitorum, Arithmetic of the Infinities. And this would be a very influential work for Newton. It has general methods for finding the slopes of curves. It has general methods for finding areas underneath curves. It also has incredible formulas, such as a formula for pi. Wallis realized that pi over 2 could be written as an infinite product 2 over 1 multiplied by 2 over 3 multiplied by 4 over 3 multiplied by 4 over 5 multiplied by 6 over 5. So for each fraction, you either increase the numerator by 2 or increase the denominator by 2. And you can show that as you take more and more terms in this product, it actually approaches the value pi over 2. Wallis also was responsible for inventing our symbol for infinity, the lazy 8, the 8 on its side. This appears in his Arithmetic of Infinities. It actually is a symbol that he had invented earlier than that, but it really is the Arithmetic of Infinities that popularized this symbol for infinity. Another one of the giants on whose shoulders Newton stood was Christian Huygens. Huygens was born in 1629. He would die in 1695. He was a Dutch scientist. His father was a scientist and diplomat, Constantine, also known as a philosopher, and he was a close friend of Descartes. And so Christian Huygens grew up knowing Descartes and being encouraged by Descartes. And Huygens' interests were all over the map. He became interested in astronomy, and in 1655 he became the first person to discover a moon circling Saturn. The rings of Saturn were already known, but he became the first person to actually observe a moon that was circling Saturn. In 1656 he invented the pendulum clock. Clocks had existed before then, but not clocks that were regulated by a pendulum. And it was Huygens who realized that this would be a very effective way of keeping a clock beating at a regular pace. Not only did he realize he could use a pendulum, but he worked out a lot of the mathematics of a swinging pendulum and the mechanics that lies behind that. He is credited with having designed an internal combustion engine. He never actually built it, and it was an engine that was run on gunpowder. It's not clear if it actually would have worked or not, but he had this idea of an internal combustion engine. And he also was one of the first to patent a pocket watch. That happened in 1675. In 1661, Huygens met Wallis, and this really marks the beginning of Huygens' work in mathematics and also in physics. Huygens had a very clear idea of inertia, although he never stated it as clearly as Newton eventually would. It's clear that Newton's understanding of inertia was also one that Huygens shared. Huygens is also often credited with being the person responsible for discovering the inverse square law of gravitational attraction. The fact that the force exerted by gravity decreases as you move farther away from the attracting body, and the force drops off as the square of the distance, so that if I double the distance, I'm going to get a quarter as much force. If I triple the distance, I'm going to get 1/9 as much of the force. And this actually comes out of Huygens' work, considering the force that's necessary to keep a rock in its orbit as you swing it on a string. So you take a rock, tie it to a string, swing it around your head, you feel a force pulling on that string. What's actually happening, as Huygens realized, is that the rock is trying to travel in a straight line. This is the effect of inertia. The rock tries to travel in a straight line. What you're actually doing is constantly pulling on that string in order to keep it going around your head. And Huygens realized that this is the idea that lies behind the fact that the planets are traveling around the sun. The planets are constantly trying to move off in straight lines, and it's the sun, through gravitational attraction, that's pulling them back in. This is an idea that Newton would come to independently, and in fact, the story of the falling apple probably is a true story. It's a story that was recorded by Newton's niece, and she said that she actually heard it from her uncle. That one day he was sitting and he saw an apple fall, and he began to think about gravity. Not gravity in the Aristotelian sense, where gravity is an inherent property that causes things to try to move toward the center of the earth, but rather gravity as a force, in the same way that Huygens was beginning to think about gravity. And he thought about this force pulling on the apple, and he wondered how far that force extends. Does it extend all the way to the moon? If it does, in fact, extend all the way to the moon, then perhaps what's really happening is that as the moon travels around the earth, it's constantly falling toward the earth. But it's falling toward the earth at the same time that it's trying to move along a tangent line. And so it moves along this tangent line and falls a little bit toward the earth, and moves along the tangent line and falls a little bit toward the earth. And compounding these motions, these different velocities, as you pull them together, you wind up with the actual motion of the moon as it circles the earth. This is something that Huygens probably realized, but he never stated it as clearly as Newton eventually would. Huygens also will play a very important role in this story because he would become the mentor to Leibniz. Leibniz would travel to Paris, meet Huygens, and Huygens would teach Leibniz a lot of the mathematics and physics also that Leibniz would need, and would introduce Leibniz to much of what was known about the calculus at that time. Another one of the giants on whose shoulders Newton stood was Isaac Barrow. Born in 1630, he would become a professor of Greek at Cambridge University, and then a few years later, while he was still holding his position as professor of Greek, he would become a professor of mathematics at Gresham College in London. In 1663, he became the very first Lucasian professor of mathematics. That's a very prestigious position. Today it is held by Stephen Hawking. Barrow would become Newton's teacher of mathematics, and in 1669, Barrow would go on to become the royal chaplain, and he would pass the position of Lucasian professor of mathematics on to Isaac Newton. In 1670, Newton prepared the geometrical lectures. These are lectures that Barrow had done, but it was Newton who pulled them together. These are lectures that talk about the connection between areas and tangents. And so these are lectures that begin to tie together the two aspects of calculus. The differential calculus, which deals with slopes of tangent lines, and the integral calculus that deals with areas. And we see here that Barrow was beginning to understand the connections between these two aspects of calculus, what today we would refer to as the fundamental theorem of calculus. And Newton clearly understood this idea and was able to build on it very effectively as he wrote the Principia. Another one of the giants is James Gregory, born in 1638, a Scotsman. He's someone who went to Italy. He studied with Angeli in Padua. And one of his important contributions is to figure out how to calculate the length of a curve. If you've got some curve traveling through space and you want to find how long it is, Gregory showed how to take that problem and translate it into a problem of finding the area underneath a different curve. And so that then could be done by the standard methods that were known by that time for finding areas under curves, the integral calculus. Gregory also found general methods for finding power series. Now that's something that I'm going to be talking a lot more about later. Essentially what a power series is a polynomial of infinite degree. So I've got a sequence of polynomials. Each one has higher degree than the previous one. And as I take polynomials of progressively higher degree, I get closer to the actual function that I want to model. And in the limit, we say that this polynomial of infinite degree, which is called a power series, is actually equal to the function in question. It has been said that Gregory might have been as great a mathematician as Newton himself, Unfortunately, Gregory died at a relatively young age, and so we do not know what his full potential might have been. Newton had a very unfortunate childhood. As I said, his father died before he was born. His mother remarried shortly after that, and Newton was packed off to live with her parents, and apparently he did not get along very well with them. He resented the fact that his mother had remarried greatly, and he went through life very much as an isolator, someone who did not get along very well with others. And one of his students wrote of him, "Newton was of the most fearful, cautious, and suspicious temper that I ever knew." This was William Whiston, who would be a student of Newton's and eventually be his successor as the Lucasian professor. Newton is someone who is constantly in conflict with the other scientists around him, arguing about who had come up with the key ideas that he had. Newton actually published very little about the calculus. The only real publication on calculus that Newton had was the Principia itself. And calculus is very hidden in that. You can't really sit down, read the Principia, and learn calculus from it. So there were earlier manuscripts that he circulated with some of his ideas of the calculus. He had gone back home between being an undergraduate at Cambridge and then returning during the years 1665 to 1667. There was a plague in Cambridge. He was forced to leave the city. He went home, and that's when he really developed most of his ideas of the calculus. And he did circulate some of these ideas in manuscripts in 1666, in 1669, and in 1691. But it's not really true to say that Newton invented calculus in the sense of establishing the foundation on which others could build. That would be a job that would be left to Leibniz. Newton understood the calculus beautifully. He was able to use it very effectively, but he never really was interested in explaining it. And later on, there would be a great controversy between Leibniz and Newton. Newton would claim that Leibniz had stolen his idea. Leibniz would claim that he, in fact, had been the first to come up with these ideas. And so there would be a great controversy, not just between Newton and Leibniz, but one that would spill over into a controversy between the English mathematicians and the continental mathematicians over who was responsible for laying the foundations of calculus. Another example of Newton's inability to get along with others is his paper on optics. The first paper appeared in 1672. There were 10 criticisms of that paper that were published, and one in particular, 1675, Hooke accused Newton of plagiarism, of stealing his ideas. Newton never forgave Hooke for this, and in fact, at this point, Newton threatened to stop publishing completely, that he was just going to keep his ideas to himself. And this was part of the reason why in 1684, when Halley went to see Newton, Newton had all these ideas about celestial mechanics, but he had not actually gone forward and begun to write them down in a form that actually could be published. Newton, as I've alluded, had many other interests. He was also interested in chemistry, or at that time it really was alchemy, trying to understand the fundamental chemical nature of substances, and he certainly spent far more time on chemistry than he ever did on physics or mathematics. But it was really too early to understand chemistry in a fundamental way, and nothing really ever came of Newton's work on chemistry. He was also fascinated with questions in theology, and his works show that he did a lot of exploring the Bible, especially the Old Testament, looking for numerical patterns, working out the dates on which various events would have happened, trying to see what the Old Testament could tell us about predicting the future. Newton eventually would leave his position at Cambridge. He would be elected to Parliament. He would become Warden of the Royal Mint. And finally, after Hooke died in 1704, Newton would publish his other very famous book on optics, an important work in which he explains refraction of light, and he explains the idea of light as a particle. Absolutely foundational work for understanding optics. Newton would be knighted in 1705, and then really spend the rest of his life in this battle with Leibniz over who had come up with the basic ideas of calculus first. As I said, he was a difficult person to get along with. He would become president of the Royal Society, and he would maintain as president of the Royal Society until his death. And one of the things that he did was to encourage the Royal Society to make a statement about the fact that he, Newton, was the one who had invented the calculus, and that Leibniz had simply stolen Newton's ideas. And because of his great influence on the English scientific community of that time, Newton was able to ram this through the Royal Society, and for this reason really alienate the continental mathematicians, the Bernoullis in particular, who I will talk about in the next lecture. Newton is a complex figure. He was very much a loner. He never married. He never had close friends. He was totally focused on his science, his mathematics, his physics, his chemistry, and yet he was very reluctant to publish any of these. He was really a mystic. And one of the people who has been most fascinated with the story of Sir Isaac Newton was the economist John Maynard Keynes. And in the early 20th century, Keynes began to pull together all of the manuscripts of Newton that he could find, and he would pore over these and study them. And Keynes made a statement about Newton that I think is very much on the mark. We think of Newton as a modern scientist, the man who would set the stage for what modern science should be. But Keynes, after looking at Newton's manuscripts, had a very different impression of Newton the man. And Keynes wrote, "Newton was not the first of the age of reason. He was the last of the magicians, the last of the Babylonians and Sumerians, the last great mind which looked out on the visible and intellectual world with the same eyes as those who began to build our intellectual inheritance rather less than 10,000 years ago. Isaac Newton, a posthumous child born with no father on Christmas Day, 1642, was the last wonder child to whom the Magi could do sincere and appropriate homage." Next time, we're going to turn to Leibniz and the Bernoullis. Newton truly understood calculus, but he was not able to lay the foundation on which others could build from calculus. This task would fall to Leibniz and the Bernoullis, and we will follow their story in the next lecture. In the last lecture, we looked at Isaac Newton and his use of calculus. Certainly, Newton understood calculus in its full complexity. He was able to use it very efficiently. But as I said in the last lecture, Newton really did not put calculus out there in a way that others could build on it and use it. That job would fall to Leibniz and two Swiss brothers, the Bernoullis. I want to say a little bit about the development of the calculus. There have been references to it throughout these lectures, And calculus really would be one of the foundational aspects of mathematics that would then carry mathematics through the following centuries. Calculus lies at the very heart of most of the mathematics that is done today. The origins of calculus really lie with the method of eudoxis, the method of exhaustion. We saw how Euclid described this method for finding areas and volumes, how Archimedes used it very efficiently, and this is the critical idea behind the integral calculus, this idea of trying to find the area underneath a curve by taking that area and subdividing it into small rectangles, whose area it's easy to find, adding up the areas of those rectangles, and using that as an approximation to the area, then taking smaller and smaller rectangles, narrower and narrower rectangles, and seeing what number you approach, what number you get close to as you take more rectangles. This is the method of exhaustion. This is the basic idea behind integral calculus. It was used and developed not just by the ancient Greeks. We have also seen that the Islamic mathematicians use this idea very effectively. Ibn al-Haytham used it in order to find the volume of the dome that's obtained by rotating a parabola. The Chinese mathematicians of the first millennium AD used this idea in order to find areas and volumes. The other part of calculus is the differential calculus. This involves looking at rates of change. So in the case of motion, if you know where something is at any given point, the velocity is the rate of change of position. And if you know the velocity at any given point in time, then the acceleration is the rate at which the velocity is changing. And so we have this other problem of looking at rates of change, and geometrically rates of change can be thought of as the slope of the tangent line to a curve. And we've also seen that this idea of looking at rates of change and building mathematical models around rates of change is something that goes right back to the Indian astronomers of 400, 500 AD. That they were beginning to look at the rate at which the sine function changes and using that in order to find their interpolating formulas. And this really came to a high level of perfection under Bhaskara in the 12th century. Bhaskara, who really in some sense was able to invent the derivative, at least for a very small class of functions such as the sine and the cosine, and begin to work with it and see the power of that. We have seen how in the 17th century Fermat and Descartes invented analytic geometry, this ability to go back and forth between a geometric object and its algebraic representation, or an algebraic expression and its geometric representation. And this really accelerated this whole process of looking at slopes of tangent lines, looking at areas. And as I said in an earlier lecture, Pierre de Fermat actually was able to find many of the formulas that we commonly associate with calculus. Formulas for finding the area underneath a polynomial curve, or finding the slope of the tangent to an arbitrary polynomial, not just polynomials, but also negative powers of x, rational powers of x. Wallis and Gregory would take these ideas and further develop them. They would come up with the idea of power series that I talked about in the last lecture, these kinds of infinite polynomials that Newton would use very effectively when he wrote the Principia, and that would be a very important part of calculus as it moves forward, especially in the 18th century. We will see how Leonhard Euler uses this idea of power series as a way of really exploiting the full power of the calculus. We've also seen how Isaac Barrow, in his geometrical lectures, was able to tie together these two ideas of the differential calculus, knowing where something is at any given point in time, figuring out the rate at which it is changing, and the integral calculus, which finds the area under curves, In fact, these two problems are related. If you want to reverse the process of differentiation, if you know the slope of the tangent line at every point, and you want to find the original curve, that can actually be accomplished by using the idea of integration. If you take this slope of the tangent line, express that as a curve which at each point gives you the slope of the tangent, and you then find the area underneath that, that area is going to give you the original function of which you had been finding the slope of the tangent line. And the same kind of reverse process also works in the other way. If you consider a curve, and you consider the function that describes the area as you go from, say, 0 up to any point, so the area underneath this curve from 0 up to x is a function of x. If we now take that function of x and look at the slope of its tangent line, look at its derivative, that takes us back to the function that we started with. So integration and differentiation are reverse processes of each other. This would become known as the fundamental theorem of calculus, this realization that you can do this. And it's where calculus really gets its name. Calculus comes about as a tool for calculating. And very often an easy way of finding the area under a curve is to recognize that the curve in question is the derivative of some other standard curve. And so by recognizing that integration is the reverse process of differentiation, it can make the calculations easier. Hence, we call this subject calculus. Newton was interested in calculus in order to explain motion. We really see him using it most effectively when he's looking at celestial mechanics, when he's trying to explain the motion of the planets. And Newton is using calculus primarily in order to understand the relationship between the position of an object, say the position of a planet, its velocity, and in particular interested in the velocity vector, not just how fast is it traveling, but what direction is it traveling in? And the acceleration, how fast is this velocity changing? And the fundamental law of gravitational attraction, that the force is inversely proportional to the square of the distance. That is, if I know the distance from the sun to the earth, then the force of gravity exerted by the sun is going to fall off as the square of the distance. Then what that gives me actually is what we call a differential equation. It's an equation that involves the derivative, because the force depends on the distance. But the force is telling us the rate at which the velocity is changing. The force tells us the acceleration. And the velocity itself is the rate at which position is changing. And so what that tells us is that the rate at which position changes, the velocity, if we then take the rate at which that changes, the acceleration, that acceleration depends on the distance. And so that's equal to 1 over the square of the distance. Leibniz enters the picture now as someone who goes beyond what Newton or any of the others did in looking at calculus in a somewhat different way. I want to back up and talk a little bit more about the story of Leibniz first, and then I will come and look at how he contributed to our understanding of calculus. Gottfried Wilhelm Leibniz was born in Leipzig in 1646. He intended to become a lawyer. He studied philosophy and law. And he became attached to Baron von Boinberg in Frankfurt as his private secretary, as a librarian, as a personal advisor. And at the same time, he opened a law office in Mainz, and he also had an independent law practice at that time. But he was interested in science, and partly because he had a patron, he had a personal sponsor, he was able to travel in order to study science. And in 1672, Leibniz traveled to Paris. And while he was in Paris, he met Huygens, Christian Huygens, who I talked about in the last lecture, certainly one of the great continental scientists of the 17th century. And Leibniz began to talk physics with Huygens, and Huygens quickly realized that there were serious gaps in Leibniz's understanding of mechanics and physics. And so he took the young Leibniz under his wing and began to teach him. And part of teaching him was to introduce him to the work of Wallis and the other people who had been working on the basic ideas on which calculus would be built. Leibniz became fascinated with this idea of calculus. He began to work on it. 2 years later, he traveled to London and would actually be elected as a Fellow of the Royal Society in London. And corresponding with Oldenburg, who was an English scientist at that time, he learned that Newton was also working on these same ideas of what today we would call the calculus. And so Leibniz wrote to Newton and asked him about what he had done. And Newton wrote back to Leibniz, and Newton was fairly guarded in his response. As I said in the last lecture, Newton was jealous of his results, but he did share some of the things that he was able to do with his tools of calculus, not explaining how he got those results, but stating some of the things that could be done. Well, Leibniz took these ideas, and he had enough understanding of calculus that he could figure out how to do them. And so he wrote back to Newton and said, oh yes, those are interesting insights, and this is how I'm able to do it. And he was hoping at that point to develop a further correspondence with Newton. Newton became suspicious at this point and cut off the correspondence. He was afraid that Leibniz would steal his ideas. And it was this initial correspondence that would be the foundation for Newton's later claim that Leibniz, in fact, had stolen his ideas, that those results that Newton had sent to Leibniz were key things that pointed to the kind of calculus that Leibniz would need to be able to develop. And Newton believed that those were the keys that Leibniz had used to develop his understanding of the calculus. In 1676, Leibniz is back in Germany. He becomes librarian to the Duke of Hanover. He gets a much more prestigious patron in the Duke of Hanover. He gets much more free time, and he's really able to devote himself to the development of the calculus. Unlike Newton, Leibniz begins to publish his results. And fortunately for Leibniz, one of the first scientific journals had just appeared. In 1682, the first scientific journal in Germany, the Acta Eruditorum, had appeared. And in 1684, Leibniz begins publishing in this journal the first known actual publications of Leibniz on the calculus appear in 1684, the same year that Newton is beginning his work on the Principia. And in 1686, Leibniz publishes his full statement of the fundamental theorem of calculus, explaining in very clear language the connection between the differential calculus, the finding of slopes, and the integral calculus, the finding of areas. The actual controversy between Newton and Leibniz would not break out for quite a while, not until 1711, and it would be in 1713 that the Royal Society would actually declare that Leibniz had plagiarized these ideas. But we know enough about what Leibniz had been doing that it really is legitimate to credit Leibniz with coming up with an independent understanding of the calculus in its full complexity. Now, I said that when Newton looked at calculus, he was interested in calculus as the mathematics of motion. And he wrote about it in terms of something that he called fluxions, what today we call derivatives, Newton referred to as fluxions. He's interested in these changes and in these rates of change. But Leibniz had a very different way of thinking about the calculus. He was looking at the integral calculus not necessarily as areas, but as limits of sums of products. And he was interested in these rates of change not as rates of change necessarily, not as velocities and accelerations, but rather as ratios of differences. He was really focused in on this idea of y depends on x. You've got some kind of equation in which y depends on x, and you look at the amount that x changes, what I'll refer to as delta x, the change in x. You're interested in the amount y changes as x makes this change. That's your delta y. And then Leibniz is looking at the rate of change as the ratio, the delta y, change in y, divided by the delta x, the change in x. And if we're trying to find the slope of the tangent line, if we're trying to find this rate of change, we need to take the delta x smaller and smaller. And if we're trying to find the limit of this sum of products, the kind of sum of products that you would get in the method of exhaustion in finding the area underneath the curve, you're looking at this idea of the limit of a sum of products. Newton sort of finessed this problem of what do we mean by this limit of sum of products? What do we mean by this limit of ratios as the delta x is becoming smaller? Leibniz tackled this problem head on. He said that what eventually happens is this delta x shrinks down to the point where it becomes an infinitesimal. It becomes a number that is so small that it is smaller than any positive number, but it's not zero. It's greater than zero and yet smaller than every positive number. That's a strange concept to try to wrap your mind around, and yet it's very useful, and intuitively it actually gives us a way of making some kind of sense of the calculus. That what we're looking at when we take a derivative is a ratio of two infinitesimals, two quantities that are so close to zero that we can't assign a positive value to them, but they're not quite zero. And one of the things that Leibniz does is to completely glide over Zeno's paradox and much of the mathematics that the ancient Greeks had done. Because Greek mathematics was based on this assumption that numbers are commensurable. If I've got two numbers, they represent lengths, and it's always possible to take one of those lengths and measure out the other length in terms of the shorter one. And what Leibniz is claiming is, no, we need to introduce some numbers that you can't do that, because if you take an infinitesimal and you take a finite length, no matter how many infinitesimals you take, you'll never be able to equal that finite length. Two other mathematicians who play a critical role here at the end of the 17th century and into the early 18th century are the two Swiss brothers, Jakob and Johann Bernoulli, from the city of Basel. Jakob was born in 1654, Johann was born in 1667, and they have an incredible family tree. There would be a total of 8 Bernoullis who would become great mathematicians, not all of them of the stature of Jakob and Johann. They were two of the very greatest. Johann's son, Daniel Bernoulli, would certainly be the equal of his father and his uncle, and the others were lesser mathematicians, but still very important mathematicians in the story of the development of mathematics. Jakob did not set out to study mathematics. He began by studying theology at the University of Basel. But he would eventually travel to France, and while in France, he would begin to study mechanics and mathematics. He went on and spent some time in the Netherlands. He actually traveled to England, continuing to explore the exciting work that was happening at that time in mechanics and mathematics. And eventually he would go back to Basel in 1683. This is the year before Newton writes the Principia. Jakob Bernoulli finds himself back in Basel, and by 1687, Jakob Bernoulli has become the chair of mathematics at the University of Basel. Johann was a good deal younger than Jakob. He enters the University of Basel in 1683. The same year that Jakob had returned to the university to begin teaching mechanics. Johann enters the university with the intention of studying medicine. But under the influence of his older brother, he becomes interested in these questions of mathematics, and especially the questions of the development of calculus. And in 1687, the two brothers discover the papers that Leibniz has begun to publish on the development of the calculus. And they are fascinated by what's going on there. In 1690, Jakob publishes his first important work on calculus. And what he does is to publish the solution of the isochrone. So I need to set up the situation here with an isochrone. If you have a ramp and you take a ball and you let it roll down the ramp, and you then take the ball and you put it at a lower position on the ramp, it's going to take less time to get to the bottom. So how long it takes depends on where we start on the ramp. And the ball that starts further up is going to take longer to get to the bottom than one that starts further down. But what if instead of a ramp that's simply an inclined plane, we take a ramp which descends extremely steeply, and then when it gets very near the bottom, suddenly levels off? If I take a ball and I start it at the top, it's going to pick up a great deal of speed as it falls quickly down the steep portion, and that speed will continue and get it to the output very quickly. If I take a ball that starts on the relatively flat part of this ramp, it's never going to pick up much speed, and it will actually take longer to get to the end of the ramp than the ball that started high up. So in this case, the one that starts high up gets to the end point before the one that started lower down. So which ball gets there first is going to depend on the shape of the ramp. And the question that came up, that several people had looked at, and Jakob Bernoulli actually was able to solve, is there a ramp? Is there a shape of a ramp that you can design so that wherever you put the ball on that ramp, it will take exactly the same amount of time to get to the end? And Jakob showed that you could do this, and he used the tools of calculus in order to find out what the shape of that curve should be. It's a curve that today we call a cycloid. Johann would go on to Geneva and then Paris. In 1691, Johann began a correspondence with Leibniz, and the two of them would then do an extended collaboration over the succeeding years, sharing their ideas of the calculus and really working together to build up the foundations of the calculus. In 1694, Leibniz wrote a very important letter to Johann Bernoulli explaining how to get these power series, these polynomials of infinite degree, for any kind of function. An absolutely foundational tool that Bernoulli would go on to use in important ways. Bernoulli did not have a patron at this point in time. He did not have a university position. He was in Paris, and a lot of the royalty, a lot of the nobility in Paris were interested in what was happening in mathematics and science at that time. And one of the noblemen who actually had a fair amount of mathematical talent was Guillaume de l'Hôpital. For 2 years that Bernoulli was in Paris, Guillaume de l'Hôpital paid for his costs, supported him, and the contract that was drawn up agreed that any mathematical results that Bernoulli came up with during this time, l'Hôpital was free to use as his own. L'Hôpital would later go on to publish the very first textbook on calculus. This was published in 1696, the Analyse des infiniment petits, the analysis of the infinitely little things, or as one of my colleagues likes to say, analysis of the itty-bitty things, which is this idea of calculus is built up of these infinitesimals. And l'Hôpital explains this idea, and contained within his textbook is a result that today we call L'Hôpital's rule. And it's a general way of taking the problem of a ratio of two quantities and looking at what happens as both of these quantities approach zero. So you have some algebraic expression, or it might be a trigonometric function or an exponential function, something involving exponentials, in the numerator. And you've got another expression in the denominator. And both of these expressions depend on the same variable. They depend on some x. And you observe that as x gets close to zero, both of these quantities are approaching zero. So it's a ratio where the numerator is getting close to zero and the denominator is getting close to zero. Well, if the denominator stays fixed and the numerator approaches zero, the entire fraction is going to approach zero. And if the numerator stays fixed and the denominator approaches zero, the whole fraction is going to blow up toward infinity. But what if both of these are approaching zero? Well, this is exactly the kind of idea that's used in the differential calculus, because that's a ratio where both numerator and denominator are approaching zero. And in fact, the answer that you get, what this approaches as the x goes toward its limit, is going to depend on the relationship between the expression in the numerator and the expression in the denominator. And one of the things that L'Hopital publishes, what today we refer to as L'Hopital's rule, is a general way of using derivatives in order to find this limit of this ratio of two things that are both approaching zero. After L'Hopital's death, Bernoulli would state that L'Hopital had learned this idea from him, and that it really was his. And later on, not until actually many, many years later, finally, the correspondence was discovered in which it was shown that this was an idea that Bernoulli had come up with. He had shared it with L'Hopital, but at about the same time, the mathematical community discovered this contract between the two, this agreement, that the results that Bernoulli came up with were ones that L'Hopital was free to use and attach his own name to. And so today we call it L'Hopital's rule still. It was Bernoulli who first discovered it, but L'Hopital paid for it quite fairly. L'Hopital was a good mathematician, and so it's not at all unreasonable to apply his name to this result. In 1705, Jacob Bernoulli dies. Johann takes over his chair at the University of Basel. And over the next several years, Johann completes the great work that Jacob Bernoulli had begun during his lifetime on the mathematics of probability. In 1713, Johann finally publishes this work, the Ars Conjectandi, the art of conjecture. It's a work on probability, but it has so much more. One of the important things that I will come back to later is something called a Bernoulli polynomial. And so this is a polynomial that makes it very efficient for finding the sums of powers. I've talked about this before in connection with Al-Haytham, who found a formula for the sum of the fourth powers. You can also ask for formulas for the sum of the fifth powers or the sixth powers. And there are ways of using binomial coefficients, Pascal's triangle, in order to find formulas for the sum of consecutive powers. So we're looking at the sum of the fifth powers or sixth powers up to a certain number. Bernoulli polynomials would turn out to be the most efficient way of doing this, but it turns out there's much, much more going on with these Bernoulli polynomials. They would be absolutely foundational. And they give rise to an interesting sequence of numbers known as the Bernoulli numbers. And they're rational numbers. It's a curious sequence, 1/6, 1/30, 1/42, 1/30 again, then 5/66, then 691 over 2730, and so on. And we will see how these come up in a fundamental way connected with Fermat's last theorem. We're going to leave Leibniz and the Bernoullis at this point. In the next lecture, we're going to turn to Leonhard Euler. Euler was also from Basel, and maybe there was something in the water there. Euler is someone who would be a student of Johann Bernoulli, And Leonhard Euler would not only be his greatest student, Leonhard Euler would go on to become the greatest mathematician who ever lived. We have reached the 18th century, and there is one mathematician who truly dominates this century, and that is Leonhard Euler. He dominates it so thoroughly that by the time he dies in 1783, his contemporaries will believe that he has solved all of the important mathematics problems that are out there, that there really is nothing left for mathematicians to do except to do some cleaning up. But the great ideas have all been found by Euler. In fact, fortunately, they were very wrong. Mathematics was just about to enter a very new and exciting and dynamic age. But the promise of calculus, the kinds of problems that calculus should be able to solve, were almost all solved by Euler in the 18th century. Euler was born in 1707 near Basel, the son of a preacher. He would go to the University of Basel with the intention of studying theology, but Johann Bernoulli quickly spied this young man as a man with incredible mathematical talent and encouraged him to pursue the mathematics. Euler would actually spend most of his life in the two capital cities of St. Petersburg in Russia and Berlin in Germany, and he was incredibly prolific. He wrote over 860 research papers. His collected publications run to over 25,000 pages. He worked in all areas of mathematics. You find a lot of work on analysis or calculus, geometry, and number theory. He also worked in mechanics and really laid out a systematic approach to mechanics using the foundational ideas of calculus in order to understand the important mechanical problems that are out there. He worked in optics. He worked in astronomy. One of the important questions of the 18th century was predicting the exact position of the moon. Very complicated because the moon is pulled not just by the Earth, but also by the sun. And Euler did a lot of the important breakthrough work in showing how to find the position of the moon. Euler also set up the science of fluid dynamics, understanding how, say, an airplane wing goes through the air or how a ship goes through water. Of course, Euler wasn't studying airplane wings, but the kind of fluid dynamics he was doing would enable later scientists, later engineers to model airplane wings. He actually was interested in shipbuilding, not just the fluid dynamics, but actually designing ships. He did work in navigation and ballistics and cartography. He was also interested in science education, and he wrote the first arithmetic books for use in the Russian school system. And in fact, much of the Russian school system in mathematics can trace its lineage directly back to the innovations of Euler during his years in St. Petersburg. In Berlin, he would become director of the Astronomical Observatory, and working for the Emperor Frederick the Great, he would do many other things that one would not expect a great mathematician to do. Apparently, he designed spectacles for Frederick the Great and also designed water fountains for Frederick's pleasure. He was not only a scientist with great scientific insight, he was really interested in exposition. And Euler would publish 25 expository books on mathematics, on science, on philosophy, on music. One of the most popular books of the 18th century was a book written by Euler called Letters to a German Princess, in which he explained to a general audience of lay people basic ideas of science and astronomy. Euler is also remarkable in that for the last 12 years of his life, he was totally blind. His eyesight was bad throughout much of his life, but he was blind for the last 12 years, and yet this did not slow down his production. He would produce papers, turning them still out at the rate of almost one a week for much of the time after he was blind. And at his death, there were still 3,000 pages of scientific articles that were waiting to be published. Clifford Truesdell, one of the great historians of mathematics, someone who has studied Euler and his period quite closely, has stated that over the 75 years from 1725 to 1800, Euler accounted for 1/3 of all of the published research in mathematics, mathematical physics, and engineering mechanics. It's not a stretch to say this was the greatest mathematician who ever lived. This certainly was a man who dominated his century. Some of his most important mathematical work was in applying the ideas of calculus to dynamical systems, systems that are in change or in flux. And to do this, you set up differential equations, equations that relate derivatives to the function that you want to actually study. Euler also showed how the use of power series, these polynomials of infinite degree, were absolutely essential to studying these problems in dynamical systems. And there was a very important work that Euler published in 1748 that talked about these power series and how to get them. It was called Introduction to Analysis of the Infinite. And if you take a look at the most important books in mathematics that have ever been published, certainly Euclid's Elements stands there as the most important. That absolutely is foundational. But if you look for the second most important book, there is some controversy. One of the candidates is Al-Khwarizmi's book on algebra and Al-Muqabala, in which he sets out the basis for algebra. Another candidate is certainly Newton's Principia. That is not a work specifically on mathematics, although just the mathematical portion of it is so important that it might be considered the second most important book in mathematics. But a very real candidate for the second most important book in mathematics is Euler's Introduction to Analysis of the Infinite. And in that book, Euler finds the power series for the exponential function. Recall when I talked about Napier, we've got this idea of the exponent as a variable. So we can think of 2 raised to the x power, where x can be any real number whatsoever. Or what was found in the 17th century, the base that you want to use in an exponential function is actually the base of the natural logarithm. If we take this number e, it's about 2.71, and raise that to the x power, we get a remarkable function whose derivative, that is to say the slope of the tangent line at any point, is again equal to e to the x. This is the remarkable function whose derivative is actually equal to itself. In this book, Euler talks about the power series expansion of e to the x, the power series expansion of the trigonometric functions, the sine and the cosine. And in order to do this, he has to make some assumptions about the sine and cosine. And I need to back up here to my earlier discussion about these two functions. Remember that the sine is actually the half chord. So you take an arc of a circle, you consider the chord that connects the two endpoints of that arc, and then you take just half of that chord and half of the arc. So the sine is a function of that half arc, and it returns the value of the half chord. Now, the value of the half chord is going to depend on the size of the circle that we start with. And in Newton's Principia, when he uses trigonometric functions, and he uses them quite often, he is using the sine in this sense. For him, the sine of a given arc does not have a single value. The value of the sine depends on the size of the radius. And of course, this is part of the reason why, when we go back to the ancient astronomers, people like Ptolemy and the Indian astronomers who followed him, they would use that circle with the very strange sounding radius of a little bit more than 57 degrees, because if the circumference is 360 degrees, the radius is going to be a little bit more than 57 degrees. What Euler does is to, instead of working with a radius that is designed to match to a circumference of 360 degrees, he decides to work with a radius of 1. And if the radius is 1, that means that the circumference is 2 pi. And so the argument in Euler's trigonometric functions is going to be a fraction of 2 pi. If we want an arc that is a quarter of a circle, that's going to be a quarter of 2 pi, or pi over 2. And if we want an eighth of a circle, what we would think of as 45 degrees, that's going to be pi over 4, 1/8 of the full circumference of the circle of radius 1, 1/8 of 2 pi. Now, setting up the power series in this way, Euler then observes in this groundbreaking work that you can take the exponential function with an exponent that is not just any real number, but an exponent that is actually any complex number, any number made up of a sum of a real number and a square root of a negative number. And it's Euler who really has the fundamental insight into the importance of these complex numbers, these combinations of real numbers and imaginary numbers. And he shows how to take an exponent with an imaginary number in the exponent. And the result that he gets is that e raised to a power I times x. I is the square root of -1. So I times x is the square root of negative x squared. So he's taking e and he is raising that to an imaginary power. And Euler realizes that that is equal to a complex number where the real part is the cosine of x, and the imaginary part is I times the sine of x. And Euler now begins a process that would not be laid out clearly until we get to Gauss in the 19th century. But he begins this process of understanding complex numbers as legitimate, honest numbers that represent positions in a two-dimensional plane. If I've got a complex number like 2 plus 3i, what that means is that I've got a horizontal axis that tells me what my real number is, and I've got a vertical axis that tells me what my imaginary number is. And 2 plus 3i is found by going 2 units to the right along the horizontal axis, and then 3 units up parallel to the imaginary axis, so that every complex number, like 2 plus 3i, represents some point in this complex plane. And all we're doing is extending the idea of numbers along a real line to numbers that exist in the complex plane. Now, what if I take e and I raise it to a complex power? Let's consider e raised to the power 2 plus 3i. Well, remember that any exponent where you've got a sum of two things in the exponent, 2 to the 4 plus 7, is the same as 2 to the 4th times 2 to the 7th. So e to the 2 plus 3i is e squared times e to the 3i. E to the 3i now is this point in the plane. It's the cosine of 3 plus I times the sine of 3. So e to the 3i is a point in the plane. Cosine of 3 plus I times the sine of 3, if I take the real part of that number, square it, and the imaginary part of that number, square it. So I take cosine squared of 3 plus sine squared of 3. That's going to equal 1. That's really the Pythagorean theorem. And it doesn't matter what x I put in there, the cosine of x squared plus the sine of x squared is always 1. So if I take e to the ix, in this case e to the 3i, that's always going to be a point that lies exactly 1 unit away from the origin. The e squared tells me the magnitude of that line. So e to the 2 plus 3i says that I want to move in a direction that corresponds to an arc of length 3 on a unit circle, and then E squared tells me how far out to move along that particular line. So, for example, if I want the point in the complex plane that is exactly E units away from the origin and is at an angle of 45 degrees above the horizontal line, well, 45 degrees corresponds to an arc length of pi over 4. And so this is going to be, E is the distance, so I take E to the 1 plus pi over 4I is going to take me out to that point in the complex plane that is E units from the origin, and it's at an angle, at an elevation of pi over 4, what today we call radians. That actually is a 19th century term. But this idea of going an arc length of pi over 4 in order to find the elevation at which you want to move out from the origin. And we're going to see in the following lectures that this idea of understanding the complex plane in terms of exponentials of complex numbers is absolutely foundational to almost everything that's going to happen in the 19th and 20th and 21st centuries. When Euler was growing up, his father actually was a friend of the Bernoullis. Euler, as I mentioned, first went to the University of Basel with the intention of studying theology. In 1726, at the age of 19, Euler published his first paper. He actually took the isochrone problem that the Bernoullis had solved, and he considered what would happen if you've got this ramp and these sliding balls, but instead of sliding in the absence of any kind of friction, you've got some kind of resisting medium through which the balls are going. So you might be looking at a ramp submerged in water, or you might be considering the effect of air resistance on the motion of these balls. That's going to change the shape of the ramp so that it's the same time to the end of the ramp no matter where you start. And this was the first result that Euler actually published. And this was the beginning of his very important work on fluid dynamics. Fluid dynamics turns out to be an extremely difficult area. It would not really be understood until the 19th century, but the foundations of fluid dynamics were laid by Euler in the 18th century. But he graduated from Basel and he needed a job, and it happened at that time that Peter the Great in St. Petersburg was establishing his own Academy of Science. And he invited two of the Bernoullis to go there. This was actually Johann's son Daniel, who I mentioned briefly in the previous lecture, and also an older son, Nicholas. Johann Bernoulli had hoped that Nicholas would become a mathematician, but he did not want Daniel to also become a mathematician. As he told his son Daniel, there is no money to be made in mathematics. Johann had originally intended to be a doctor, and so he greatly encouraged Daniel to go off and learn medicine. Daniel, in fact, did go to Italy in order to study medicine, but while he was at university, he snuck in some math classes, and that convinced him that mathematics was what he really wanted to do. And despite his father's wishes, he began publishing in mathematics, made his reputation as a mathematician. And eventually his father, Johann Bernoulli, had to admit that he was capable. But Johann always thought of Nicholas as the greater mathematician. But when Peter the Great set up the academy, he invited both Nicholas and Daniel to come and be members of this new Academy of Science. Unfortunately, shortly after they arrived, Nicholas suffered appendicitis. His appendix burst, and he died shortly after he got there. Daniel seriously considered going back to Switzerland at this point, but another option opened up because Euler was looking for a job. And Daniel managed to convince the Russian court. At this point, it was Catherine who had succeeded Peter the Great. He convinced Catherine in order to invite Euler to come and join him. And the two of them would then work together on incredible work in dynamics. Daniel Bernoulli and Leonhard Euler actually would live together in St. Petersburg for a number of years, and together publish many, many important joint papers developing the ideas of the calculus. They would look at a lot of dynamic systems, things like springs, vibrating strings, drum heads, the vibration of drum heads and modeling that, also fluid dynamics and aerodynamics. Euler would originally go as a professor of physics. In 1733, Daniel finally got tired of St. Petersburg and left, and Euler took over his position as chair of mathematics at the Institute. That same year of 1733, Euler married Katharina Gesell. She was the daughter of a Swiss painter who was working for the Russian court. And in 1735, Euler really made his reputation as a mathematician by solving one of the great open problems that was out there at the time, which is summing the reciprocals of the squares. If we consider 1 plus 1 over 4 plus 1 over 9 plus 1 over 16 plus 1 over 25, and continue forever. The Bernoullis had shown that this in fact does approach a fixed value, but they couldn't figure out what that value was. And it was Euler who showed that this particular infinite summation approaches the quantity the square of pi divided by 6. Some brilliant mathematical work that really made Euler's reputation as somebody to watch out for. It was in 1738 that Euler picked up an infection in one of his eyes. He fairly quickly lost sight in that eye, and his eyesight was never good in the remaining eye throughout the remainder of his life. In 1741, he was invited by Frederick the Great to go to Berlin as director of the astronomical observatory there. In Berlin, he was in the company of the great philosophes, the great philosophers, French philosophers of the Age of Enlightenment. Voltaire was there, Maupertuis, Diderot, Montesquieu. Frederick loved the company of these great conversationalists. Euler was a brilliant scientist. He was not a great conversationalist. He had little time for that. And Frederick was quite disappointed in this mathematician that he had hired. And in fact, he is quoted as having referred to him as that huge cyclops of a mathematician. Euler was never really very happy in Berlin. He did wind up staying there for 25 years. But he really had enjoyed St. Petersburg and the kind of scientists and other mathematicians he'd been able to work with there. And finally, in 1766, he was able to return to St. Petersburg, and he would spend the rest of his life there. He contracted a cataract in his remaining good eye. In 1771, he underwent cataract surgery. And I hate to think of what cataract surgery was like in 1771. Unfortunately, the operation was not successful, and at that time he completely lost the sight of his remaining good eye. 2 years later, his wife Katharina died, and Euler married her half-sister, and I think this was probably a marriage of convenience. He needed somebody who could help him, who could take dictation, and since he was totally blind, help him get through the day. But he was still a brilliant mathematician doing brilliant work. And he died what has got to be a happy death. He died in 1783. He died very suddenly of a brain hemorrhage. It's known that he was at home, he was playing with his grandchildren at the time that the hemorrhage hit. I want to say just a little bit more about some of the other things that Euler studied. He was also very interested in the harmonic series, the sum of the reciprocals of the integers, 1 plus a half plus a third plus a quarter, and so on. This does not approach any finite number. It gets arbitrarily large. But one of the things that Euler realized is that it grows like the logarithm of the largest number whose reciprocal we take. So if I take this sum of reciprocals up to 1 over n, That's about equal to the natural logarithm of n. This is Napier's logarithm with the base that's about 2.71. But Euler went beyond that. He was interested in how big is that error? How close are we? And he was able to show that the difference between the sum of the harmonic series and this natural logarithm is about 0.577. It's a number that today we refer to by the Greek letter gamma, and it's usually called Euler's gamma, for Euler was the first person to find this particular constant. Euler was also interested in Fermat's work in number theory, and many of the problems that Fermat had put out there, results that Fermat had stated, without proof, Euler then went through and proved them, or showed that in fact they were not true. Euler took a look at Fermat's last theorem. The very first case is the case of x cubed plus y cubed equals z cubed. And Euler published a proof that you could not find three positive integers that satisfy this equation. In fact, his proof was not quite correct. There are some gaps in his proof, although if you look at all that Euler did understand about number theory, there is enough in his corpus of work that you can take other pieces of what Euler knew and fill in those missing gaps. And so, in some sense, it is still appropriate to credit the proof of this first case of Fermat's last theorem to Leonhard Euler. In the brief time I have left, I want to say just a little bit about some of the other mathematicians of the 18th century, because in the next lecture I'm going to start moving into the 19th century. One of the greatest of the 18th century mathematicians was Jean-Léon d'Alembert. He worked with Euler on many projects. There also was some competition between him and Euler. D'Alembert worked on many of the same problems in dynamical systems that Euler would work on: vibrating strings, vibrating drumheads. Another great mathematician of this era is Joseph Louis Lagrange. Born in 1736, he would die in 1813. He actually was an Italian mathematician who adopted a French form of his name, and he would succeed Euler to Euler's position at the Science Academy in Berlin when Euler went back to St. Petersburg. In fact, it was Euler who had recommended Lagrange for this particular position. In 1787, Lagrange moved from Berlin to Paris. He began to work at the Academy of Sciences in Paris. He managed to survive the French Revolution, and in 1794, one of the first acts of the new French Republic was the establishment of a technical university, the very first institute of technology in the world, the École Polytechnique, founded in 1794. Lagrange was appointed as one of the first professors at this technical university, and he would be one of those who was very much responsible for setting it out there as one of the great institutes of learning, and especially learning in technical subjects in the world. Another mathematician that I want to say a little bit about is another woman mathematician, Maria Agnesi. Born in 1718, she would die in 1799. She was an Italian, as the name suggests, and she was the first person to write a calculus text in Italian. It was a 2-volume work explaining the ideas of calculus and really going into a great deal of depth in how to use these ideas and what they meant. Her book was insightful enough that it was fairly quickly translated into French and to many other languages and used quite widely. And because of her reputation that she managed to establish with the publication of this calculus text, she was actually offered the chair of mathematics at the University of Bologna. This was in 1750. Maria Agnesi's father had died at about the same time that the chair was offered to her, and at that point she decided to enter a convent and devote the remainder of her life to good works. And so she turned down the chair. She had the chance to be the first woman chair of mathematics in a European university. She would not be that because she turned it down. That honor would go to Sonia Kovalevskaya at the end of the 19th century. As I said at the beginning of this lecture, by the end of the 18th century, there was this feeling that Euler had solved all the really important problems that were out there, and there was no more really important mathematics to be done. In fact, that's not at all true. There was a whole new way of looking at mathematics, a mathematics based on geometry and transformation. And this will be the subject of my next lecture. In this lecture, we're going to look at a new element in the development of mathematics. We're going to see how art has really influenced geometry and all of mathematics within the past few centuries. I've been standing in front of a picture of the Lion Court at Alhambra in Granada because it's an excellent example of symmetry in art. There is all kinds of symmetry throughout Alhambra, and symmetry is really fundamental to much of what artists do. To be symmetric means to be left unchanged under some kind of a transformation. And as we look at the Lion Court at Alhambra, we see that if we do a mirror reflection of the building, this is a kind of transformation, shifting the left for right in a mirror image. Under this transformation, the picture is left unchanged. Quite intentionally, of course. It was built so that it would have that symmetry. The Lion Basin at the center also has a symmetry, a different kind of symmetry. It does have this mirror symmetry, so that if you look at the reflection of that basin, you get back exactly the same basin. But if you were to look down on the basin from above, you would see that it is surrounded by 12 lions, equally spaced, around the circumference of the basin. And so this means that if I take this configuration, the circular basin, with its 12 lions, and I rotate it by 30 degrees, I'm not going to change the configuration that I've got. And so we say that this basin has 12-fold rotational symmetry. I can rotate it 12 times by 30 degrees each time, and each time I rotate it, I get back to exactly the figure that I had before. There's another kind of transformational symmetry that occurs in Alhambra and that is present throughout the palace, and that is translational symmetry. The idea that you've got a pattern and that pattern repeats as you move horizontally or it repeats as you move vertically. Such a pattern is often referred to as a wallpaper pattern. And the first of the illustrations of the kinds of tiling patterns that are at Alhambra is shown in this particular picture that shows this translational symmetry. And the thing about a pattern that has translational symmetry is that you can tile a surface of arbitrarily large size. The pattern is going to continue off forever in all directions, which has a fundamental religious truth hidden within it for the Islamic creators of this particular piece of art, the idea of the infinitude of creation. But it also is very appealing to create a pattern that has this kind of translational symmetry. Now, this particular pattern at Alhambra has more than translational symmetry. It also has rotational symmetry. We've got figures here where if we rotate them by 120 degrees, we get back exactly the same figures. Now, there are colors within this tiling pattern that disrupt some of the symmetry, and I think there was an intentional effort on the part of the artist to have the symmetry and yet have something that seems to break it. But if we just look at the geometric patterns, we see that not only do we have translational symmetry, we also have a threefold rotational symmetry. There is another type of translational symmetry or wallpaper symmetry that is shown in the next picture that shows a six-fold rotational symmetry. Now, if I take this pattern, which is going to repeat arbitrarily in both horizontal and vertical directions, and I rotate it by only 60 degrees instead of 120 degrees, I'm going to get back to exactly the same wallpaper pattern that I had before. Here is yet another example of a wallpaper pattern that is present in Alhambra. This particular pattern has fourfold symmetry, so I can rotate it by 90 degrees and get back to the original pattern. It almost has mirror symmetry, but if you'll notice, some of those bands that outline the figure actually overlap in ways that it doesn't quite have perfect mirror symmetry. And there's something very interesting going on here. You've got translational symmetry. You have, at first glance, mirror symmetry, and yet the artist has been quite clever in breaking that mirror symmetry, so it's not really quite there. It invites the observer to look at the pattern more closely and think about what's going on. Another example of a wallpaper pattern is given in Alcazar, the castle in Seville. This is actually taken from a metal door in the castle, and it shows another wallpaper pattern that has both fourfold rotational and mirror symmetries, but they're quite different from the other fourfold or mirror symmetry that we saw in the previous picture, in that in this particular case, the rotational symmetry has its center in the center of those circles, whereas the mirror symmetry is located at a different point. The mirror symmetry is located at the center of these lozenges. So one can have a wallpaper pattern that has both fourfold rotational and mirror symmetry, either with the centers of both of these symmetries at the same point, or you can have a pattern that has these symmetries at different points. So we've been looking at different kinds of symmetries, different kinds of transformations that leave a picture unchanged. We've looked at the mirror symmetries, we've looked at rotational symmetries, we've looked at translational symmetries, we've looked at various combinations of these. Another important kind of symmetry is what is called a dilation. And we see this quite clearly in the kinds of images that are often used where you have a picture, and inside that picture there is a smaller picture which is an exact copy of the large picture. And inside that small copy of the large picture there is an even smaller copy of the large picture, and this continues off to infinity. We call this dilation symmetry because if I take that small picture that's inside the large picture and I expand it out to the size of the original large picture, I get back the original large picture. So this is a transformation, this idea of dilating that small picture, expanding it out, or a dilation can be a contraction. So the dilation is either expansion or contraction, and to have a pattern that is left unchanged once I accomplish that particular expansion or contraction. The graphic artist Moritz Escher, born in 1898, died in 1972, traveled to Alhambra in 1922. He was quite taken by the art of Alhambra, and he returned there in 1936 and began to do an extensive study of the kinds of symmetry patterns that he saw in the Alhambra, in the tiling of the walls, and the various kinds of transformations that were used. And he became fascinated by this idea of patterns that are left unchanged under various kinds of transformations. And he actually went back to the Netherlands, where he was from, After spending several months at Alhambra in 1936, he went back and he began to explore the mathematics behind it. There was a very important paper on these wallpaper patterns that was published by George Polya, one of the great Hungarian mathematicians of the 20th century, a paper that Polya had published in 1924, looking at all of the different ways you can take a wallpaper pattern and combine it with other kinds of symmetries, rotational symmetries, mirror symmetries, and so on. And one of the things that Polya shows in this paper is that there are exactly 17 different types of wallpaper patterns. If you've got a pattern that's going to repeat indefinitely in the horizontal and vertical direction, what kind of rotational symmetries can it have? What kind of mirror symmetries can it have? In fact, there are 17 of them. That result was not original to Polya. It had first been done in 1885 by Fedorov. And there are interesting questions that raises. What if instead of a translational pattern in 2 dimensions, you think of a crystal pattern, a translational pattern in 3 dimensions, which is going to be unchanged as you translate horizontally or vertically, or translate in the 3rd dimension of depth? How many ways can you combine such an invariance with various rotational and mirror symmetries? It turns out that in 3 dimensions there are lots of ways of doing it. There are 320 different ways of combining 3-dimensional translation invariants together with other symmetries. Escher began to create drawings, graphic art that used all of the wallpaper patterns. And fairly quickly, he began to move beyond that and look at other transformations that mathematicians had been studying, and looking for creating art that was unchanged under these particular transformations. And one of the most important groups of transformations that mathematicians would use, it's a group that would come into importance in the 19th century, and as you will see, would actually come to play a role in the ultimate proof of Fermat's last theorem. This is a group of transformations that are known as the modular transformations. And they're one of the reasons why I talked about complex numbers and the complex plane so much in the last lecture, because understanding the plane as being made up of complex numbers is critical to understanding these modular transformations. So there are 2 basic modular transformations. The first of these is to take the object and translate it by 1 unit to the right or to the left. So one of the things about any of these transformations that they're studying is that they can always be reversed, and you can always then build on them. So if I can take my picture and move everything 1 unit to the right and it doesn't change, then if I move it another unit to the right, it again won't change. And so we get a translational symmetry, but only in the horizontal direction, not a vertical translational symmetry. The second symmetry that comes to play a role in the modular transformations is a kind of inversion. What you do is to take a point in the complex plane, let's denote it by the letter Z, and that gets translated into the point which is the negative of the reciprocal of Z. To understand what happens if I take a point in the plane, I want to think of this point in the plane as being represented by an exponential with a complex exponent. And in the last lecture, I explained how this can be done. If I've got a point in the plane, I need to figure out how far that point is from the origin. If it's e squared away from the origin, then that's going to be that distance, and that will go into my representation of this number. That will be the real part of the exponent, the number 2. And then if the angle of elevation is pi over 4 radians, or in other words 45 degrees, that goes into the complex part of the exponent. And so this complex number that is e squared away from the origin and at an elevation of 45 degrees, or pi over 4, is represented by e to the 2 plus pi over 4 times I. Now I want to take the reciprocal of that number. If I take the reciprocal of that number, that means taking the negative of the exponent. So instead of looking at e to the 2 plus pi over 4i, I'm going to look at e to the minus 2 minus pi over 4i. Now, the distance from the origin has changed from e squared to e to the minus 2. And when I take the reciprocal of any complex number, what's going to happen is that the distance from the origin turns into the reciprocal of that distance from the origin. If I've got a complex number that is 5 units from the origin, its reciprocal will be a fifth of a unit from the origin. Something different is happening with the angle, though. The angle had been pi over 4 radians, an arc of pi over 4. That turns into minus pi over 4. So instead of traveling in a positive direction from the positive real axis, in other words, instead of traveling counterclockwise, we travel pi over 4 radians in a clockwise direction. Instead of moving above the real axis, we now move below the real axis. And so to take the reciprocal of a number is, first of all, to replace its distance by the reciprocal of that distance, and then to reflect that number over the real axis. So take the reflection across the real axis. Now, in the case of a modular transformation, we're taking z and replacing it not with 1 over z, but the negative of 1 over z. So there's one more action that has to take place. We take the distance, replace it by the reciprocal of the distance. We take that remaining point and reflect it over the real axis. And now we take the negative of that number. And to take the negative of a complex number, you simply draw the line from that number through the origin and go out the opposite side of the origin exactly the same distance. Now, one of the things that this does, if I start with a complex number that is in what we call the upper half plane, so I start with a complex number where the imaginary part is positive. It lies above the real axis. And I take the negative reciprocal of that number. That's going to change the distance from the origin. It's going to flip that number across the real axis, so I'm now below the real axis. And then when I take the negative, I wind up back above the real axis. So this transformation is one that takes a number that is above the real axis and turns it into another number that is above the real axis. And we can now start to combine these transformations to get all of the modular transformations. So, for example, if I take the region that is shown in this particular picture, the gray region that is in here, it's what is called the fundamental region. And all of the other spaces that you see above the real axis can be reached by some combination of these modular transformations. So I can start with some point in this gray region in my fundamental domain, and I can move it by 1 unit to the right, and I'm now in this second region. And I can now take the negative reciprocal of that, which moves me into this small region, which is down near the axis, down near the real axis. I can now move it 1 unit to the left, and then take the negative reciprocal again, and I get into one of these even smaller regions that is even closer to the real axis. And so any of the regions that you see can be reached from my original fundamental domain by some combination of these transformations that are called the modular transformations. Well, to get back to Escher, he was fascinated by this idea of these kinds of modular transformations. And in particular, what he realized is that you can take this upper half plane and you can wrap it up into a circle. And what you get is a figure that is shown in this piece of graphic art, which is called circle limit 3. that really illustrates what is going on and all of the kinds of symmetries that are inherent in the modular transformations. Modular transformations, as I said, will be very important to the mathematics we'll be looking at after this. And so we'll be coming back to Escher's circle limit 3 very often in the succeeding lectures. Another type of transformation I want to talk about is one that is credited to August Möbius from Leipzig. He was a student of Gauss. He was actually an astronomer. And his name is generally associated with the Möbius band. If I take a strip of paper, this is colored differently on the two sides, and I put it together, something like this, we have a clear inside to the band, and we've got a clear outside to the band. But if I put a half twist into it, something like this, you can see that now we have a band with only one side. As we come around to the brown side, it turns into the orange side, and the orange side goes around and it turns into the brown side. There is only one side to a Möbius band. Actually, Möbius was not the first person to come up with this idea of a one-sided band. Johann Listing was the first person to do it about a decade earlier, but Möbius made it famous. Now, the group of transformations that Möbius looked at were made up of translations, rotations, dilations, and simple reciprocals. And there's a very useful way of taking a look at this particular combination of transformations. And I want to show you a short video clip now that was put together by two friends of mine at the University of Minnesota, Doug Arnold and Jonathan Rognus. So we're going to look at the Möbius transformations. These are fundamental to many, many different areas of mathematics. And as I said, the basic transformations are translation, and here we see a region that is being translated, dilations, expansions, and contractions, rotations, and then we also have this process of taking the reciprocal. And this shows what happens as we take the reciprocal or the inverse of the points in the complex plane. We can combine the Möbius transformations, and we see here some of those combinations. This was an inversion combined with a translation. We're going to see how to combine the Möbius transformations in a slightly different way that really illustrates very nicely what's really going on using something called a projection. Rather than just working with the plane, we're going to consider a sphere that sits above that plane, and we look at a region of the sphere that is projected down onto the plane. We get our translations by moving the sphere around the plane, our dilations by moving the sphere up and down, our rotations simply by rotating the sphere. And the inversion then becomes a very simple operation on the sphere. It is simply rotating the sphere across a horizontal axis. And we can now combine these Möbius transformations just by combining motions of the sphere. So I get a rotation of the sphere about a horizontal axis, followed by a rotation of the sphere around a vertical axis, followed by moving the sphere. We get our translation, and that gives us one of the Möbius transformations. What we've seen in this video clip is actually another type of transformation that will play a very important role, and that's the idea of a projection. Taking a region or a collection of points that lies on one surface and projecting it onto another surface. That was what was done. We took a region on the sphere and we projected it onto the plane. And projections will come to play a very important role in mathematics, and they trace their ancestry right back to the understanding of perspective. A lot of the artists of the Renaissance were very interested in developing this idea of perspective, and they tended to be very mathematical. Many of the great artists of the Renaissance, people like Piero della Francesca and Leonardo da Vinci, were artists, but they were also interested in the mathematics of the art, and they saw how to combine these two. One of them that I want to talk a little bit about is Albrecht Dürer from Germany. Born in 1471, he would die in 1528. He was born in Nuremberg. He went to Italy to study. That, after all, was the place to study both art and also mathematics at this time. He went to the University of Bologna and he studied mathematics with Pacioli. He came back to Germany and he actually wrote the first book of mathematics in German. He wrote actually a number of books on mathematics, one of which was on compass and straightedge constructions. And I want to show you one of the pictures that Albrecht Dürer created using compass and straightedge constructions. It does not look like your standard compass and straightedge construction. This is his Adam and Eve, created in 1504. Obviously, there are more lines in there than just what was created with a straightedge and compass. But the importance is that the outline of the figures and the basic proportions were all worked out very geometrically. Dürer's St. Jerome, that was created in 1514, is an excellent example of the use of perspective. There are very clear lines of perspective, and one of the interesting things that comes through this perspective is that you see how shapes change. If you look at the pot that is hanging from the ceiling, the bottom of that pot certainly is a circle, but looking at it from the side, looking at it in perspective, it no longer looks like a circle, it looks like an ellipse. And that's one of the important aspects of perspective or projection, is how an object looks one way initially, and then as you project it, it changes its appearance. And this property is something that would be studied extensively in the 19th century. We know projections from a number of sources, and especially the Mercator projection, which is the way we have of representing the surface of the Earth. This was developed by Gerardus Mercator, lived 1512 to 1594. And the idea here is that you've got a spherical Earth, and we want to represent that surface on something that is flat, so we wrap a cylinder around the Earth, and we take a vertical line that runs through the Earth, a line that runs from the North Pole to the South Pole, and we simply project out from that line through the surface to the Earth onto our cylinder. And that is the standard representation of the Earth that you see in most maps, known as the Mercator projection. And it is a projection from the surface of a sphere onto this cylinder. And once we've got the surface of the Earth represented on the cylinder, we can simply slice the cylinder and unroll it in order to get a rectangular map. Someone who did important work on projections was Jean-Victor Poncelet. He was born in 1788, died in 1867. He was a student of Monge, one of the great geometers of the 18th century. Monge was somebody who joined Lagrange at the École Polytechnique, teaching at that illustrious school. Poncelet did go to the École Polytechnique and learned from Monge there. And Poncelet was particularly interested in the properties that are left unchanged when you do a projection. So as we saw in perspective, a circle becomes an ellipse, but you can't find a perspective that changes a circle into a square. What kinds of figures can you get under what kinds of projections? This is the problem that Poncelet studied. And as he studied this, he realized that there was a basic duality between points and lines. If I've got 2 points in the plane, there is a unique line that goes through them. If I've got 2 lines in the plane, they are going to cross at a unique point. Well, almost. The 2 lines in the plane might be parallel lines. But Poncelet decided that he wanted these parallel lines to meet, and so the natural place for them to meet is out at infinity. And so you get what is known as the projective plane, where you include this point at infinity as one of the possible points, so that every pair of lines gives you a point, every pair of points gives you a line. The basic idea behind the projective plane is to take all of the lines that radiate from the origin in three-dimensional space and replace each one of those lines by a single point. Now, it becomes very difficult to actually work this out, because in order to do this, to see the resulting surface that you get, you actually need to think in four-dimensional space. But geometers have been very ingenious in trying to visualize what the projective plane looks like. And I want to close this particular lecture by looking at one of those representations. Again, the projective plane really can only be seen in four-dimensional space. But the Boy surface, named for Werner Boy, who came up with this representation in 1901, is one of those who found a way of showing it. It really exists in four dimensions, but we get some idea of the complexity of this projective plane. In the next lecture, we're going to continue look at Gauss and his contributions to the development of geometry. In Lecture 15, I talked about Leonhard Euler, the greatest of all mathematicians. But if there is one person who might challenge him for that title, it's Carl Friedrich Gauss, about whom I'm going to talk in this particular lecture. Gauss is responsible for referring to mathematics as the queen of the sciences, and largely because of that, later mathematicians and historians of mathematics would refer to Gauss himself as the Prince of Mathematics. Gauss was born in 1777. He was born in Brunswick, the son of a laborer, and eventually the Duke of Brunswick would become his patron and support him through his early work in mathematics and the sciences. The Duke of Brunswick, unfortunately, was killed during the Napoleonic Wars, and so Gauss would need to seek employment, and he would become director of the Astronomical Observatory in Göttingen, and eventually he would take a position as chair of mathematics at the University of Göttingen. He did absolutely groundbreaking work in a number of areas of mathematics, including algebra, geometry, and number theory. He also did very important work in astronomy. And one of the important results that he did, one of the things that really made his mark as an astronomer, was when the asteroid Ceres was spotted in the heavens in 1801. It was spotted just before it passed behind the sun. And only a few observations had been made, and astronomers tried to figure out where the asteroid would reappear as it came out from the other side of the sun. And Gauss was among those who did those calculations, and Gauss's calculations were the most accurate. He was able to, just from a few observations before the asteroid disappeared, he was able to predict the exact location and the exact time when Ceres would reappear. Gauss is also noted for his work in electricity and magnetism. The unit, the Gauss, that is common in this field is named directly for him. One of his important books early in his career was a book on number theory called Investigations of Arithmetic, published in 1801, and this is arithmetic in the sense of Diophantus's Arithmetica. So he calls it arithmetic, but what he really means is what today we refer to as number theory, the study of the integers. And this received a lot of attention throughout Europe, and one of the people who became fascinated by this book and began to study it was a woman by the name of Sophie Germain. Sophie Germain had been born in 1776. She was interested in questions in algebra and questions in number theory, and she corresponded with a number of the great mathematicians of the time, including Lagrange and also Gauss. And she went under the pseudonym of Monsieur Leblanc. She was afraid that if she admitted the fact that she was a woman in her correspondence, people would not take her seriously. Eventually, both Lagrange and Gauss realized that they were corresponding with a woman, and we know that Gauss was quite delighted to discover that there was a woman who was doing such important work in mathematics. We're going to be returning to Sophie Germain later on when I talk about Fermat's last theorem, because she will be one of the many players in the story of the eventual proof of Fermat's last theorem. But in this lecture, I want to focus on Gauss's work in geometry. And I'm going to back up a bit, right back to Euclid's Elements. Euclid's Elements include 5 postulates, 5 axioms, 5 things that he assumed in order to be able to proceed with the development of geometry. The first of these is that if you have 2 points in a plane, they determine a line, and there is only one line that goes through these 2 points. If you've got a point and a length that denotes the radius, that uniquely determines a circle. All right angles are equivalent. And the 5th postulate is a rather strange sounding one. It says that if you've got 2 lines and you've got another line that cuts across it, and you take a look at the 2 interior angles of the line that cuts across, if both of those angles are less than right angles, then the original 2 lines must meet someplace on that side of the transversal. This is known as the parallel postulate, and it's a little bit easier to state what's going on if it's put in an equivalent form. People fairly quickly realize that this 5th postulate is equivalent to saying that if we've got a line, and if we've got a point that is not on that line, we're working in a plane, then there is exactly one line that passes through that point and never intersects the given line. So there is one parallel line through this other point. And this was a postulate that a lot of people wondered whether it was really needed. Is it possible simply to take these natural assumptions about geometry and show that the parallel postulate must follow from those? There seems something arbitrary about the parallel postulate. And a number of people tried to do this, to find a way of proving the parallel postulate, or at least reducing it to something that seemed obvious, where it was clear that there had to be one line through this point, and only one line through this point. One of the people who made progress on this was Girolamo Saccheri, born in 1667. He died in 1733. And he looked at what would happen if there was no line through this point that did not intersect the given line. In other words, there's no parallel line. Every line through the point must intersect at some point. Or what would happen if there's more than one line through this point that never intersects the given line. And what Saccheri was able to show is that if there is no parallel line, then the sum of the angles in any triangle must be greater than 180 degrees. And if there is more than one parallel line through this point, then the sum of the angles in any triangle must be strictly less than 180 degrees. Now, we all know that the sum of the angles in any triangle is 180 degrees, so that seems to settle it. But in fact, all that shows us is that the parallel postulate and this result about the sum of the angles in any triangle are actually equivalent statements. If you know the sum of the angles in any triangle, you can derive the parallel postulate from that. If you know the parallel postulate, you can derive the formula for the sum of the angles in any triangle. But you can't really say that one is more obvious than the other. They simply are equivalent statements. The next person to really make progress on this is Johann Lambert, born in 1728. He would die in 1777. And he fairly quickly dismissed the possibility that you might have no parallel line through that point, But he was really concerned about this question of more than one line through the point that never intersects the given line. And how could you show that that could not happen? And he explored the kind of geometry that would follow if you could have more than one parallel line. And he came up with something that seemed totally impossible. He was able to show that if you've got more than one parallel line through the point, then if you look at the sum of the angles in a triangle, not only is that less than 180 degrees, but the sum of the angles in a triangle is going to depend on the area of the triangle. And that seems totally counterintuitive. Why should the sum of the angles in a triangle depend on the size of the triangle? We're used to Euclidean geometry where you can scale things up, and that does not change the sum of the angles in the triangle. But what Lambert showed is that if you've got this strange kind of geometry with multiple parallels, when you try to scale things up, that necessarily forces the sum of the angles to change. Well, real progress on this question really now begins to happen with Gauss, who studied geometry. He did not set out to study this problem of whether or not the parallel postulate is correct. He was interested in geometry on various kinds of surfaces. So considering the geometry on the surface of a sphere, or considering geometry on the surface of a cone, or some other two-dimensional surface. And he explored the idea of distance, so curves that trace the shortest distance between 2 points, or areas of pieces of these surfaces, and how to do that. And he realized that the key to finding distances or finding areas was really to use the key ideas of calculus, to go back to Leibniz's idea of the differential, this infinitesimal little change, and build up your distance by piecing together little straight lines, even though you might have a very curving surface. Build up your distance by these little straight lines, the infinitesimals, and use the techniques of calculus in order to define distance. In the same sort of way, you can use the techniques of calculus to define the idea of areas. Now, when we're working on a surface, say the surface of a sphere, there is something that corresponds to a straight line, but it doesn't look like a straight line in the normal sense. I live in Minneapolis, St. Paul, and there is nonstop service from there to Amsterdam. When I fly from Minneapolis to Amsterdam, though, I do not fly mostly east. Amsterdam is a little bit north of Minneapolis, St. Paul, but only a little bit. It's mostly east. Yet when my plane takes off from Minneapolis, I start out going almost due north. What I'm doing is traveling on a great circle. If we're on the surface of a sphere, the shortest distance between 2 points is given by what's called the great circle. And the great circle is defined by taking the plane that goes through the 2 points that I want to travel between and that goes through the center of the Earth. So I take a plane that includes my starting point, my ending point, and the center of the Earth. That plane is going to slice the Earth along an arc, and that arc is the great circle. That arc gives you the shortest distance between the 2 points that you want to work with. And so straight lines now correspond to, on a surface, straight lines become these great circles. And you can begin to build triangles on a surface out of these great circles. So, for example, one of the triangles that you can get is the triangle that goes from the North Pole down along a line of longitude to the equator. And then you take another great circle that goes from the North Pole along another line of longitude down to the equator. And then as the third great circle, you simply follow along the equator. And this gives you a triangle on the surface of the Earth, a triangle on the sphere. And if you think about it, each of these lines of longitude hit the equator at a right angle. So what I've got is a triangle that has two right angles plus another angle at the top. I've got a triangle where the sum of the angles is strictly greater than 180 degrees. And actually, if you think about it, if your lines are great circles, then if I take any great circle on the surface of the Earth, a complete circle, and I take any point that's not on it, and I look at any great circle that goes through that point, it must intersect the other great circle. There is no such thing as a pair of parallel lines when we're working on the surface of the Earth. And so this exactly agrees with Saccheri's prediction that if you don't have parallel lines, then the sum of the angles has got to be strictly greater than 180 degrees. Now, Gauss was also interested in something that is called curvature. So he looked at these surfaces, and a surface that is flat is said to have curvature 0. If I take a sphere whose radius is 1, Gauss said that that has curvature equal to 1. And as the radius gets smaller, as the surface turns more abruptly, the curvature is going to get larger. And so as I take smaller spheres, the curvature is actually going to be the reciprocal of the radius. So the curvature is going to get greater as the surface bends more sharply. The curvature gets closer to 0 as the surface begins to flatten out. Now, not every surface is the surface of a sphere, and so the general way that you have of trying to determine the curvature is to look at a piece of the surface and try to find that sphere that most closely approximates the way that surface is bending at that point. So a surface might have different curvatures at different points. And you can also have a surface that is bending in two different ways. Consider a saddle, where if you travel along it from the front to the back of the saddle, it curves upward. But if you travel over the saddle from side to side, it bends downward. And so what Gauss said, in this case, we have something that he called negative curvature, where in one direction it curves down, while at right angles to that, it's curving upward. And so every surface has a curvature. If it's a flat surface, the curvature is 0. And otherwise, it has either a positive curvature if it looks like a piece of the surface of a sphere, or a negative curvature if it looks like a piece of the surface of a saddle. And a nice example of a surface that has negative curvature every place is the Enneper surface. And I have a nice picture of a snow sculpture that was created by a colleague of mine at Macalester, Stan Wigan, and a team that he put together for a snow sculpting competition at Breckenridge. This Enneper surface stands about 8 feet tall, stood about 8 feet tall. It, of course, no longer exists. It did win second place in the Breckenridge snow competition, and they called it Rhapsody in White. And one of the things that Stan Wigan has pointed out is that surfaces of negative curvature are ideal for trying to do snow sculptures, because if you've got two different ways in which the surface is bending, that really tends to strengthen the surface. And so this is an idea that is often used in architecture. If you want interesting curved surfaces, do surfaces of negative curvature. They not only are aesthetically appealing, but they also tend to have greater strength than a surface that has positive curvature. Now, as I said, on the surface of a sphere, we've got positive curvature. And we also have the fact that the sum of the angles is greater than 180 degrees. And if you'll remember, what Lambert said was that the sum of the angles is going to depend on the area. And Gauss actually found a relationship between the curvature, the area of a triangle, and the sum of the angles. This today is known as Gauss's theorem. And what he proved was that if you take a look at your triangle and you figure out the total curvature of the triangle. So what you do is at each point on that triangle, you look at the curvature of that point, and you find a small area around that particular point and multiply the curvature times the area. So we subdivide this triangle into little pieces. We take curvature times area on each of these little pieces, add those up, and then let the little pieces become smaller and smaller. It's exactly the idea behind calculus. And we look at the limit of curvature times area as we sum these up over the entire triangle. And the value that we're approaching then becomes the total curvature of the triangle. And what Gauss was able to prove is that the sum of the angles in any triangle on any surface is 180 degrees plus the total curvature. In the case of a sphere of radius 1, the curvature never changes. That's always equal to 1. And so the sum of the angles of any triangle on a sphere is going to be 180 degrees plus the area of that triangle times the curvature, which is 1. In other words, the sum of the angles is always 180 degrees plus the area of the triangle. Now, Gauss was working with surfaces, and he clearly saw that surfaces could be non-Euclidean, but all of the surfaces that he looked at existed within Euclidean space. We're looking at the surface of a sphere, but it still rests inside normal three-dimensional Euclidean space. And so a question that was still out there was, could space itself be non-Euclidean? And there are two mathematicians in the early 19th century who really explored this, and I want to say a little bit about them. The first is János Bolyai, born in 1802. His father, Farkas Bolyai, had actually been a schoolmate of Gauss, and they maintained a close friendship throughout their lives. And the son, János, began working on this possibility that space itself might not be Euclidean, and began to explore what that would mean. And in 1832, he wrote up what he had done on this, and he included it in a mathematics book that his father was publishing. It was included as an appendix to that book. And the father, Farkas, sent a copy to Gauss, thinking that Gauss might be interested in this. And Gauss wrote back with an interesting quote. "If I commenced by saying that I am unable to praise this work, you would certainly be surprised for a moment. But I cannot say otherwise. To praise it would be to praise myself. Indeed, the whole contents of the work, the path taken by your son, the results to which he is led, coincide almost entirely with my meditations, which have occupied my mind partly for the last 30 or 35 years. So far as my own work is concerned, of which up till now I have put little on paper, my intention was not to let it be published during my lifetime." This was a real put down, and János actually would not publish anything more or very little more about his idea of non-Euclidean geometry. And it points to one of the real flaws of Gauss. Gauss was brilliant. Gauss's motto, though, was few but ripe. He didn't want to publish anything until he felt that he had perfected it and the time was right to put it out there. And while he understood a lot of what was going on with non-Euclidean geometry, and almost certainly his investigations of what happens on surfaces led him into exploring non-Euclidean geometry in general, he felt that the time was not right to publish. And because Gauss had already done all of these things, it really put a damper on what other people were interested in doing. And unfortunately, this did not just happen with geometry, it happened with many of the areas in which Gauss worked. It was not until after Gauss died and people were able to go through his manuscripts that they found that he had indeed discovered many of the things that other people discovered in the early 19th century, but often decades before the others had, and often in a much better and more complete form. And mathematics certainly would have benefited if Gauss had been more aggressive in getting his results out there and distributing what he knew, because he really was incredibly talented. Another person who worked on the question of non-Euclidean geometries was Nikolai Ivanovich Lobachevsky. Tom Lehrer has made this mathematician famous in his song about plagiarism, and there really is no connection between Lobachevsky and plagiarism. Lehrer simply liked the name, and it fit into the song very, very well. Lobachevsky was a Russian from Kazan, born in 1792. He also had a connection to Gauss. His teacher was Martin Bartels, who earlier had taught in Germany and had been Gauss's teacher of mathematics. And so when Lobachevsky came up with his ideas on non-Euclidean geometry, he also corresponded with Gauss. Gauss would eventually share these with Bolyai, and there was some thought, especially on the part of Bolyai, of perhaps pulling together what he and Lobachevsky had accomplished. But nothing ever really came of this, and it would not be until geometers much later in the 19th century that non-Euclidean geometry would finally be accepted and fully worked out. I want to close this lecture talking about something else that Gauss did that's going to be important for later work in later lectures, and that's his study of elliptic functions. If we go back to the trigonometric functions, the sine function, I talked about how Euler looked at the sine function and thought about this as a function of a variable which is the arc length of a circle of radius 1. And so we can easily define the sine for any number from 0 up to 2 pi. But there's no reason that we need to stop at 2 pi. Once we get beyond 2 pi, we just start repeating the values of the sine function. And we repeat the values up to 4 pi and then repeat them again up to 6 pi and so on. And we can also continue in the negative direction. And so we can build up the sine function as a periodic function, a function that keeps repeating. And the same is true of the cosine function. We can do the same thing with the exponential function in the imaginary direction, because recall that the exponential function e to the I times x is the cosine of x plus I times the sine of x. So once we get up to e to the I times 2 pi, we are back to 1. And so we can continue it beyond that. And if I think of the exponential function as I take imaginary values, as I travel up along the imaginary axis, taking the exponential function, that also is going to continually repeat its values. And one of the questions that then comes up once you start working with functions of complex numbers, and Gauss was the one who really pushed this idea of working with functions of complex numbers, you realize that you've got the trigonometric functions that repeat as you move in the real direction, and you've got the exponential function that repeats as you move in the imaginary direction. Can you get a doubly periodic function, a function that repeats both in the real direction and also in the imaginary direction? This is a kind of function that actually had been studied earlier by the French mathematician Adrien-Marie Legendre. Gauss became fascinated by these doubly periodic functions, what today we call elliptic functions, and he studied them in a great deal of detail. They're called elliptic functions for a strange reason. There is a connection with the ellipse, but it's rather obscure. One of the ways of building elliptic functions is out of certain definite integrals. So they come up in working with the integral calculus. And one of the definite integrals that gives rise to the elliptic functions is an integral that is related to the problem of finding the length of the arc of an ellipse. And so all of this type of definite integral got the name elliptic integrals because one of them was useful in finding an arc length on an ellipse. And then these elliptic integrals became one of the ways of finding these doubly periodic functions, and so the doubly periodic functions became known as elliptic functions. We will also see them sometimes referred to as abelian functions. It's Niels Henrik Abel, who I'll be talking about in the next lecture, who did a lot of important work on these functions. And so his name, especially in the 19th century, was often associated with them. Now, if we think about a doubly periodic function, we've got a function that's going to be repeating as we move horizontally and repeating as we move vertically. And so we can look at a fundamental domain for this function. We can look at a rectangular region, and as we translate that rectangular region, the function is taking on exactly the same values. We can translate it horizontally, we can translate it vertically. If I know all of the values of the function within this fundamental domain, I know the values of the function every place else in the complex plane. Now, if I think about this fundamental domain, this rectangle that determines the value of the function everywhere, and I think about what happens as I move off the right side of that fundamental domain, I'm really coming back in on the left side. I'm moving into the next copy of that fundamental domain, and the values that I'm taking on are exactly the same as the values that I would get coming in on the left side of that fundamental domain. So one of the ways of thinking of that fundamental domain is to wrap it around in a cylinder. So I take this rectangle and I simply wrap it around to reflect this fact that as I move off one side, I'm coming back around onto the opposite side. But the same kind of thing happens if I go off the top of this fundamental domain. I come back in on the bottom of the fundamental domain. So I don't just want to wrap the left and right side around into a cylinder. I want to take the top and the bottom and wrap them around. And what I'm going to get is a donut or a torus. And so these elliptic functions naturally live on a torus, on a donut. And this is the beginning of the realization that interesting functions, especially functions defined on the complex values, often really exist on some other kind of surface. And we begin here to get a connection between geometry and interesting sorts of surfaces and problems in analysis and calculus and the study of functions. For the next lecture, we're going to be turning to algebra and seeing how this idea of transformations will come to play a fundamental role in the development of algebra in the 19th century. In this lecture, we're going to look at the ways in which algebra underwent a fundamental change in the 19th century. Instead of being the kind of algebra that we learn in high school, working with these x's and these equations, algebra really becomes a tool for studying transformations. And the origins of this lie in the algebraic problem of finding the exact value of the root of a polynomial, the exact value of the place where a polynomial is equal to 0. And as I mentioned in an earlier lecture, once you know one of the roots of a polynomial, you can always use that in order to reduce the degree of the polynomial so that you now have a simpler problem to work with if you want to continue finding additional roots. We have the quadratic equation, which tells us how to find the root of a quadratic polynomial. And I've talked about how that particular solution to the root of a polynomial goes all the way back to the Babylonians. In the case of cubic polynomials, polynomials of degree 3, the method for finding the exact value of a root was found by Del Ferro and Tartaglia. And then for a fourth degree or a quartic polynomial, that was found by Ferrari, Cardano's student. The natural next question is, what about a polynomial of degree 5? is their way of finding and expressing the exact value of the root of a polynomial of degree 5. And here we need to be a little careful of exactly what we mean by the exact value. In the case of a quadratic polynomial, a cubic or a quartic polynomial, what we can find is an expression for the root that simply involves rational numbers together with addition, subtraction, multiplication, division, and the taking of radicals. So you might need to use square roots with a quadratic equation, cube roots with a cubic equation. We'll go ahead and allow ourselves fifth roots or sixth roots or seventh roots or whatever kind of radical we need. But what we'd like to be able to do is to take a polynomial and express its root precisely, exactly, not just an approximation, but the exact value in terms of the four arithmetic operations together with the radicals. And a lot of people studied this problem of trying to find the root of a fifth-degree polynomial. And in 1771, Lagrange did an intensive study of what was known up to that point. He looked at these formulas for the root of a quadratic polynomial, a cubic, or a fourth degree, and he tried to understand exactly what was going on there. And he published a very important paper in which he explained what was happening, why it was possible to find an exact value for those roots. He was hoping that in doing that, he would get the insight that he needed in order to find the formula for the root of a fifth-degree polynomial. But in fact, what this paper did was open the mathematical community to the suspicion that maybe there wouldn't be a way of finding the exact value for any fifth-degree polynomial. Now, there are fifth-degree polynomials for which you can find the exact value of the root. If I take the polynomial x to the fifth minus 2, there is an exact value for a root of that polynomial, namely the fifth root of 2 works. But if I've got an arbitrary fifth-degree polynomial, is it always possible to find a nice closed expression for the root of that polynomial? Some of the important work done on polynomials and their roots was done by Gauss. In 1798, while he was still a student, he showed how to construct a regular 17-gon using compass and straightedge. So this is a regular polygon with 17 sides that can be constructed just with compass and straightedge. And the key to this actually is finding the exact value of a certain polynomial of degree 8. The polynomial is more complicated than I want to say verbally, but I'll put it up on screen for you. And he actually found an explicit formula for a root of this polynomial. And again, it's an explicit formula using the four arithmetic operations together with square roots. In particular, the square root of 17 plays an important role. And once again, I'm not going to say that root verbally, but I'll put it up on screen and you can see the complexity of it. This is the kind of thing that people were looking for in general for polynomials, exact values of what a root would be. Gauss had another important breakthrough in this problem of finding roots. He proved in his doctoral thesis of 1799 that in fact every polynomial always has a root. Now you might have to look in the complex values. There is not necessarily a real number that's going to make that polynomial 0, but there always will be a complex number that makes that polynomial 0. This is known as the fundamental theorem of algebra, and in fact Gauss's thesis did have some gaps. There were some problems with his proof. Gauss would return to this problem later on in life, and I suspect maybe this might be behind Gauss's reluctance to publish things until he was absolutely certain that they were correct. The fact that one of the first things he had published wasn't quite correct as he put it out there. But Gauss would go back and publish other complete and correct proofs of the fundamental theorem of algebra in 1815, in 1816, and again in 1848. But Gauss never really made any progress on this fundamental question of the fifth-degree polynomial. Is it always possible to find a nice expression for the root? And the first person to actually prove that it cannot always be done was a Norwegian mathematician by the name of Niels Henrik Abel. And Abel will be the first of several mathematicians I'll be talking about in this lecture who died tragically young. Abel was born in 1802. He would die in 1829. He was born of a family of modest means, but his father died while he was still a teenager. And Abel, as the second oldest of the sons in this family, suddenly took on much of the responsibility of providing the money to keep the family going. And so he continued to study mathematics, but he really didn't have much in the way of financial support. His teacher in Norway realized the tremendous talent that this young man had. And when Abel came up with a proof that, in fact, there isn't a nice closed solution to every fifth-degree polynomial, his teacher went to the Norwegian government and managed to get them to agree to fund Abel's studies on the continent. Abel would go first to Berlin and then eventually to Paris. At this time, this now was the 1820s, Paris really was the center of mathematical work in Europe. But the amount of money that the Norwegian government could give him was not very much. Abel himself was sending much of that money back to his family to support the family, and so we know that he was living in very mean conditions. And while he was in Paris, he developed tuberculosis. He eventually would return to Norway, but he would never be cured of it, and in 1829 he died of the tuberculosis. The other mathematician I want to talk about is Évariste Galois. Galois was born in 1811. He would die in 1832. He died before his 21st birthday. And Galois was interested in the same problem that Abel was interested in, namely trying to see if there is a solution in closed form to polynomials of degree 5 or degree 6 or degree 7 or higher degree polynomials. And even more importantly, the broader question, as we've seen, sometimes these polynomials do have exact roots. Sometimes they don't. How do you decide when there is an exact root and when you don't have an exact root? And this is the question that Galois set himself to studying. Galois had a very tragic life. He tried to enter the École Polytechnique in 1828. He was only 16 years old at the time. He took the entrance examination. He failed it. The following year, at the age of 17, he again tried to enter the École Polytechnique. He again took the entrance examination, and once again he failed it. That same year of 1829, he got the fundamental insight into why it is that some polynomials have exact values for the roots and some polynomials don't. As we saw with Gauss, he was looking at a polynomial of degree 8 that did have an exact value for the root. But most polynomials of degree 8 do not have an exact value for the root. Well, Galois wrote up what he had done. It's a method of analyzing polynomials that later would come to be known as Galois theory. And he sent his first draft to Augustin Louis Cauchy. Cauchy is a French mathematician. I'll be talking much more about him in the next lecture. But in the 1820s, he was the greatest of the French mathematicians, and certainly one of the greatest of the mathematicians at the time, not of the stature of Gauss, who was in Germany at this time, but certainly comparable to Gauss. But Galois sent his work to Cauchy, and Cauchy was not particularly interested in this question at the time. Cauchy lost the manuscript, never made any commentary about it. And so nothing happened with this first draft of Galois. 1830, Galois still was unable to get into the École Polytechnique, but he did succeed in being admitted to the École Normale. This was probably the second most prestigious university in all of France at that time. It also had been established by the First French Republic in order to train teachers. And again, it was an institution that was really concentrating on science and mathematics. It was a very good place for him to be, but he was only there for a few months before he was expelled from university. 1830 was a tumultuous year in France. That's the year that Charles X was forced from the throne. And there was a lot of uncertainty about what kind of government would succeed him. Now, eventually, Louis-Philippe would come in as a constitutional monarch. But there were a lot of people during the year of 1830 who were trying to reestablish the French Republic. And Gallois was among those at the forefront of arguing for and demonstrating for a republic to be reestablished in France. And because of his writings, because of his activism, he was expelled from the university. Gallois went out and joined a National Guard unit, a particular unit that was very well known for its Republican sympathies. And this is Republican in the French sense of being a supporter of the French Republic. And at the same time, he wrote up another draft of his understanding of the roots of polynomials. And he sent this second draft to Joseph-Louis Fourier. Fourier, unknowns to Gallois, was on his deathbed at this time. Fourier was totally incapable of reading any kind of mathematical manuscript, and we don't know what happened to this second draft that was sent to Fourier, but it disappeared. Sophie Germain, who I mentioned just briefly in the last lecture, became aware of Gallois and the fact that he was doing this important work in algebra, and she became one of his supporters. She took an interest in Gallois. She encouraged him to rewrite his manuscript and send it out to several other mathematicians. And among the two mathematicians that he sent it to were Poisson and Lacroix. We don't know what happened to the copy that went to Lacroix. That also seems to have been lost. We don't know what Lacroix's response was, if any. The copy that went to Poisson, we do know that Poisson looked at it, couldn't make any sense of it whatsoever, and filed it away. Fortunately, he didn't lose it. Later on, that would be discovered, and it was the copy of the manuscript that went to Poisson that would be the basis for the fame that Gallois eventually would achieve, but not until long after he died. The National Guard unit that Gallois had joined was disbanded at the time that the monarchy was turned over to Louis-Philippe. But that did not stop Gallois from arguing and demonstrating for a republic in France. He was in the summer of 1831 at a gathering of former members of the National Guard unit in which he proposed a toast to the king, holding up in his hand not just the glass of wine, but also a knife. And that was seen as a threat against the life of the king. There was some controversy over exactly what Gallois had said as he made this toast, whether he was verbally threatening the king at the same time or not. But he was arrested at this point. When it came up for trial, because of the uncertainty of exactly what he said, he was released. But this did not stop his Republican sympathies, and later on that summer he was seen walking through the streets of Paris, completely armed, and also wearing his National Guard uniform, which had been banned because, again, of the Republican ties that it had, and he was rearrested. He remained in prison until March of 1832, when he contracted cholera. He was sent to the prison hospital, and there, while he was convalescing, he fell in love with the daughter of the doctor who was taking care of him. Unfortunately, she did not return that affection. In April, Gallois was released from prison, and very shortly after that, he found himself challenged to a duel. And unfortunately, we don't know the circumstances of the duel. It might have been connected with this daughter of the doctor. It might have been that her boyfriend had challenged him to the duel, or somehow he had done something that somebody was going to her defense. It might very well have been connected with his political activism that he was challenged to this particular duel. But he was challenged to the duel, and the night before the duel, he realized that he probably would not survive it. Gallois was only 20 years old at this time. There is a story often told that it was the night before the duel that he wrote up his work on finding roots of polynomials. In fact, we do know that that night he did write a letter to a friend of his in which he did talk about this work. But in fact, it was the manuscript that had been sent to Poisson almost a year earlier that really was the basis for what we know about Gallois' work on finding roots of polynomials. But in fact, Gallois did die in that duel. In the 1840s, there was a resurgence of interest in this question of finding the exact value of roots of polynomials. And in fact, 1842, Charles L'Hermite had published a proof of the impossibility of finding the root of a general quintic polynomial. And it would then be shortly after that that Joseph Louville would discover Poisson's manuscript, and in 1846 publish the work that Gallois had done, and also do an exposition of that work. Gallois, being a very young man, being a very inexperienced mathematician, had a lot of trouble expressing his ideas in ways that other mathematicians could appreciate and understand. And so it was Joseph Louville, who had been born in 1809, who took Gallois' ideas, not only published the manuscript, but also began to expound on it and show the rest of the mathematical community the depth of understanding that really lay behind this. Other mathematicians would begin to work on this theory of Galois, this understanding of when a polynomial has a root. You would get many more papers published during the 1840s and the 1850s. And finally, in the 1860s, actually in 1866, Serre, in the third edition of his fundamental work in algebra, his Cours d'Algèbre, in the third edition, he has a section on Galois theory in which he explains this. And at this point, 1866, Galois theory has found its way into the most popular textbook of the time, and it is now part of the standard mathematics curriculum. Now, the idea behind Galois' theory is really something closely related to transformations. If we think about a polynomial of degree 2, it has two roots. A polynomial of degree 3 is going to have 3 roots. These are roots that exist in the complex plane. So they might be real numbers, but you might have to use complex numbers. And when I say a polynomial of degree 3 has 3 roots, some of the roots might be at the same point in the plane. So you might have a double root or a triple root. But as long as you count the roots according to their multiplicity, you're going to get the same number of roots as you have the degree of the polynomial. And these roots are distributed around the plane. And the key to finding an exact expression for any one of these roots is based on the symmetry of the roots. If you take a polynomial such as x to the 5th minus 2, I said that there is a nice expression for a root of that polynomial, namely a 5th root of 2, but in fact all 5 of those roots can be found very easily just by looking in the complex plane at the circle of radius 5th root of 2. And the 5 roots of x to the 5th minus 2 are simply going to be equally spaced in the complex plane around that circle of radius 5th root of 2. In this particular case, for this particular polynomial, the roots have a lot of symmetry. If I rotate this by 72 degrees, rotate my entire plane by 72 degrees, that's a transformation that maps each of the roots to another one of the roots. And what Galois realized was that the trick to finding a nice expression for the roots of a polynomial is that the location of the roots fall into some kind of nice symmetric pattern, where there are nice transformations that take the roots into each other. If you've got these kinds of transformations operating on the roots, then there will be nice closed formulas for the roots. And if you don't have this kind of symmetry, you're not going to be able to find such a formula. Now, if we only have a few roots, we have to have this kind of symmetry. If I'm looking at a polynomial with real coefficients, and I look at a quadratic polynomial, either both of the roots are real, or if they are complex, one of them lies above the real axis, and the other one is the mirror image of that point across the real axis. So with a polynomial of degree 2, I always get this symmetry. And the same thing happens with polynomials of degree 3 and 4. There is always enough symmetry in these polynomials in order to guarantee that you're going to be able to find exact values for the roots. But as soon as you get to a polynomial of degree 5, you no longer have a guarantee that there is sufficient symmetry in order to be able to find exact values of the roots. And this would turn out to be the key, the symmetry of the roots. And largely because of this, in the 19th century, algebra changes from looking at algebraic expressions as we think of them in high school algebra, and really becoming the study of these transformations, looking at the kinds of transformations not just in two-dimensional space, but transformations in three-dimensional space or four-dimensional space or even infinite-dimensional space. Transformations in all kinds of strange spaces, such as the projective space that I talked about at the very end of lecture 16. So algebra becomes the study of transformations because it is the understanding of transformations that really lies behind being able to solve algebraic problems. And so we get what becomes really an entirely new field that today is called modern algebra or abstract algebra, that is really the study of transformations. I want to close this lecture by talking about another mathematician who died not as tragically young as Abel or Galois. He was in his 40s when he died, but I now consider somebody who dies in their 40s to have died tragically young. This is Jacob Jacobi. Jacobi was a German mathematician. He also was Jewish. And in the early 19th century, it was still very hard to be a Jewish mathematician. At many universities in Europe, you had to be Christian. Often you had to belong to a particular church in order to go to that university. In fact, at Cambridge and Oxford, you had to belong to the Church of England in order to be able to matriculate, let alone teach at Cambridge or Oxford. Jacobi was a little bit luckier. He was able to go to the University of Berlin, even though he was Jewish, and study there and obtain his doctorate there. But there was no question of being able to get an academic position at any of the major German universities being Jewish. And so he converted to Catholicism in order to be able to get an academic position. He would get his first position at the University of Königsberg, and then eventually he would move on in 1844 and get a position as in a chair of mathematics at the University of Berlin. He actually died in 1851 of smallpox. I want to say a little bit about his important work of 1829, essential work that he did on elliptic functions that I talked about at the end of my lecture on Gauss, these doubly periodic functions. And in 1829, Jacobi published a groundbreaking work called The New Fundamental Theory of Elliptic Functions. And he was interested in this fundamental domain that we have for elliptic functions. Now, the fundamental domain that I described in the last lecture was a rectangular region. There actually is no reason why it has to be rectangular. It might be that the fundamental region is actually a parallelogram. Now, you can always do a rotation of the variables so that one of the periods is moving in the real direction, and we might as well scale things so that that real period is equal to 1. So we can always take our elliptic function, rotate it, rescale it, so that one of the periods is obtained just by moving 1 unit to the right or 1 unit to the left. But then the second period actually can be any complex number. And we might as well assume that it's a complex number with a positive imaginary part. So I've got one period that is real and a second period that is a complex imaginary number, and that gives me a period parallelogram. Once you know the values of this elliptic function inside this parallelogram, you can just translate the parallelogram horizontally or vertically in order to find the values of the elliptic function anywhere. Now, the question that Jacobi faced was the following. If we're given an elliptic function, it is possible to figure out what the period is, what the shape of the parallelogram is. Jacobi asked, what if I know the shape of the parallelogram I want to get? Is it possible to construct an elliptic function that has that particular shape? So he went from the shape of the parallelogram, which is equivalent to finding the complex period. If I know the value of the complex period, can I use that to construct an elliptic function with this particular period? And the key to finding an elliptic function with this particular period is something that Jacobi called a theta function. And the theta function, which has as its input the complex period that you want, and as its output it produces various parameters that are needed to construct your elliptic function. This particular theta function has an interesting symmetry. It doesn't change if you replace the variable by one more than that variable. And it also essentially does not change if you replace the variable by the negative reciprocal of that variable. This is the modular transformation that I talked about in lecture 16. These theta functions of Jacobi that tell you how to construct an elliptic function with a given period. These theta functions are invariant under the transformations of the modular group, under these modular transformations. And this takes us back to that piece of the upper half plane, so this piece of the complex plane that lies above the real axis, where we had these the large fundamental domain that lies above 0, and then smaller and smaller copies that go off get smaller and smaller as they get closer to the real axis. This is exactly the picture that's represented in Escher's print, Circle Limit 3. What Escher is really looking at is the region that is invariant, the kind of transformation invariance of Jacobi's theta functions. These functions that are unchanged under the modular transformations are today known as modular functions. Theta functions are just one example of these modular functions. And the modular functions will come to play an important role, as so much else I've promised will, in the story of the proof of Fermat's last theorem. In our next lecture, we're going to look at some fundamental changes that happened to calculus in the early 19th century. In this lecture, we're going to look at developments in calculus in the early 19th century. Calculus, as I explained earlier, really builds on the work of Leibniz. And Leibniz explained calculus in terms of the language of infinitesimals, these itty-bitty pieces that are positive, they're larger than 0, and yet they are smaller than any actual positive number. And they're very difficult to work with and to really get a handle on, and especially because you don't just need infinitesimals, you need infinitesimals of infinitesimals, and infinitesimals of infinitesimals of infinitesimals. Now, throughout the 1700s, this really wasn't a problem. There were enough people who had a good intuitive sense of what was going on that they were able to work with this idea. And as I said, even modern physicists and engineers often work with this idea of infinitesimals, even though they can't say exactly what it is. But this always was a problematic point for mathematicians working with the calculus. And there's a very famous essay that was written by Bishop George Berkeley in 1734, in which he argues against the claim that science is rational. And he attacks the rationality of science by actually getting to the rationality of mathematics and of calculus itself, and pointing out that that sits on an irrational foundation, this idea of the infinitesimal. And I'd like to read a short piece from that essay. Now, to conceive a quantity or than any the least finite magnitude is, I confess, above my capacity. But to conceive a part of such infinitely small quantity that shall be still infinitely less than it, and consequently, though multiplied infinitely, shall never equal the minutest finite quantity, is, I suspect, an infinite difficulty to any man whatsoever. But how are we to make sense of calculus if we get rid of these infinitesimals? What do we really mean by the derivative, the dy over dx, if it isn't a ratio of infinitesimals? What do we really mean by the integral of a function multiplied by dx, if that dx isn't an infinitely narrow piece of the rectangle? Now, as I said, in the 1700s, mathematicians worked with this idea of infinitesimals without worrying about it too much, but it was a constant nagging problem. And in the early 1800s, there were three events that happened that really forced the mathematical community to go back and look at the very foundations of calculus in an entirely new light and try to get rid of these infinitesimals. I should say that it actually is possible to define infinitesimals precisely and rigorously and to build a calculus on them. In the early 1800s, though, the three problems that led mathematicians to go back and try to get rid of infinitesimals were, first of all, that you didn't have just a small group of scientists who were using calculus. You were starting to train a large cadre of engineers in order to do calculus. In particular, the École Polytechnique, which had been founded in 1794, was established precisely to train engineers. And part of the education of these engineers was to learn calculus. And if you wanted to be able to explain these ideas not to sophisticated scientists, but to young men who were going to go out and try to apply it, you had to be quite clear about what you were explaining to them. Another reason for needing to know exactly what we mean by calculus, by the foundations of the derivative and the integral, was the fact that people now in the early 1800s were beginning to think about how to apply calculus to these complex valued functions. They were now looking at functions not just of a real number, but functions of a complex number. When we've got a function that has a real number as its input and a real number as its output, we can graph a curve that represents that function, and it's easy to talk about the area underneath the curve or the slope of the curve. But when we take a function that goes from a complex value to a complex value, now the domain sits in two-dimensional space and the range sits in two-dimensional space. And in order to graph it, we actually need to have four-dimensional space, with the two-dimensional plane of the input orthogonal to both of the dimensions of the two-dimensional plane of the output. And you can't visualize a four-dimensional space very easily. So what do we mean by the integral in this case? What do we mean by the derivative in this case? But the third reason I think was the most important in the early 1800s, and that was the development of Fourier series. And before I explain Fourier series, I want to talk a little bit about Joseph Fourier, because he's a fascinating character. He was born in 1768. His original intention was to become a monk. He had entered the monastery when 1789 came and the French Revolution broke out. And a young man such as Joseph Fourier realized that life would be much more exciting if he went to Paris. And so he did, and he got himself attached to the scientific community there and learned a great deal of science and mathematics from the great people who were living in Paris at the time. In 1794, the École Normale was established. As I said in an earlier lecture, this was established in order to train future French teachers of science and mathematics. And Joseph Fourier got himself enrolled as one of the first students at the École Normale. In his first year there, it was realized that he knew much more than the other students. In fact, he knew enough that in the second year he was named a professor at the École Normale. And shortly after that, he managed to move up to a position teaching at the École Polytechnique. He eventually would become a science advisor to Napoleon. And when Napoleon invaded Egypt, Joseph Fourier was one of the scientists that he took along. Napoleon took scientists with him because he wanted people who could identify those antiquities in Egypt that should be taken back to France. And in fact, if you go to the Louvre today, you will see that some of the greatest of the Egyptian antiquities now are housed in the Louvre as a result of this Napoleonic expedition, and precisely as a result of the work of Fourier and others who selected what should be shipped back to France. Fourier actually was very interested in Egyptian archaeology. He wrote a very important 2-volume work in which he described the antiquities that he saw at that time in Egypt. And this really marks the beginning of modern Egyptian archaeology. And his work describing these antiquities is very important for Egyptian archaeologists today because he described many things that in fact no longer exist or have been severely damaged since Fourier was there. When Fourier came back to France, Napoleon appointed him as precept of the department of Isère. That's the department in the French Alps that has its capital at Grenoble. And Napoleon was setting up a French civil system of government. It was Fourier's job to actually set up the government, create a governmental structure from the ground up for the department of Isère. That certainly must have been an enormous task, and yet at the same time he was doing scientific work. And one of the great scientific questions of this time was trying to model the flow of heat. How do we come up with the equations and the mathematical models that show how heat will move through a body? And one of the things that Fourier realized was that the flow of heat was actually very closely related to the kind of modeling that Euler and D'Alembert had done in the 18th century, looking at vibrating strings. That in fact, the same kinds of differential equations that are used to model vibrating strings can be modified slightly in order to model what goes on as heat is flowing. Now, one of the keys to modeling a vibrating string is to use the trigonometric functions, the sine and the cosine. These are nice periodic functions. They set up a wave, which is what we expect to see when we're looking at a vibrating string. And what Fourier realized was that it's exactly these trigonometric functions, the sine and the cosine, that are essential in order to be able to model and describe the flow of heat. And so he considered a thin bar with a uniform supply of heat along one edge, and he was interested in how the heat then would spread through this bar. And what he needed to do was to describe this constant heat in terms of these oscillating functions, the sine and the cosine. What he actually needed to do in purely mathematical terminology is to take the constant function 1 and write it as a sum of cosine functions. And one of the incredible results that Fourier realized was that you really could do that. 1 is equal to 4 over pi times the sum of cosine functions. And that sum of cosine functions is the cosine of pi x over 2 minus a third of the cosine of 3 pi x over 2 plus a fifth of the cosine of 5 pi x over 2 minus a seventh of the cosine of 7 pi x over 2, and continue that arbitrarily far out. If we just take the first cosine function, we see the nice clear oscillation. But as we add more and more of these cosine functions together, we see that the oscillations become smaller and tighter, and the sum of the cosine functions begins to close in on the constant function 1. So that if I go out and take 100 of these terms, you now see just a very little wiggling around this constant function 1, and you actually then get, at the limits that you're looking at, this is only valid for values of x between -1 and +1, as you get out toward the edge, you get a little shoulder, a little hump, and then the whole function jumps down and it wiggles around the values -1. And then as you get out to -3 or +3, you get a little shoulder, what's called the Gibbs phenomenon, and then you jump back up and you oscillate around +1. So you get this function that's jumping between -1 and +1 with tighter and tighter oscillations around these constant values. And as you take more and more terms, the oscillations become progressively tighter until in the limit, as you take infinitely many of these terms, you actually get a function that's the constant function 1, and then it jumps down to -1 on either side, and then jumps back up to +1 on either side, and so on out to infinity. Now that's a very strange function, because that's a discontinuous function. That's a function that has jumps, and we were building it out of these nice cosine functions. And the mathematicians began to wonder, what's going on? Is this whole procedure legitimate? If you take a function, when can you represent it as this kind of sum of cosines, or very often what you need is not just a sum of cosines, but a sum of cosines and a sum of sines. This process of taking a function and decomposing it into a sum of sines and cosines is what would come to be known as Fourier analysis. And actually, one of the ways of thinking about this is in terms of music, is in terms of the vibrating string. What's really happening is that you're getting different frequencies on the different pieces, and each of the cosine functions is representing one of the harmonics, one of the overtones of the bass tone that is represented by the very first trigonometric function that you look at. What you're really doing is taking some arbitrary expression and breaking it down into a basic tone and the various overtones that are on top of it. Now, it seems very strange that this is what's really going on in heat, but as people would discover throughout the 19th century and the 20th century, almost every kind of physical phenomena actually can be broken down in this way using a Fourier analysis. Now, Fourier set out a method for discovering what these trigonometric functions should be. The problem was, do you really know that this infinite sum of trigonometric functions really approaches the function that you're interested in? This is the question of the convergence of the Fourier series. As you take more terms, does it get you progressively closer to your target function that you want to do the Fourier analysis on? And that would be a driving question not just of the early 1800s, that would be a driving question right through the middle of the 20th century. Augustin Louis Cauchy was undoubtedly the greatest of the French mathematicians of the 1820s. He was born in 1789. He taught at the École Polytechnique. And in 1821, he started writing his great book on calculus, what was called the Cours d'Analyse. His intention was that this would be a book that the students at the École Polytechnique would use to learn calculus. In fact, it was a total disaster as a textbook. The students at the École Polytechnique protested against it, and they actually stopped Cauchy's writing of it. It was used the first year, and then it was never used again. But the Cours d'Analyse was the basis for Cauchy's work on refounding the foundations of the calculus. And to see what's going on, let's consider a problem of the differential calculus, finding the slope of the function x cubed at x equals 1. And what we can do, and this is certainly the way Leibniz or Newton thought of this initially, is you approximate the slope by looking at the difference in the function divided by the difference in the variable. So if my function is x cubed, I'm looking, say, I look at it at 1 and I look at it at 1.1. So the change in the function is 1.1 cubed minus 1 cubed divided by the change in x, which is 1.1 minus 1, or that turns out to be about 3.31. As I take smaller and smaller changes in x, what is happening is that this ratio gets closer and closer to 3. What Leibniz argued is that if I take an infinitesimal change in x, I now get a ratio that is exactly equal to 3. And this is what Cauchy would not allow. What Cauchy actually did was to go right back to the way Eudoxus and Euclid and Archimedes argued about numbers and these kinds of limiting processes that they were doing in the integral calculus, which was to look at that ratio and say the ratio cannot be larger than 3 because I can always take a change in x that is small enough so that my ratio, whatever number I take bigger than 3, my ratio is less than that. And I can also force this ratio to be larger than any number that is less than 3, just by taking that change in x to be arbitrarily small. So given any number that's larger than 3, I can force the ratio to be less than that. Given any number that's less than 3, I can force the ratio to be larger than that. The ratio must be 3. And this is the basis for Cauchy's view of the calculus, really based on the ancient Greek idea of how do you compare two irrational numbers. And that would be our modern basis for calculus. Today we couch it in the language of epsilons and deltas, and actually Cauchy did use these epsilons and deltas. But the idea that sits behind them is this idea that it can't be a smaller number, it can't be a larger number, it must be exactly the 3. Now, as Cauchy was trying to explain the foundations of calculus, he had a lot of trouble doing this, and he came up with things that weren't quite right. And a number of the young mathematicians in Paris at the time, of whom Niels Henrik Abel was one, realized this. And there's a marvelous quote from Abel. In 1826, he wrote back to his teacher in Norway, and he wrote, "Cauchy is crazy, and there is no way of getting along with him, even though right now he is the only one who knows how mathematics should be done. What he is doing is excellent, but very confusing." An example of this confusion comes from the Cours d'Analyse of 1821, when Cauchy actually proves that every sum of continuous functions is continuous. And Abel, in one of his papers that he published in 1826, wrote, "It appears that this theorem suffers exceptions." And of course it does. The Fourier series is a prime example of an exception. This is an infinite sum of continuous functions, but as I said, it gives us this discontinuous function, which is jumping between +1 and -1. A number of people worked on this question of the Fourier analysis, and when does it really work? When does this sum of sines and cosines actually converge to the original function? Very important work was done by another young mathematician of the 1820s, Gustave Lejeune Dirichlet. He was born in 1805, would die in 1859, and we're actually going to see him coming up again in a later lecture. In 1829, he showed that Fourier analysis is valid as long as you've got any monotonic function. A monotonic function is one that is always increasing or always decreasing. And you can extend that idea so as long as the function changes direction a finite number of times, the Fourier analysis is going to be valid. But there are functions that even within a finite interval oscillate infinitely often. And Dirichlet's analysis simply doesn't work for those functions. Throughout the 19th century, a lot of people would be looking at this question of convergence of functions, convergence of the Fourier series for functions that oscillate infinitely often. And the final theorem would actually not be done until 1966. It was a Swedish mathematician, Lennart Carlsson, born in 1928. He would then go on and teach at UCLA for much of his career. And in 1966, he was able to prove that if the square of the function can be integrated, then not only does the Fourier series exist, but it actually converges to the original function. Carlsson did a lot of important work in analysis throughout his career. He is still alive at this moment. And in the year 2006, he was awarded the Abel Prize. The Abel Prize is a prize awarded by the Norwegian government, quite appropriately because it is named for Abel. It is the exact equivalent of a Nobel Prize. It's a fairly recent prize. It was only established in the year 2002, but it goes to mathematicians who have done important work in their careers. And very appropriate that Lennart Carlsson should get this award named for Niels Henrik Abel. I want to finish this lecture up by talking about another very important mathematician who really understood what was going on in calculus and really set the stage for a lot of what other people would do with calculus in the 19th and then on into the 20th century. And that's Carl Weierstrass, born in 1815. He would die in 1897. He was someone who had started out in university as a law student. He was not particularly interested in studying law. We know that he got involved in all kinds of pranks and duels and basically wasted his time at university and eventually was expelled. But what he really loved was mathematics. And so he went back and he decided to become a high school teacher, actually in the German system, a gymnasium teacher. And so he went to the Münster Academy, and he had the very great luck that one of the mathematicians who was teaching at the Münster Academy at that time was Guderman. And Guderman was one of the few mathematicians who had really studied elliptic functions in detail. And Guderman wanted to be able to teach a class on elliptic functions, but most of the prospective gymnasium teachers were not at all interested in learning about elliptic functions. But Weierstrass was. Guderman taught a class to one student who was Weierstrass. And Weierstrass was fascinated by what was going on with these elliptic functions, or as he usually referred to them, abelian functions. Weierstrass would go on to become a high school teacher. He taught a wide range of subjects. He taught 30 hours a week. In addition to the mathematics, he taught German language, botany, geography, history, penmanship. He even taught gymnastics. But he was also working on these elliptic or abelian functions that Abel had studied. And in 1854, he published a groundbreaking paper called On the Theory of Abelian Functions, in which he laid out a new and comprehensive way of looking at abelian functions. And it was a paper that really brought him to prominence within the mathematical community. The following year, he was awarded an honorary doctorate at the University of Königsberg. Shortly after that, he obtained an adjunct position at the University of Berlin, and he would go on to hold a chair of mathematics at the University of Berlin, taking over that chair in 1864. Over the period from the 1850s into the early 70s, while he was at the University of Berlin, he would lecture on analysis, on the calculus. And he's the one who really explained the fundamental ideas, who clarified many of the things that Cauchy and Abel and Dirichlet had wrestled with in the 1820s and the 1830s. Weierstrass really saw clearly through to what was going on. Weierstrass realized the importance of understanding the real number line and the complexity of the real number line, and he encouraged his students to think about it. One of his students was Georg Cantor, who would go on to develop set theory and explore all of the complexities of the real number line, and he was motivated by Weierstrass's lectures, in which Weierstrass had explained the importance of understanding real numbers. Many of the results that Weierstrass came up with, he did not publish. He simply expounded them in his lectures. His students then would go on to build on those results and state them and get credit for them. Although much later, after Weierstrass died, many of his lectures were collected and published, and it was discovered that his students were taking ideas that had originally come from Weierstrass. And in fact, Weierstrass was an outstanding teacher. He had 41 doctoral students. He really trained the next generation of German mathematicians. And if you take a look at his mathematical genealogy, all of the people who can trace their mathematical doctorates back through their advisor to their advisor's advisor to their advisor's advisor's advisor, there are a total of 12,508 mathematicians who can trace this back to Weierstrass. Some of the other famous mathematicians who studied with Weierstrass are Killing, Frobenius, and Schwarz. Schwarz in particular would be someone who would lay the foundations for Einstein's work in geometry and general relativity. I want to close by mentioning one of his students and bringing up another woman mathematician of the 19th century, and that's Sofia Kovalevskaya. She was usually known as Sonia Kovalevskaya. Born in 1850, she would die in 1891. I talked about the difficulty in the early 19th century of being Jewish and trying to pursue a career in mathematics. It was even more difficult for women, even by the end of the 19th century. Sonia Kovalevskaya was able to go to university as an undergraduate, but she could not find a university that would accept her for graduate work. But what she did do was to go to the University of Berlin, where Weierstrass was teaching, and arrange to take lessons with and sit in on the classes that Weierstrass was doing. And Weierstrass became her advisor in an unofficial capacity. And in 1874, when she did her doctoral thesis on elliptic or abelian functions, it was Weierstrass who tried to get her an official doctorate. It turned out to be impossible to do it at the University of Berlin, but he had good contacts at the University of Göttingen, and he managed to convince the people at Göttingen to give a doctorate to Sonia Kovalevskaya. And Sonia Kovalevskaya would become the first woman to hold the position of chair of mathematics in a European university. This is 1889, when she would be appointed by the University of Stockholm. Unfortunately, 2 years after she joined the faculty at the University of Stockholm, she contracted the flu, which was complicated by pneumonia, and she died. In the next lecture, we are going to be looking at Gauss's most famous student, someone who also studied with Weierstrass. Although he did his undergraduate work with Weierstrass, his graduate work would be done with Gauss. And that is Bernhard Riemann, someone who had no students, no doctoral students, but who nevertheless had a profound influence on the development of mathematics. He fundamentally changed the way we think about questions in complex analysis, the calculus of complex numbers, how we think about geometry, and how we think about number theory. In this lecture, we're going to look at the life and work of Bernhard Riemann, one of the great German mathematicians of the middle of the 19th century. In fact, between Riemann and Weierstrass, you certainly have the two mathematicians who really dominate German mathematics and most of mathematics in the late 1850s and well into the 1860s. Riemann was born in 1826 in Hanover in Germany. He went to the University of Göttingen initially with the intention of studying theology, and he went there simply because that was the appropriate university at which to learn theology for his particular denomination. However, he got there and discovered the mathematics teacher Gauss. Gauss quickly realized that in Riemann he had an exceptional student, and Gauss also realized that Göttingen was not the right place for Riemann. Gauss was really the only mathematics teacher there, and Riemann was someone who needed exposure to the entire breadth of mathematics. And so at Gauss's suggestion, Riemann switched to the University of Berlin, which really was the exciting place where most of German mathematics was happening at this time. And Riemann did his undergraduate work at Berlin, but he then returned to Göttingen to do his doctoral work with Gauss. Riemann would earn his doctorate in 1851, and then he stayed on at Göttingen in order to do his Habilitation. Now, this is something that happens in the German system beyond getting a doctorate. In order to prepare to be a research mathematician and to get a position as a chair of mathematics in a German university, you have to build up a body of work that shows that you really are capable of doing original research in mathematics. And this then leads to a second thesis, a more advanced thesis that is called the Habilitation, and involves an oral defense. And both the Habilitation and the oral defense are part of Riemann's story, and I will come back to them later. At the same time that Riemann was a graduate student in Göttingen, there was another graduate student there also studying mathematics with Gauss. That was Richard Dedekind. Dedekind would be one of the people who really explored the nature of the real number line. He's the person responsible for what is called the Dedekind cut, which again goes back to the ideas of Eudoxus and Euclid and Archimedes in trying to explain what we mean by an irrational number by saying it's not one of the numbers that's larger and it's not one of the numbers that is smaller. We're also going to see Richard Dedekind coming back into the story as we talk about Fermat's last theorem. In 1855, Gauss died. It was Gustav Lejeune Dirichlet who took over his position as chair of mathematics at the University of Göttingen, but Dirichlet did not live much beyond that. In 1859, Dirichlet died, and Riemann was appointed to the chair of mathematics at this university. This also was the year in which Riemann published his very important paper on the prime number theorem, and I'm going to say much more about that later in this lecture. It seemed that Riemann was set for a very auspicious career, but just a few years after taking over the chair of mathematics at Göttingen in 1862, Riemann came down with tuberculosis. He traveled through Italy for several years after that, hoping that the warmer climate would improve his health, and Dedekind often accompanied him on these trips through Italy. And Riemann did work with many of the Italian mathematicians at the time, and in fact he had a lot of influence on Vito Volterra, who was then a young graduate student in Italy, and Volterra would go on to build on many of Riemann's ideas. But in fact, the tuberculosis did not get better, and in 1866, Riemann died. At the time that he died, he had left much of his most important work unpublished. It was Richard Dedekind who discovered his manuscripts, went through them, prepared them for publication, and saw that they got published. And they had an enormous impact on the mathematical community. I want to talk first about his doctoral dissertation, in which he was looking at the problem of calculus applied to complex numbers, so complex analysis. And we're looking at functions that go from one complex variable to another complex variable. And I've talked about some of these functions, taking the reciprocal, for example. So z goes to 1 over z, and I've talked about how that moves points around in the complex plane. Another example of a complex function is the simple exponential function. So it takes z to e to the z. And what that does is it takes the real number line, and the real number line, if I take e to a real number, I get a positive real number. So it takes the real number line and it maps it to a ray that starts at the origin but does not include the origin, and then travels infinitely far off to the right. If instead of the real number line, I move up by pi over 4 times I, and consider the horizontal line whose imaginary part is pi over 4 times I, and I now take e raised to a point on this line is now going to become a ray that goes out from the origin at an angle of 45 degrees. If I move up again to the horizontal line whose imaginary part is pi over 2 times I, that now gets mapped to a ray that goes vertically upward. And so as I take these horizontal lines that go upward, so horizontal lines become these rays going out from the origin. So if I take horizontal lines at pi over 4, pi over 2, 3 pi over 4, and so on, I'm going to get rays going out from the origin at 45-degree angles from each other. If I now consider the vertical lines, if I take the imaginary axis and I look at what happens to that under this mapping that takes z to e to the z, e to a purely imaginary number is going to be a point on the unit circle. So this transformation takes the vertical line and turns it into a point on the unit circle. And as I take other vertical lines, if say I take the vertical line that has real part equal to 1, that's going to map into a circle with radius equal to e to the first power. And the vertical line with real part equal to 2 is going to map to the circle with radius equal to e squared. And if I then take, say, the vertical line with real part equal to -1, that's going to turn into a circle with radius equal to e to the -1 power. So it's a radius less than 1. So as I take the horizontal lines, get rays going out from the origin. As I take the vertical lines, I get concentric circles with their center at the origin. And one of the interesting things that happens if you think about the grid that is formed by my horizontal and vertical lines, that turns into a kind of polar grid where I've got rays going out from the origin and I've got circles. If I look at my original domain with my horizontal and vertical lines, these lines meet at right angles. If I look at the image, which has these rays going out from the origin together with the circles, each of these rays cuts the circle at a right angle. The ray is perpendicular to the tangent of the circle at that point. Now, it turns out this is not just true of the horizontal and vertical lines. They meet at right angles, and so their images meet at right angles. This actually is true of any pair of curves. If I take two curves in the domain, and I consider the angle at which they meet, that is to say, I take the tangent lines at the point they meet, and I look at the angle between those tangent lines, and I do the exponential function, and I look at the images of those curves. They're going to be two different curves that still meet at a single point. I can find the angle between those two curves, and the angle between the curves in the range is going to be exactly the same as the angle between the curves in the domain. And so this is a mapping that preserves angles, and there is a name for it. It is called a conformal mapping. Conformal just means angle preserving. And in fact, it's not just the exponential function. Most of the nice functions that you might think of polynomial functions in a complex variable, trigonometric functions in a complex variable, rational functions, a function that's a ratio of two polynomials in a complex variable. These are all conformal mappings, all conformal functions. They preserve angles. Now, what Riemann did in his thesis was not just to study this problem of preservation of angles. He actually turned it around. And he asked, if I've got some region over here in my domain, and I've got another region over here in my range, and I want to come up with a complex valued function that goes from this region to this region over here, can I always find a conformal mapping that does it? And in fact, what he proved in his thesis is that the answer is yes. You always can do it. There's some qualifications. The boundary can't be too tricky. But if you've got a reasonably nice boundary over in the domain and a reasonably nice boundary over in the range, then you can always find a conformal mapping that goes from one to the other, an angle-preserving mapping from one to the other. And this then would be the subject of Riemann's thesis. I want to move on now to the prime number theorem, the result that Riemann published in 1859. And it deals with the problem of counting the number of primes that are below a given number. So the primes start with 2, 3, 5, 7, 11. And given a number like 20, one can ask how many primes are below 20, how many primes are below 100, how many primes are below 100,000. And we can actually graph this prime counting function. It's going to be a step function. Every time we hit a new prime, we increase the value by 1. And a number of mathematicians had explored this question of how fast does that function grow? Is there a good way of estimating the number of primes that are less than x? And it actually was the young Gauss in 1792, he was only 15 years old at the time, who realized that the right function for modeling the growth of the number of primes is something called the logarithmic integral. Now, one of the functions that can be used is simply to take x, that number below which we want to count the primes, x, and divide it by the natural logarithm of x. So the number of primes less than x is about x divided by the natural logarithm of x. But a more accurate function is this logarithmic integral, which is obtained by taking the reciprocal of the natural logarithm, so 1 divided by the natural logarithm. So this is a function that's going to approach infinity at 1, and then it's going to drop off and gradually get closer to 0. The logarithmic function approaches infinity as the variable gets larger, so the reciprocal of the logarithmic function is going to approach 0. But the logarithmic function grows very slowly, and so its reciprocal approaches 0 very slowly. And what you can do is look at the area underneath this reciprocal of the logarithmic function from 2 up to some variable x. And the area underneath the reciprocal from 2 to x is called the logarithmic integral of x. And that turns out to give you a very accurate approximation to this prime counting function. If you look at the prime counting function, x over log x, and the logarithmic integral of x for values of x up to 100, you'll see that the prime counting function, this step function, lies between these two curves. And in fact, up to 100, you can see that the logarithmic integral is above the step function, and x divided by log x is below the step function. And it looks like the actual prime counting function occurs roughly halfway between the two. Well, in fact, that's what it looks like up to 100, but if you go a good deal larger than that, say if you go up to 100,000, so you're looking at the prime counting function all the way up to 100,000, now our horizontal increments are small enough and our vertical increments are small enough that it's hard to see the steps. This prime counting function now begins to look like a smooth function. And it's quite clear as we go up to 100,000 that it's much, much closer to the logarithmic integral than it is to x divided by the natural logarithm of x. But one of the things that you observe in comparing the prime counting function with the logarithmic integral is that the prime counting function always seems to be below the logarithmic integral. And a natural question to ask is it always less than the value of the logarithmic integral? And there's an important result that was done in the very early 20th century by Littlewood, and we're going to run into Littlewood again when we talk about Srinivasa Ramanujan. But Littlewood, who was at Cambridge at that time, was able to prove that, in fact, the prime counting function does not stay below the logarithmic integral. Eventually, it will become larger than the logarithmic integral, and then it will go back below the logarithmic integral, and then back above, and then again below. And as you go out toward infinity, the prime counting function and the logarithmic integral are going to interchange places infinitely often. But a question for mathematicians in the 20th century was, where is the first place where the prime counting function is larger than the logarithmic integral? They did calculations out to millions and billions, and it was clear that the prime counting function was staying below the logarithmic integral. Where is the first place where they switch and the prime counting function is larger? This first place became known as the Skews number. And for a long time, the best that we knew was that it was absolutely humongous. Well, in fact, it is very large. Just in the past few years, people have been able to pin it down a little bit more closely. The first place where the prime counting function is larger than the logarithmic integral is at a number that is about 10 to the 316th power. In other words, it's an integer of 317 digits. It's not known exactly, but it's known that this 317-digit number starts with 139 and then continues on with another 314 digits, not all of which are yet known. This is work actually that was done by the mathematician de Michel in 2005. Now, as I said, we know that the prime counting function can be well approximated by this logarithmic integral, and in order to do that, what Riemann did was to look at the zeta function. This is the sum of the reciprocals of the integers raised to a power that is an arbitrary complex number. So we're looking at the sum 1 over 1 to the z plus 1 over 2 to the z plus 1 over 3 to the z, and continue this infinitely far out. If the real part of z is larger than 1, then this infinite summation converges. But one of the things that Riemann realized was that you could actually take this function, and the fact that it's defined when the real part of z is larger than 1 implies that it must be defined for all complex values except exactly at z equals 1, where as you approach z equals 1, this number is going to approach, this function is going to approach infinity. But it can be defined over the entire plane. And something else that Riemann realized was that understanding the nature of this function would enable you to prove that the number of primes less than or equal to x is well approximated by the logarithmic integral of x. And in fact, what he showed was that all you need to do in order to prove that logarithmic integral is a good approximation is to show that this zeta function does not take on the value 0 any place else on the vertical line with real part equal to 1. It would take a long time before this actually would be proven. In the 1890s, it would be two French mathematicians, Hadamard and de la Vallée-Poussin, who would finally put together this proof of the prime number theorem. But they exactly followed the outline that Riemann laid out for them in what it would take in order to prove it. Riemann went beyond that. He also looked at the size of the error term. How close is this approximation? How close does the prime counting function stay to the logarithmic integral? And he realized that the key to that was understanding the location of the other places where the zeta function could equal 0. Now, he showed that the zeta function has a kind of symmetry about the vertical line with real part equal to 1/2. so that if I know the values on one side of that line, I can take the mirror image of those values, and I know the value of the zeta function on the other side. Well, since we know the values when the real part is larger than 1, simply using the series expansion, we can use that to find very good approximations of the values. In fact, we can really pin down the values when the real part of z is less than 0. The trick comes for complex numbers where the real part lies between 0 and 1. This is known as the critical strip. And what Riemann showed is that if all of the zeros of the zeta function that lie within this critical strip actually lie along the single vertical line with real part equal to 1/2, then the error term in approximating prime counting by log integral, that error term is about the square root of x, much, much smaller than the size of the logarithmic integral. This would become known as the Riemann hypothesis, that all of the zeros of the zeta function that lie inside the critical strip, all of the places where the zeta function is 0, actually lie on this single vertical line. Now, it's known that there are infinitely many places where the zeta function is 0 inside this critical strip. And a lot of people have worked on this problem, the Riemann hypothesis. It is probably the most important open problem in all of mathematics today, just because so much of what we study depends on having a good idea of the gaps between the primes and exactly how large a given prime is going to be. And so pinning down this error term turns out to be very important. A lot of work has been done on actually showing that many of these zeros, hopefully most of these zeros, lie on this critical line. And in 2004, Gordon, using a method developed by Andrew Odlyzko and Schoenhagen, actually was able to check the first 2.4 trillion zeros of the Riemann zeta function that lie within the critical strip and show that all of them lie precisely on this single vertical line. Now, that may seem like pretty convincing evidence, but remember that there are infinitely many of these zeros. So checking the first 2.4 trillion really tells you nothing about the next 2.4 trillion or the next 2.4 trillion after those. I want to look now at some of the work that Riemann did with geometry. This was part of his habilitation. So I said that the habilitation that he did in 1854 involved both a written part and also an oral part. His written part was on Fourier series. It was very important work on trigonometric series. And normally your oral report, your presentation, would be based on what you wrote. But usually the candidate for the habilitation had to submit several different topics that he was willing to talk on. And Riemann had said that he was also willing to talk about geometry. Well, Gauss, of course, was interested in geometry. He had done all of this work on differential geometry, was interested in non-Euclidean geometry. He wanted to know what Riemann had to say about geometry, and so that became the topic of Riemann's habilitation talk. And what Riemann did was to take what Gauss had done and invert it, turn it around in a very clever way. I've talked about Gauss and differential geometry, where the idea was that you're given a surface and you want to define distances and areas, and you use the differential calculus in order to find the distances on a given surface. What Riemann did was to say, rather than start with the surface and ask how to define these differentials, how to define distances, let's take an arbitrary definition for the distance and look at the kind of geometry that implies. So start with the definition of distance, which can be defined very generally in terms of notions of differentials and calculus, and see what geometry that implies. This would be the root of what today we refer to as Riemannian geometry, building geometries up from our understanding of how distances are connected. And this would be the key insight that would enable Einstein to do his work in general relativity. Because in general relativity, what Einstein actually did was to come up with a particular definition of distance that was consistent with his understanding of the physical world. And what Einstein then did was to go back to Riemannian geometry and the way other geometers had developed it through the remainder of the 19th and into the early 20th centuries, and see how to start with this definition of distance and use that to see what it implies about the nature of the geometric space in which we are actually working. Another one of the people to make important contributions to geometry at this point is Arthur Cayley, born in 1821. He would take a look at this problem of projective geometry. We've seen how you can project from a sphere onto the plane. Projective geometry generally considers taking some kind of a space with the geometry on that space and then projecting it into another space and seeing what kind of geometry you get. And Cayley was able to show that all of these projective geometries can actually be explained in terms of differential geometries. It's the differential that is key. Felix Klein, born in 1849, would really advance our understanding of geometry in very fundamental ways. One of the interesting things that Klein came up with is something called a Klein bottle. This is really an extension of the idea of a Möbius strip. If you'll recall, a Möbius strip is something two-dimensional. You can give it a half twist through the third dimension and get something that only has one side. What a Klein bottle is a three-dimensional bottle that is given a twist through the fourth dimension so that there is no distinction between the inside and the outside of the Klein bottle. So what we have is the neck of the Klein bottle comes up and comes back inside, and what had been the inside of the Klein bottle now becomes the outside. Now, of course, I can't actually hold a Klein bottle for you in four-dimensional space. This is a three-dimensional model, and so you see that handle passing back through the side. A true Klein bottle doesn't use that. That's really a cheat, so that we can create a Klein bottle in three-dimensional space. A real Klein bottle really only lives in four-dimensional space. Klein took on a program of trying to understand geometries not just in terms of differentials, but also in terms of the transformations that leave the geometries unchanged, what are called the invariants. And Klein set out a problem while he was at the University of Erlangen to try to characterize all geometries and to show how all possible geometries could be explained in terms of these invariants. That became known as Klein's Erlangen program. He would work on it, other mathematicians would work on it, and eventually come to a way of thinking of all geometry in terms of transformations. Now, I've said that algebra is really the study of transformations. And so what begins to happen in the late 19th and early 20th centuries is that the geometry and algebra begin to merge. Algebra is the study of transformations. Geometries are understood by understanding what transformations act on them, what transformations leave a given geometry unchanged. And so we begin to get an area of mathematics that is known as algebraic geometry, which may sound like it should be analytic geometry, high school algebra, and high school geometry, but it really is extremely sophisticated mathematics in which you look at the algebra that sits behind the kind of geometric spaces that you want to study. Klein would go on to become chair of mathematics at Göttingen, and while he was there, he decided to turn Göttingen into the premier center of mathematics for the entire world. And in fact, he was successful in that in the early decades of the 20th century, first under Klein and then under David Hilbert. Göttingen would be the place where you had to go if you wanted to study with the greatest mathematicians, if you wanted to find out what was really happening in mathematics. Unfortunately, in the late 20s and into the 1930s, with the rise of Hitler's Germany, the Jewish mathematicians at Göttingen were forced to leave the university. Many of the other mathematicians at that time realized that it would be wiser to leave and go to, many of them to the United States, some of them to England or to other countries. And in fact, that mathematical community at Göttingen was destroyed by the rise of Hitler's Germany. But during the time that it was at its peak, during the 1890s, and right up until about 1930, it was the very center of mathematical activity in the world. David Hilbert would make a name for himself in 1900 when he addressed the International Congress of Mathematicians and laid out his 23 problems. These are problems that would motivate much of the work of mathematics in the 20th century. In this lecture, I'm going to talk about two of my favorite mathematicians, James Joseph Sylvester and Srinivasa Ramanujan. They are people whose mathematical work laid much of the foundation for the work that I have done in mathematics. In particular, they were both interested in the problem of counting partitions, the number of ways of taking an integer like 5 and writing it as a sum of positive integers. So 5 can be written as just 5, or 4 plus 1, or 3 plus 2, or 3 plus 1 plus 1, or 2 2s and a 1, or a 2 and 3 1s, or 5 1s. There are 7 different ways of writing 5 as a sum of positive integers. And that may seem like a rather uninteresting problem, but it turns out to have some very deep repercussions. And there are extensions of this idea that play out in modern physics today. Not only did Sylvester and Ramanujan do work that I find personally relevant, but also they led fascinating lives. James Joseph Sylvester was born in 1814. He was born as James Joseph. Joseph originally was his family name, and when he became an adult, he decided to change his last name to Sylvester. James Joseph Sylvester was Jewish, and just like Jacob Jacobi, he ran into a lot of difficulties both getting into university and then getting a university position because he was Jewish. He was from England. He went to Cambridge, but he was never allowed to officially matriculate at Cambridge. At that time, you had to belong to the Church of England in order to be officially enrolled as a student, either at Cambridge or at Oxford. So not only could Jews not enroll at Cambridge or Oxford, if you were Roman Catholic, you could not enroll there. If you were Unitarian, you could not enroll there. You had to be Church of England. What Sylvester did was to go ahead and attend classes at Cambridge, and he even took the great examination that followed a normal Cambridge undergraduate career in mathematics, the Tripos exam, which was a very extensive examination, took place over several days and was designed to identify the very best mathematicians who were coming out of Cambridge. Sylvester took that examination, but he never actually got a degree from Cambridge. And after taking the examination, even though he came in second, he was not able to turn that into an academic position at either Cambridge or Oxford. That simply was out of the question since he was Jewish. He did wind up going to University College in London, where he got a position teaching natural philosophy or physics, and he would eventually go to Trinity College in Dublin. Trinity College in Dublin is also a university that's affiliated with the Church of England, the Anglican Church, but because it was in Ireland, it was willing to open its doors to people who were not members of the Church of England. And so Sylvester did go there, and he wound up getting a master's degree from Trinity College, Dublin. Back in London, he was not entirely happy being at University College. It was a fine place. It had actually been started a few years earlier as a university where people who did not belong to the Church of England could go and get a college education. But Sylvester really wanted to teach mathematics, and so he began to look for a place that would accept him as a professor of mathematics. And not finding such a place in England, he looked to the United States. And he got himself a job teaching at the University of Virginia. This is 1841. At that time, the University of Virginia was really out in the wilderness, out in western Virginia. And so it was very far from the kind of civilization that Sylvester was used to. Also, the University of Virginia had been founded just a few years earlier. The University of Virginia was founded in 1819. And it was really a place that was established for the sons of the plantation owners. This is a place where they would go, and these were young men of privilege. And these were young men who were very conscious of their social position and the fact that the faculty at the University of Virginia did not share that particular social position. And so we know from many accounts of the time, and also from what Sylvester himself talked about his very short stay at the University of Virginia, that the students there treated the faculty despicably. It was very difficult to be a faculty member at the University of Virginia in those days. Sylvester lasted about 3 months and then finally got so disgusted with the way the University of Virginia was being run that he left. He stayed in the United States for about another year and a half trying to find another academic position. He knew some of the mathematicians at both Columbia University and at Harvard University, and he spent time in Boston and New York trying to arrange for a teaching position at one of those universities. He was unsuccessful, and so eventually he went back to England, and he decided to get a job as an actuary working for one of the new life insurance companies that were just then beginning to come into existence. And so he would work as an actuary, and then eventually he realized that he would be even more useful for his employers if he got a law degree. And so he studied law and passed the bar. But he was really interested in mathematics, and what he wanted to do was to find a position teaching mathematics. And finally, in 1855, this became possible. A teaching position opened up at the new Royal Military Academy in Woolwich. Sylvester went there, and Sylvester now was engaged in conflict with the administration at the Royal Military Academy because he wanted to do mathematics. And he found himself with a very full teaching schedule that left him very little time to do the kind of research mathematics that he wanted to do. And he actually became one of the important people in the 19th century who would argue for the right of faculty at universities to have time to do research. In many respects, this position has been exactly reversed now. At the major universities, it is expected that the faculty will spend most of their time on research and also do teaching. But back in the 19th century, research was not something that was expected of any of the faculty and wasn't even allowed for as the time was being apportioned. And so Sylvester really had to work at this, and he would go down and he would talk with members of Parliament and try to arrange for pressure to be put on the Royal Military Academy to give him more time to conduct mathematical research. Sylvester also had problems at the Royal Military Academy because in 1870, when he reached the age of 55, he was forced into retirement. He was by no means ready to retire. He was at the peak of his powers. But at that time, the regulation was that you had to retire at age 55. Fortunately for James Joseph Sylvester, somebody else would realize his potential and hire him, and that was the Johns Hopkins University in Baltimore, Maryland. In 1877, James Joseph Sylvester was brought in and began teaching at the Johns Hopkins University, which began its first classes in that year. They hired Sylvester in order to set up a graduate program in mathematics Sylvester came to the United States, and now he had the kind of good experience that he had always really been looking for, a chance to work with excellent graduate students, to really spend time doing the research and using the research in order to influence what he was doing in his classes, to begin to build a research mathematical community in the United States. And at the same time, he also founded the first journal devoted exclusively to mathematics in the United States, the American Journal of Mathematics. And the seminars that Sylvester led were fascinating seminars, and one of his students wrote about it. Any unsolved difficulty, any suggested extension, such would have been passed by with a mention by other lecturers, became inevitably with him the occasion of a digression, which was sure to consume many weeks if indeed it did not take him away from the original object permanently. So Sylvester would find something in the lecture that was interesting, and he'd just take the whole class away and begin to pursue that. And he would get the class involved in his research. So he would introduce a topic such as partitions and look at the various ways this could be extended, and various students would work on pieces of these. And then at the end of the semester, he would take all of this work and get it published in the American Journal. So one of my favorite papers from this journal is one entitled A Constructive Theory of Partitions, arranged in 3 acts, an interact, and an exodian, which gives you some idea of the kind of flowery language that Sylvester loved. And what this was an article in which Sylvester begins to explain this theory of partitions. And then after he's done some explanation, he turns the paper over to one of his students, who then explains a particular result that he or she had found, because this graduate seminar contained not just men, but there also was a woman in this seminar. And so they would explain what they had been doing, and then Sylvester's voice would come back in, and he would continue for a while, and then he would turn the paper over to another one of his students. And so it's fascinating to read this just for the way the paper is put together and draws on the work of his students. And in fact, Sylvester would be very successful in training research mathematicians who would go on to work in the other great universities of the United States and help to build up the graduate programs there. In 1883, Sylvester was finally recognized by the British universities for the great mathematician that he was. By this time, the restriction against Jews in Oxford and Cambridge had been lifted, and Sylvester came back and was appointed to the position of civilian professor at Oxford. This is the same chair of mathematics that John Wallis had held back in the 17th century. The next mathematician I want to talk about is Srinivasa Ramanujan. Ramanujan was born in southern India in Tamil Nadu in 1887. He grew up in Kumbakonam. He was a Brahmin, so he was of the highest caste. He was of the priestly caste. Even though his family was of high caste, this did not mean that they had much money. His father was a clerk in a store, and in order to supplement their income, they took in boarders. In Kumbakonam, there is a government college, and they would take some of the students from that college and board them at their home in order to get this extra source of income. And Ramanujan was extremely talented in mathematics from a very early age, and he was fascinated by the mathematics that these boarders were studying in the government college. And so he began to look at their textbooks and began to learn mathematics on his own even before he was ready to go on and enter college. And one of the books that he read that had a profound influence on him was a book by G.S. Carr called A Synopsis of Elementary Results in Pure Mathematics. And this is an incredible book. It's 935 pages of dense formulas and equations. It was really written in order to help prepare students for this Tripos exam, the exam given at Cambridge that would run over several days and decide who was ready for a research career. And the idea was you were supposed to memorize everything in these 935 pages, and they are really dense. There's some indication of where these results come from and how they're connected, but basically it's just a listing of results. And Ramanujan was fascinated by these, and he began to play around with these ideas. Some of the kinds of things that he discovered are the Bernoulli numbers that I mentioned earlier, coming from Jacob Bernoulli's book Ars Conjectandi, that his brother Johann had managed to get published after Jacob had died. And so Ramanujan began to play with these ideas and see how he could build on them, and he began keeping notebooks in which he wrote down the things that he had found. Even though the family was very poor, being high caste Brahmin, education was extremely important to them. So Ramanujan's family decided that they would make the sacrifice and see that he could go to college. And in 1904, he entered the Government Arts College in Kumbakonam. Unfortunately for Ramanujan, he was only really interested in mathematics, and he failed his examinations in every subject except mathematics, and so he was expelled from the college. 2 years later, he tried again to enter college. He went to a private college in Madras, Pachayappa's college, and again he failed his examinations in the first year and was forced to leave. But one of the nice things that his family did for him at this point was allow him to continue working on his mathematics. And so for the next several years, he traveled around southern India, staying with family members, staying with friends, carrying his notebooks with him. He had no source of income, but he was willing to find people who were going to put him up for a few weeks or perhaps a few months, let him work on his mathematics, and just do what was of great interest to him. But eventually he realized that he did need some kind of source of income, and he also needed to connect with the wider mathematical community. And fortunately for Ramanujan, he got connected with Ramachandra Rao. This was a civil servant, a very prominent civil servant in Madras, and also a very active mathematician. He was the secretary of the local section of the Indian Mathematical Society, and eventually Ramachandra Rao would go on to become president of the Indian Mathematical Society. And he became Ramanujan's patron. He gave Ramanujan a little bit of spending money, but even more important than that, he gave Ramanujan an entry into the mathematical community at Madras. So Ramanujan began interacting with those mathematicians, and he also began going to the university library at the University of Madras and reading the mathematical books that were there, and learning mathematics on his own from the mathematical books in that great library. Now, as he shared his results in mathematics with the other mathematicians in Madras, they began to realize that he was doing things that they couldn't fully appreciate. And so the mathematicians of Madras suggested that Ramanujan contact some of the mathematicians in England to see how important it was, how important his mathematics really was, and how it tied into what other people are doing. And we know that Ramanujan wrote to several mathematicians. Mathematicians always get letters from people who think they've accomplished great things, and most of the time we pay very little attention to those letters that come in. But one of the people to whom Ramanujan wrote was G.H. Hardy, probably the greatest mathematician of the time in England. Hardy had worked on problems similar to those that Ramanujan was working on, and Hardy later wrote about receiving this letter from Ramanujan. He opened it one morning. He usually would open his mail in the morning and do some mathematics and then go off to lunch and then perhaps play tennis and watch a game of cricket, go for a walk in the afternoon, and then after supper he would go back and work on his mathematics. And he had read the letter, and he'd seen many letters that were kind of that sort. Dear sir, I've discovered something remarkable that I'm sure you'll find very impressive. He had put it aside. He'd glanced at some of the results that Ramanujan had found, but during the day these results began to nag at him. Some of them looked familiar enough that he thought there was some real mathematics there. And after supper, he went back and he looked over the letter more closely. And as he looked through it, he saw some things that he already knew, results that were known to him and to other mathematicians who worked in this area. He found some results that he didn't recognize, but he figured out that he could do them, and some of them he actually worked through, and was surprised that they were a little bit more difficult to do than he had thought they might be. And then there were other results in this letter that just totally astounded him. They were unlike any mathematics he'd ever seen before. And he came to the conclusion that this could not be pure bunk, that nobody would have the genius just to invent these out of whole cloth. There had to be some method behind them. There had to be some real understanding of mathematics behind these results that were truly new to Hardy. Well, what Hardy did was then to share this letter with his colleague at Cambridge, Littlewood, and the two of them came to the conclusion that Ramanujan really had done something outstanding. And so they wrote back to Ramanujan, asked him to explain some of his methods. Ramanujan had not gone through a traditional training in mathematics, and so he didn't have proofs in the usual sense that mathematicians look for these proofs. He understood the patterns, he understood what was going on in the structure of the mathematics, and used that in order to predict the formulas that he came up with. In some cases, he was wrong. He simply misunderstood what was going on, and Hardy and Littlewood were able to pick up some of those errors. But in other places, he had very deep insight that nobody else had been able to find. And so a long-distance correspondence of trying to explain Ramanujan's ideas to Hardy and Littlewood became very difficult, and fairly quickly Hardy and Littlewood realized that they needed to bring Ramanujan to England, hopefully to help fill in some of the gaps in his education, but also to be able to work with him directly in order to understand what he was doing and help him fully develop his talents. Well, one of the problems is that Ramanujan was Brahmin. And to be Brahmin is not to hold a set of beliefs, it is to be embedded in a community. And for this reason, to leave the community is to cease to be a Brahmin. To leave India and to go to England would be to lose caste. And so this would be a momentous decision. And initially, Ramanujan was reluctant to make this decision to go to England. And certainly his family was reluctant to let him go. But there's a wonderful story of Ramanujan and his mother making a pilgrimage to the shrine of the goddess Namagiri, which was the family goddess. And for several days they fasted and prayed for a sense of whether or not Ramanujan should accept this invitation to go to England. And there are various accounts of what happened. It's not clear if it was a vision or a dream. There also are conflicting reports whether it came to Ramanujan or it came to his mother. But eventually, after several days of prayer and fasting, it was revealed that Ramanujan's fate, in fact, was to go to England. That is what the goddess wanted him to do. And so he traveled to England in the summer of 1914. He went there with the decision that he would try to live as best he could as a Brahmin and maintain the dietary restrictions. This became very difficult because at the end of the summer of 1914, the First World War broke out. And it would have been difficult for Ramanujan in any case. He was used to having someone else cook his meals. Suddenly he had to cook them himself. He was only used to eating the food of South India, and that was very difficult to find in England. It was even difficult during the war to find fresh fruit and vegetables. And so he was under a great deal of stress. He was unused to the cold climate. And his years in England became very, very difficult. He did brilliant mathematics. His collaboration with Hardy was very important. He did incredible things during that time. One of them deals with the partition function. So I talked about this problem of taking the number 5 and asking how many ways we can write it as a sum of positive integers, and there are 7 of them. Well, what if I want to take 100? Well, you can actually list the number of ways of writing 100 as a sum of positive integers. But what if I've got 100,000, or 1,000,000, or 10 million, or 1 billion? Well, one of the amazing things that Ramanujan and Hardy were able to do together is to find a precise formula that enables you to find the number of partitions of 1 billion. very, very quickly, very efficiently. And it's something that nobody else would have suspected was possible. Certainly Hardy didn't expect it was possible. And the collaboration really worked beautifully here because Ramanujan got the insights, he got the ideas, and then Hardy filled in the details that were needed in order to turn this into a mathematical paper that could actually be published and accepted by the rest of the mathematical community. In 1918, Ramanujan was elected as a Fellow of the Royal Society. And there are a number of stories of his mathematical prowess, one of them that I just want to mention. In the latter years that Ramanujan was in England, as his health deteriorated, he spent a lot of time in hospital. One of the times that Hardy visited him in hospital, he arrived and trying to think of something to say, remarked to Ramanujan, "I came in cab number 1729, and I've been thinking about that number, and it's not really very interesting." And Ramanujan replied to him, "No, Hardy, that is a very interesting number. It's the smallest integer that can be written as a sum of two cubes in two different ways. We can write it as 12 cubed plus 1 cubed, or we can write it as 10 cubed plus 9 cubed. And one of the things that people have said about Ramanujan that's very true is that every number was a personal friend to Ramanujan. He knew the numbers intimately, he knew the properties of these numbers and what could be done with them. In 1919, Ramanujan returned to India really as soon as the sea routes were open and it was possible to go back. It was hoped that going back to India would restore him to health. In fact, it didn't. His health continued to deteriorate, and within a year he was dead. He died in 1920 at the age of 32. But in the last year of his life, he was working feverishly on his mathematics. And he wrote back to Hardy with a few intriguing descriptions of the kinds of things he was working on. He was working on something that he called Mach theta functions. Now, I described the theta functions that Jacobi came up with in the 1820s. So these were functions that were used in order to find elliptic functions with a particular period. And the theta functions have this transformation invariance that's connected with that picture that you see in the Escher graphic, circle limit 3. So this is connected to the theta functions, and it's this kind of transformation invariance that gives the theta functions so much of their power. What Ramanujan was doing was looking at functions that have many of the same kinds of properties that were discovered for the theta functions, but did not have the same transformation invariance that we have for theta functions. In fact, what he was showing is many of the properties that people thought came from transformation invariance, in fact, came from other properties that applied to a much larger class of functions. But unfortunately, nobody knew very much about what Ramanujan had been doing in this last year. In the early 1960s, at the University of Pennsylvania, a young graduate student by the name of George Andrews was given the task for his doctoral thesis of looking at what people had been able to figure out about these Mach theta functions and see what he could do with them. George Andrews would go on to be a very prominent research mathematician. And in 1976, he was visiting in England, talking with a mathematician in London, who said, you're interested in Ramanujan, you should go up to the Cambridge Library. They've got some papers of Ramanujan's that nobody has ever looked at very carefully. And so George went up there, and periodically there had been Ramanujan papers that had surfaced. These were usually manuscripts from Ramanujan's time in Cambridge. So he had produced a lot of scraps of paper that different people had collected and put away, and eventually they would find themselves in the library at either Cambridge or Oxford. And Andrews expected that he would find these papers there. When he opened up this box, he was amazed at what he found, because what he saw in one of the first pages that he pulled out of the box were precisely the Mach theta functions that Ramanujan only looked at during the last year of his life. What George Andrews had found were Ramanujan's work on the Mach theta functions from his year after he had returned to India. This collection of papers would become known as the Lost Notebook, which is a double misnomer. It was never lost. Certainly the librarians at Cambridge always knew it existed. It was in a box that was labeled as Papers of Ramanujan, although what had been lost was the fact that this was work from Ramanujan's last year of life. And it was never a notebook. It's simply a pile of loose sheets of paper. But one of the fascinating things is that this is work that Ramanujan had done between 1919 and 1920, and when it was rediscovered in 1976, it was fresh and important. It turned out to have direct applications to questions that people like Rodney Baxter were then looking at in physics, in the area of statistical mechanics. And George Andrews, Bruce Berndt at the University of Illinois, myself, many other mathematicians have looked at these papers and tried to understand what Ramanujan was doing, trying to put them into the broader context of what we know about mathematics, what we know about theta functions, what we know about modular functions and elliptic functions. And there are a lot of fantastic insights. And in the decade since 1976, there's been a whole industry, mathematicians building on these results of Ramanujan. It is absolutely incredible that this man was so far ahead of what the rest of the mathematical community was doing. For my next lecture, I'm going to turn to the proof of Fermat's last theorem and get into some of the very deep mathematics of the 20th century. In this lecture, we're going to look at the proof of Fermat's last theorem. The actual result is something that mathematicians really don't have much use for. I personally don't know of any other mathematical results that rest on Fermat's last theorem. But it's the process of trying to find the proof of this result that would be so important, and that would open up entirely new areas of mathematics that would have important repercussions for lots of the applications of mathematics. If you'll recall, Fermat's last theorem is something that Fermat referred to in the margin of his copy of Diophantus's Arithmetica, and he'd been looking at the Pythagorean triples. So these, again, are triples of integers, so that the square of the first plus the square of the second is equal to the square of the third. Examples of Pythagorean triples are 3, 4, 5, 5, 12, 13, 8, 15, 17, and so on. And we know that there are infinitely many of these. What Fermat had considered was trying to do the same thing for third powers or fourth powers or other higher powers. Can you find three integers so that the first integer cubed plus the second integer cubed is equal to the third integer cubed? Or the first integer to the fourth power is equal to the second integer to the fourth, or the first integer to the fourth power plus the second integer to the fourth power is equal to the third integer to the fourth power, or fifth powers, or so on. And he wrote in the margin to Diophantus's Arithmetica that this could not be done, but he didn't have a proof that could fit into the margin, that he figured out how to do it, but he couldn't fit it in there. In fact, we do know that Fermat had worked out the case for the exponent 4. And so he actually did have that result, which was in another manuscript that was discovered later after his death. But the other cases, he almost certainly did not know how to prove them. It was in the 18th century that Leonhard Euler would take a look at Fermat's last theorem for the exponent 3 and come up with a proof that you can't find three integers that satisfy this equation with the exponent 3. And as I said when I was talking about Leonhard Euler, there are some gaps in his proof, But Euler himself knew the mathematics that was needed to fill in those gaps. And so it's appropriate to credit the n equals 3 case, the exponent 3 case of Fermat's last theorem to Leonhard Euler. So in the beginning of the 1800s, the next case that was out there was the case of the exponent 5. And there's a nice story behind proving that there is no solution for the exponent 5 that involves 3 very different mathematicians. The first of these was Sophie Germain, and we have talked about her before. She's the person who corresponded with Gauss about number theory. Gauss was so pleased to see a woman working in mathematics. She is the person who discovered the young Galois and what he was trying to do and encouraged him and helped connect him with other mathematicians who might be interested in his work. And Sophie Germain was interested in the problem of Fermat's last theorem, and she studied this problem of the exponent 5. And while she was not able to find a proof that it could not be done, she was able to show that if there is a solution, then one of those 3 integers must be divisible by 5. This idea was then picked up by the very young Gustave Lejeune Dirichlet. This is in 1825 when Dirichlet began working on this problem. He was only 20 years old. We have encountered Dirichlet at various other points later in his career. In 1829, he would publish the very important work on Fourier analysis, and then he would go on and succeed Gauss as chair of mathematics at the University of Göttingen in the 1850s. But this was early in his career. He was 20 years old, and he was able to show that if there is a solution to Fermat's last theorem with the exponent 5, then the number that is divisible by 5 must be an odd integer. Well, this then was picked up by Adrien-Marie Legendre, and we've also encountered Legendre before. He's somebody who played a role in the development of elliptic functions, one of the first people to study these doubly periodic functions. And after Dirichlet did his work, Legendre picked it up. This also was in 1825. Legendre at this point was a relatively old man. He was 72, but he was still extremely sharp. And he looked at what Sophie Germain and Gustave Lejeune Dirichlet had done. They had shown that there must be a number that's divisible by 5 if there is a solution. Dirichlet had shown that that number must be odd. And what Legendre was able to show is that number can't be odd. The number divisible by 5 must be even. And since there are no integers that are both even and odd, there can't be a solution with the exponent 5. The next progress that was made on Fermat's last theorem was in 1832. Dirichlet went back to this problem, and he showed that you can't get a solution when the exponent is 14. So he's really skipped ahead quite a few. And actually, you can skip some of the exponents. There's no reason to check the case where the exponent is 6, because if we can't have a solution with the exponent 3, then we also can't have a solution with the exponent 6, because if I know that x to the 6th plus y to the 6th is equal to z to the 6th, then I just work with x squared, y squared, and z squared, and x squared cubed plus y squared cubed is going to equal z squared cubed. And so if I've got a solution with 6, I will also have a solution with 3. No solution with 3 means no solution with 6. So from here on out, we can restrict ourselves to the prime exponents. The next case to study is 7, and then after that, we need to consider 11 and 13 and so on through the possible primes. The case of the exponent 7 was solved by Gabriel Lemay in 1839. And in 1847, Lemay took his work on the exponent 7, and he announced that he now could extend this and prove Fermat's last theorem in general. And I want to give you some idea of the approach that Lemay was taking, because it would be very important for some of the later developments in mathematics. If we back up to the Pythagorean triples, I want to find 3 integers x, y, and z so that x squared plus y squared equals z squared. And one of the keys to finding all of the possible triples of integers that give you Pythagorean triples is to take that polynomial on the left-hand side, x squared plus y squared, and factor it. Now, if I had x squared minus y squared, I could factor that. X squared minus y squared is equal to x minus y times x plus y. X squared plus y squared doesn't seem to factor, but if I introduce the complex integers, so these are integers that are made up of a real part and an imaginary part that also is an integer, something like 2 plus 3i is a complex integer, I can now factor x squared plus y squared. It's equal to x plus I times y multiplied by x minus I times y. And we can use this factorization in order to discover all of the Pythagorean triples. So one of the things that happens, though, as we begin to expand our idea of integer to what would come to be called the Gaussian integers, because Gauss did a lot of work with these complex integers, is that factorization changes. Some of the numbers that are prime remain prime. 3 cannot be written as a product of two smaller positive integers in the ordinary integers, and it also can't be written as a product of two smaller positive integers in the Gaussian integers. But 2 can be factored. 2 is equal to 1 plus I multiplied by 1 minus I. 5 also can be factored. It's no longer a prime in the Gaussian integers. It's 1 plus 2i times 1 minus 2i. And if you look at the proof that Fermat's last theorem is true for the exponent 3, the best way of proving that is actually to use the same sort of idea. You want to try to factor that polynomial x cubed plus y cubed. Now, x cubed plus y cubed actually can be factored normally as x plus y multiplied by the quantity x squared minus xy plus y squared. But you can't completely factor it into linear factors. But you can factor it completely into linear factors if you extend your idea of what constitutes an integer and introduce the cube root of 1. So the cube root of 1, which is e to the 2 pi I over 3, if you introduce that and look at the integers that are made up from ordinary integers and then powers of this primitive cube root of 1, you can do that factorization of x cubed plus y cubed into linear factors. It turns out to be x plus y times x plus this cube root of 1 times y plus times x plus the cube root of 1 squared times y. And using that, you can then prove the impossibility of finding a solution to x cubed plus y cubed equals z cubed. And the idea that Lemay was using in his work of 1847 was to try to do this factorization in general. If I'm looking at x to the n plus y to the n, I want to factor that into these linear factors, into n products of simple binomials. And if we introduce these integers that use the nth roots of unity, then it is possible to do that factorization. Now, Lemay presented his result to the Academy of Science in Paris in 1847, and there was a good deal of discussion that this engendered. Liouville was one of the mathematicians who was present. We have encountered Liouville before. He's the person who discovered Galois' manuscript and saw that it got publicized and saw that Galois theory would actually emerge into the general mathematical conscience. And Liouville pointed out that there was a basic flaw in Lemay's approach to this problem of trying to prove Fermat's last theorem. If we think of the primes in the ordinary integers, there is only one way of taking an integer and writing it as a product of primes. 6 is equal to 2 times 3, or it's equal to 3 times 2. But I can't find two completely different primes and multiply them together in order to get 6. If I want to take 2 primes and multiply them together to get 6, I've got to use 2 and 3. And Lemay had assumed that this would continue to be true for these other kinds of extended integers that involve these nth roots of 1. And what Liouville said was that he wasn't so sure that that was true, that it might in fact be possible that at some point you would encounter cases where factorization was not unique. There might be more than one way of choosing the primes that get multiplied together to get one of these extended integers. Another response that was made to Lamay's assertion of a proof was from Cauchy. We've met Cauchy in connection with his attempt to set calculus on a firm foundation. Cauchy had also thought about the problem of Fermat's last theorem, and Cauchy announced to Lemay that everything that Lemay said, Cauchy had already thought of first. On March 15th of that year, another mathematician by the name of Wenzel announced that he had a proof that this factorization in fact would be unique, and so Lamay's approach should be correct. And the following week, on March 22nd, both Lemay and Cauchy submitted sealed envelopes in which they put all of their work. Neither Lemay nor Cauchy, felt that they had a complete proof in place yet. They had an idea of a proof, and so they wanted to write down what they thought they knew. And this was a common practice at the Academy of Science at that time, and in many other academies of science throughout Europe, is if somebody had a brilliant idea but had not yet worked out all the details, they would put that idea down on paper, put it in a sealed envelope, and deposit it with the Academy, so that if later on there was a controversy over who came up with a critical idea first, they could go back and say, open this dated envelope and you'll see that I really knew that result on March 22nd of 1847. Liouville still had his suspicions that perhaps Wenzel wasn't correct in saying that factorization had to be unique. And in a series of correspondences with another mathematician, Ernst Kummer, in Berlin, Liouville shared his skepticism. Kummer wrote back and said, in fact, your skepticism is well placed. I know for a fact that the factorization is not always going to be unique. And as Kummer would later show, if you look at the prime exponent 37 and you take extended integers that involve the 37th root of 1, you are not going to get uniqueness of factorization. And so the proof that Lemay and also Cauchy thought they had for Fermat's last theorem fell apart at this point. Kummer continued to work on this problem, though, of the factorization. One of the things he was able to show is that if factorization is unique, in other words, for all of the primes below 37, you can in fact prove Fermat's last theorem. And so he came out with this, and he began to study this whole question of these extended integers, these generalizations of the integers, something that eventually would come to be called algebraic integers. And what is the property of them? How does their factorization work? How do they differ from the ordinary integers? And this whole work on algebraic integers would really come to its fruition in 1877, when Richard Dedekind would publish a very influential book, The Theory of Algebraic Integers. Richard Dedekind is also somebody that we have encountered before. He was a graduate student with Riemann. He was Riemann's friend who traveled with him in Italy. And it was Richard Dedekind who got many of Riemann's manuscripts published. And one of Dedekind's most important contributions to mathematics would be this great understanding of the algebraic integers. I mentioned the Bernoulli numbers before, these numbers that came out of Jakob Bernoulli's work in probability theory. And one of the things that eventually would be discovered is a connection between the numerators of these rational Bernoulli numbers and Fermat's last theorem. What eventually would be shown is that if you take the Bernoulli numbers up to the p minus third Bernoulli number, and if p does not divide any of those numerators, then if you look at the algebraic integers that involve the pth root of 1, factorization is going to be unique. So what this says is you take the numerators of the Bernoulli numbers up to p minus 3, and if p does not divide any of those numerators, then Fermat's last theorem is true for the exponent p. And eventually people would extend this result. What if p divides one of those numerators, but only one of them, and p squared does not divide any of those numerators? Eventually it would be possible to extend the result and show that in that case, Fermat's last theorem can be proven. Well, what if p squared divides one of the numerators, but you can't divide p cubed into the product of these numerators? Eventually it would be shown that in that case, Fermat's last theorem is true. And so mathematicians began building up cases where they knew Fermat's last theorem was true, that you couldn't find the triple of integers, so that x to the p plus y to the p equals z to the p. And by 1976, it had gotten to the point where it was known that Fermat's last theorem was true for all exponents below 100,000. Well, that's quite an accomplishment, but of course the claim is that Fermat's last theorem is true for all possible exponents. And there are a lot more exponents that are larger than 100,000 than exponents that are less than 100,000. So a really new approach was needed. And the first breakthrough came about in 1983. The German mathematician Gerd Faltings, who was born in 1954, was able to show that for each exponent greater than or equal to 3, we have at most finitely many solutions. If you'll recall, with the Pythagorean triples, we actually get infinitely many solutions. And a number of people hoped that maybe this would be the door into an ultimate proof. Maybe you could show that once there is one solution, there have to be infinitely many solutions that can be generated from that. And Faltings now has proven that in each case you have at most finitely many solutions. But as it turns out, nobody was able to build directly on Faltings' result, although it was an important result. Something else that was going on at this time, as I said, Fermat's last theorem had been proven for all of the exponents up to 100,000. And there are many other types of exponents for which it was known that Fermat's last theorem was true, but it was not known that there were infinitely many exponents for which Fermat's last theorem is true. And in 1985, two mathematicians working quite independently would show that, in fact, Fermat's last theorem must be true not just for infinitely many exponents, but in some precise mathematical sense, it must be true for most of the exponents. There could still be infinitely many exceptions, but they would have to occur at rather infrequent intervals. This result was found by Andrew Granville and Roger Heath Brown. But even that result would not really lead into the ultimate proof of Fermat's last theorem. What was needed was a totally different approach, and this would come out of the study of elliptic functions and modular functions. And it's the reason why I talked so much about elliptic functions and modular functions in earlier lectures. I want to go back to Weierstrass's work. I said that Weierstrass, this high school teacher, had published a very important work on abelian functions. And one of the things that he accomplished in that paper and in his later work on these abelian or elliptic functions was to find a very efficient way of describing these elliptic functions with two specific parameters. Parameters that today we refer to as G2 and G3. You pick two numbers to take on these values, G2 and G3, and that uniquely determines your elliptic function. And he denoted these elliptic functions by the German letter P, a script P. And so they are known as P functions today very often instead of elliptic functions, especially if they are in Weierstrass's form. And Weierstrass found the differential equation that these P functions satisfy. He was able to show that if you take the derivative of the P function and square it, that is equal to a cubic polynomial in the P function. It's equal to 4 times the cube of the P function minus this constant G2 times the P function minus the constant g3. Now, as succeeding mathematicians studied these elliptic functions, they found that it was very useful to actually look at a surface in which they could be analyzed. And the surface that you want to look at is a surface that corresponds to this exact equation. Namely, it's the surface y squared equals 4x cubed minus g2 times x minus g3. Now, I said surface. Normally, that would be a curve, because what I have is an algebraic equation between two variables, an x variable and a y variable, and so that defines a curve on the plane. But in this case, the input is going to be a complex number, and the output is going to be a complex number. And so what you're really looking at as you look at the space of all solutions to this equation is a two-dimensional surface that sits in four-dimensional space. This two-dimensional surface in four-dimensional space is what is known as the elliptic curve. It's called a curve because if we restricted it to one input variable and one output variable, a simple real variable in and a real variable out, we would in fact get a curve. But it really is a surface sitting in four-dimensional space. And more than that, we want to include the point out at infinity. And so we really want to look at this this elliptic curve and take its projection in much the same way that I looked at projective space before, when I took all of the lines through the origin and took each of these lines and replaced them by a single point. The same kind of idea can be used with this elliptic curve in order to include the point at infinity in this surface that you're looking at. So you get a very strange surface that you can't actually visualize. It's a two-dimensional surface sitting in four-dimensional space to which you've applied this projective operator so that you get the point at infinity included in this particular space. It's called the elliptic curve, which is a bit deceptive because it really doesn't have much to do with ellipses. If you'll recall, I was able to trace that adjective elliptic that's applied to elliptic functions back to something that was connected with the arc length of an ellipse. But the name has stayed there. An elliptic curve doesn't look at all like an ellipse. But these elliptic curves turned out to be very useful in many questions in mathematics, in analysis, and people began to study these. And you have the elliptic curves that come out of the elliptic functions, but there also are other elliptic curves out there. And during the 1950s, a number of mathematicians looked at elliptic curves that come from modular functions. So these modular functions are the generalizations of theta functions. The modular functions are the functions that are invariant under the kinds of transformations that we see represented in Escher's print, the circle limit 3. And each modular function gives rise to an elliptic curve. And what the mathematicians of the 1950s began to suspect was that every elliptic curve also corresponds to one of these modular functions. If that's true, that would be a very powerful statement because it connects two very different areas of mathematics: the geometry of elliptic curves and the analysis of these modular functions. The statement that was made, the conjecture that was made, was that every elliptic curve is modular, and this is a conjecture that would be made by two Japanese mathematicians who were working together, Yutaka Taniyama and Goro Shimura, and also by a French mathematician who was working in the same area, André Weil. And they independently came up with this conjecture that every elliptic curve is modular. And that would be very powerful if we think back to analytic geometry that provides this correspondence between geometry and algebra. Every algebraic equation gives rise to a geometric curve. Not every geometric curve comes from an algebraic expression. But what if we did know that every algebraic curve, or every curve that had sufficiently nice geometric properties, in fact corresponded to an algebraic equation? That kind of correspondence would be very useful to know. And what Taniyama, Shimura, and Wei conjectured is that that precisely is what is going on with the elliptic curves, that every elliptic curve corresponds to a modular function. So if you've got a question about modular functions, you can translate that over into the geometry. And it may be obvious what's going on in the geometry, and you can use that for insight into modular functions. Or if you've got a question about the geometry, you can translate that into the modular functions. And it may be that there's a property of modular functions that enables you to say something important about the geometry. Now, the next progress was made around 1980 when Jean-Pierre Serre and Gerhard Frey were able to show that if Fermat's last theorem is false, that has to give us three particular integers, some x to the n plus y to the n equals z to the n, that can be used to construct a very strange elliptic curve. A curve that is so strange that in fact it is not modular. It does not correspond to a modular function. And while they conjectured that this would be the case, it was not until 1986 that Ken Ribet was actually able to show that this curve that can be constructed, this geometric object that can be constructed out of a counterexample to Fermat's last theorem, actually could not be something that corresponds to a modular function. So if Fermat's last theorem is false, that says that not every elliptic curve is modular. On the other hand, if we know that every elliptic curve in fact is modular, that tells us that Fermat's last theorem must be true. And in 1993, Andrew Wiles at Princeton announced that he was able to prove this Taniyama-Shimura-Wei conjecture. He actually was not able to prove it in its full generality, but he was able to prove it in the case of the elliptic curves that included this Serre-Frey curve that was built on a counterexample to Fermat's last theorem. And so it was Andrew Wiles who announced in 1993 that in fact Fermat's last theorem is true because every elliptic curve of the appropriate kind is modular. There were some flaws in the original proof. In 1994, Richard Taylor, one of Andrew Wiles' students, was brought in to help with cleaning up the proof. And then in 1995, this proof of Fermat's last theorem was finally published. Initially, Fermat's last theorem was done as a special case of the Taniyama-Shimura-Wei conjecture. The full Taniyama-Shimura-Wei conjecture would be proven in 1999 by a group of mathematicians, including Christophe Breuil, Brian Conrad, Fred Diamond, and Richard Taylor, thus closing one of the most important stories in the history of mathematics, a result that was not important in and of itself, but important because of all the mathematics to which it gave rise. In this lecture, we're going to look at mathematics as the ultimate physical reality. Our intuition serves us very well when we're looking at things on the scale of a meter, or a few tens or hundreds or thousands of meters, or a centimeter or a millimeter. Those are the scales at which we understand how the world works, and we can rely on our intuition. But as soon as we try to extend our understanding to the cosmic scale, to speeds that approach the speed of light, or to the subatomic scale, our intuition fails us. And what scientists have learned is that in these realms that are outside of our intuition, we need to rely on mathematics in order to tell us what is going on. And so in this lecture, beginning with Maxwell's equations and continuing through general relativity, quantum mechanics, and modern string theory, we're going to see how mathematics enables us to work with physical realities for which our experience fails us. If you'll recall, we've already seen some of the ways in which mathematics suggests excess content. This was certainly true of Fourier in his work with heat, the transfer of heat. What he saw was that there is a connection between the transfer of heat and the mathematics of a vibrating string. There's no reason why anyone would have expected this before, but the mathematics shows us this connection, and this connection would turn out to be very powerful. And it's precisely these kinds of connections, these unexpected excess content that comes out of applying the mathematics to the physical reality that is what makes mathematics so important in understanding the fundamental nature of reality that is out there. I want to start with the story of electricity and magnetism. Initially, the study of electricity was the study of static electricity. But in the late 1700s, the voltaic pile, or what today we would call a battery, was invented, and it became possible to actually generate a current. So electricity that was not simply discharged as a spark in a single instant, but the ability to produce a continual discharge of electricity, thus creating a current. People were also interested in magnetism at this time. And in 1820, the Danish scientist Hans Christian Ørsted realized that there was a connection between electricity and magnetism. The story is that he was giving a lecture, and he had an electrical apparatus set up on his table, and there also was a compass there, and he noticed that as he closed the circuit, the needle on the compass would move. It was clear that the electric current was creating some kind of magnetic field. And Ørsted actually sat on this result for several months. He was trying to work out what exactly was happening, what was the mathematics behind it. But eventually he realized that he needed to share this result with the rest of the scientific world. And his announcement came out on July 21st of 1820. And immediately all of the great scientists of Europe dropped whatever they were doing, and they started working on this question of what is the relationship between electricity and magnetism. And the work was really feverish. Ampère in Paris, by September of that same year, just 2 months later, would announce an entire series of lectures on the mathematics explaining the connection between electricity and magnetism. Actually, the first important mathematical model of the connection between electricity and magnetism would come in that year of 1820, but from other French scientists. It was Jean-Baptiste Biot and Félix Savart who would come up with an equation that would relate the electric current to the magnetic field. And so we have the Biot-Savart equation. Several years later, in 1831, Michael Faraday would realize that not only does an electric current create a magnetic field, but a magnetic field can be used to create an electric current. So that if we take a magnet and we simply move it around a wire, that's going to induce an electric current. And this is the idea behind our modern generation of electricity. It's done by dynamos, which basically have rotating magnets, which in turn then induce this current. And out of Faraday's work, it became possible to come up with an equation that explains how this magnetic field interacts with the electrical current. And now we get an equation that actually depends not just on 3 spatial dimensions, but it also depends on the dimension of time, because it's the change in the magnetic field that turns out to be critical in generating the electric current. Now, another important piece of our understanding of electricity and magnetism will come from Carl Friedrich Gauss, who did a lot of work in electricity and magnetism. He actually created one of the very first telegraphs to be created. And he was interested in the question of electrostatic potential. And so I need to back up a little bit and talk about potential and potential energy. When we were looking at Newton, Newton explained gravitational attraction through the forces. Gravity exerts a force which is proportional to the rate at which the velocity is changing. And all of Newton's celestial mechanics was stated in terms of these forces. By the late 1700s, scientists working in astronomy realized that life would be much easier if instead of working with the forces, we worked at potential energy. So you think about a book that's lying on the floor. If you lift that book up and hold it high in the air, it now has a much higher potential energy. We can let go of it, and it has the potential to develop energy as it falls. So its potential energy level is much higher. That potential energy can then be translated into kinetic energy as it falls. And it turns out to be much easier to work with potential energy rather than forces, because the way the force of gravity works is it tends to move an object from an area of high potential energy to an area of low potential energy. And the advantage of working with a potential energy is that that is a single number. It's not a vector. It doesn't have direction. But once you know what the energy level is at each point in space, you know that an object is always going to be pulled in the direction of the greatest change, the greatest decrease in its potential energy. So if you know the energy levels, you can use that to determine the forces, but it's much easier to work with the energy. And what Gauss did was to take a look at electrostatics. So these are the kinds of attractive or repellent forces that you get with something that is electrostatically charged. And he set up a model for the way in which electrostatic potential energy works. And so this is known as the electrostatic potential. In the 1860s, the British scientist James Clerk Maxwell decided to try to take this idea that Gauss had done for electrostatics and apply it to electrodynamics. So we've got this interaction between electricity and magnetism, and it's a dynamical system. It's something that's changing over time. The magnetic field changes over time. The electric current can change over time. What Maxwell wanted to do was to find an electrodynamic potential that could be used in order to simplify the various equations that were out there that related electricity and magnetism. And in 1864, he succeeded in this, and he published his results as the groundbreaking paper, A Dynamical Theory of the Electromagnetic Field. Now, Maxwell's equations are often stated as four separate equations, but in fact, you can unite all four of these equations if you think about the electromagnetic potential. And Maxwell then took a look at this electromagnetic potential, and he began to explore its properties. And one of the curious things that he discovered about the electromagnetic potential is that just like Fourier's heat flow, the electromagnetic potential is related to the problem of a vibrating string. That this idea of the vibrations is happening in the electromagnetic potential. And the best way of understanding the electromagnetic potential is in terms of vibrations that are happening. Now, in the case of a string, those vibrations only happen in one direction. The string vibrates up and down. And as I said, Euler and others in the 1700s extended this to the idea of a drumhead, where the drumhead now is a two-dimensional surface that's going to vibrate in the third dimension. One of the strange things that happens with Maxwell's electromagnetic potential is that we are actually looking at a three-dimensional object that is vibrating. Now, it's not clear what direction it vibrates in because there aren't any dimensions left over for it to vibrate in, but it clearly is vibrating. And one of the things that happens if you pluck a string is that this disturbance in the string is going to spread out. Or if you take a pool of water and you disturb that, you see the waves that spread out. And what Maxwell realized was exactly the same sort of thing should happen with this electromagnetic potential. So mathematically, he was able to establish that this electromagnetic potential that is three-dimensional should spread out in all three dimensions, in all possible directions. The electromagnetic potential should spread out, and experimentally, he discovered that the electromagnetic potential should travel at the speed of light, thus suggesting that there is a fundamental connection between light and the electromagnetic potential. But the electromagnetic potential is a very strange thing. It is, at this point, it was only a mathematical construct. And a question for the scientists who were studying electricity and magnetism at this time was, is there any reality to this mathematical thing that we're calling the electromagnetic potential? You couldn't touch it, you couldn't see it, there wasn't any way of measuring it. It was just the mathematics that suggested that it was there. And so a number of scientists began exploring this question: can we actually get a handle on the electromagnetic potential? Can we show that it's real in some way? It took a long time. But finally, in 1887, the German scientist Heinrich Rudolf Hertz found a way of actually detecting electromagnetic potential and showing that, in fact, there was something there that could be detected. And a number of people realized at this point that that suggested the possibility of something that nobody had thought of before, which is communication over long distances without any physical connection, without the use of telegraph wires. Because if it is possible to detect these changes in the electromagnetic potential, then a person in one place could do some kind of manipulation with an electric current to cause certain changes in the electromagnetic potential, which should then travel at the speed of light. And somebody in a distant room might be able then to detect these changes in the electromagnetic potential and decode them in a way that would actually communicate a message. So it looked like it might be possible to communicate over substantial distances, perhaps even hundreds of yards, at the speed of light. Well, eventually, two scientists would figure out a means of actually doing this communication. That would happen independently in 1895 by the Russian scientist Alexander S. Popov and the Italian scientist Guglielmo Marconi. And what they invented, of course, was the radio. And what the radio does is it simply picks up these changes in the electromagnetic potential. And the electromagnetic potential, as it is traveling, is what today we refer to as radio waves. And what I love about this story is that nobody would have suspected the existence of radio waves had it not been for the fact that Maxwell did this mathematical work, came up with a purely mathematical construct that suggested that there was something called an electromagnetic potential that had to be traveling at the speed of light and that could actually be used to communicate over large distances without any physical connection. A lot of scientists then at this point began studying this electromagnetic potential in a great deal more detail. And there were two of them, the Irish scientist Fitzgerald and the Dutch scientist Lorentz, who both realized that there is a kind of basic transformation of space-time, a transformation of the four dimensions of space and time that leave electromagnetic potential unchanged. And so there's something about electromagnetic potential that as we do this transformation, that's a bit difficult to explain, but it's a transformation that in some way twists space and time. That doesn't change the basic equation of electromagnetic potential, and that suggests that electromagnetic phenomena, in fact, are invariant themselves under this transformation that would come to be known as the Lorentz transformation. And one of the consequences of this is that for an electromagnetic phenomena, distances actually contract as it is moving very close to the speed of light. That distances contract by a factor that's equal to the square root of 1 minus the square of the velocity of the electromagnetic phenomena divided by the square of the speed of light. It was Albert Einstein in 1905 who suggested that maybe this kind of contraction, this kind of invariance under Lorentz transformations, doesn't just happen for electromagnetic phenomena, but in fact it happens for everything. And this then would give rise to Einstein's special relativity This idea that if you take any object and you move it at a speed that is near the speed of light, that object is actually going to contract spatially. And more important, something else that he realized was that time itself is going to contract. So that this gives rise to the apparent paradox that if you've got two people who are standing on Earth, and one of them gets into a rocket ship and travels near the speed of light out to a distant galaxy, and then travels near the speed of light back home, the person who has traveled, when they're back together again, will have experienced less change in time than the person who had stayed stationary. And in fact, this is a phenomenon that has been verified. It has been possible to take extremely accurate clocks, put them up in orbit where the velocity is great enough. It's nowhere near the speed of light, but the velocity is actually great enough to be able to measure the fact that time progresses differently when you're moving very fast than it does when you're not moving. And so this became part of the excess content of this mathematics of the Lorentz transformation, actually predicting things that would happen when you travel near the speed of light that nobody would have expected. Einstein then took this idea of invariance under these Lorentz transformations, and he applied this idea to the geometry of space itself. I've been talking about geometry. I mentioned Riemann's contributions to geometry and how Riemann showed that the basis to understanding geometry is to begin with this idea of distances, these differentials that define distances. And you can define the distances any way you want, have any kinds of properties, and that in turn determines the geometry of the space that you're working in. And Felix Klein further developed this idea, and he showed that you don't have to start with the distances. You can actually start with the transformations that leave the geometry unchanged. And following mathematicians, Schwarz, Minkowski, other mathematicians then would build on these ideas and really develop the tools needed in order to see what transformations left space unchanged and show what that told us about the nature of space itself, the nature of the geometry. Einstein then drew on this mathematics of geometry, and he was able to postulate that all of the universe is invariant under the Lorentz transformations. He looked at the geometry that would preserve these Lorentz transformations, and he said, what if the universe has this kind of geometry? And there are amazing predictions that came out of it, predictions that a massive gravitational body actually would distort the shape of space. And so this was Einstein's prediction coming out of general relativity, that light itself would be bent as it came near a massive body just because space itself was being distorted. And the way space was being distorted was understood by creating this geometry invariant under the Lorentz transformations. I want to look at another area of physics, and this is quantum mechanics. And it goes back to the basic idea, what is an electron? And we usually think of an electron as a little subatomic particle that goes whizzing around the nucleus. And as scientists realized very early in the 20th century, that's not quite accurate. Electrons are much more complex than that. And in 1922, Louis de Broglie was able to show that this electron is not just a particle, but we can also think of it as a wave. This actually goes back to earlier work, controversy on light. Is light a particle or is light a wave? I mentioned just very briefly in passing that Newton, when he studied his optics, had explained light as something that is transmitted by particles, what today we might call photons. In the 19th century, it was shown absolutely that, in fact, light has to be a wave. Well, in the same year that Einstein published his work on special relativity, he also published a groundbreaking work on optics and on light, in which he showed that light must be both a wave and a particle. If you try to study it as if it is a wave, it will look like a wave. And if you try to study it as if it is a particle, it will look like a particle. And what de Broglie said is that that's not just true for light, it's also true for electrons. If you want to look at an electron as if it's a particle, it will look like a particle. If you want to look at it as if it's a wave, it will look like a wave. 4 years later, in 1926, Erwin Schrödinger would find a way of actually getting a handle on this wave. He found the differential equation, so the equation involving derivatives, that actually explained the behavior of this particular wave. And in the same year, Max Born then took a look at Schrödinger's equation, and he realized that the kind of function that satisfies this equation is actually a probability distribution. I talked about a probability distribution in the very first lecture when I was talking about Wigner's article. And there's a reason why physicists are very interested in probability distributions, because electrons can be thought of as probability distributions. It's a function that tells you the likelihood that something will be in a particular position. So you take a piece of space and you ask, what's the probability that my electron will be there? Well, what actually happens, what Born was able to show, is that the electron is the probability distribution. You don't really have a particle. All you have is a mathematical function that tells you that the particle is likely to be there. Well, that's a very difficult idea to wrap your head around. And again, intuition simply breaks down when we try to work at this subatomic level. What you have to do is simply rely on the mathematics that has been created and decide that an electron is this mathematical function, this probability distribution, and work with that. Werner Heisenberg began working with this idea of the electron as a probability distribution, and in fact, all subatomic particles really are best understood as mathematical functions, as some kind of probability distribution. And this led Heisenberg to his uncertainty principle, that this kind of probability function that you've got has the strange property that if you try to pin down how fast your particle is moving, you necessarily are going to lose certainty about where it is. And if you try to pin down more precisely where it's located, you're going to lose certainty about how fast it's moving in the direction that it's moving in. And so you can never know with precise accuracy, actually you can never know with precise accuracy either the position or the velocity. But to try to narrow your knowledge of the position necessarily expands the realm of uncertainty in the velocity. Narrowing down what the velocity is necessarily expands the uncertainty in your understanding of the position. So we have electrons and subatomic particles being explained by Schrödinger's equation. So this is the mathematics that enables us to figure out what's going on at the subatomic level. But there's a basic problem with Schrödinger's equation. It is not invariant under the Lorentz transformation. Now, Einstein saw quite clearly that all of the universe must be invariant under this transformation of four-dimensional space-time. So there's something wrong with Schrödinger's equation. It somehow is not grasping all of the reality that is out there. What we really want to do is find a way of expanding our understanding of Schrödinger's equation so that it's really a special case of something more general that is in fact invariant under the Lorentz transformations. And so this would become the great goal of scientists in the 20th century, and it still is the goal of scientists in the 21st century, of physicists in the 21st century, to try to figure out how to combine Lorentz invariance with the Schrödinger equation. Because if we really want to understand the nature of subatomic physics, we've got somehow to bring these together. And so the question that can be asked is, what kinds of transformations necessarily preserve Lorentz invariance and at the same time also preserve all of the symmetries that are inherent in Schrödinger's equation? And so the physicists were looking for a mathematical model that combined all of the different kinds of symmetries that they were seeing. And one of the models that they eventually came up with is what today we refer to as string theory. And many people are amazed that string theory is not a theory of objects living in four-dimensional space-time. String theory, depending on the version that you look at, either is about objects that live in 10-dimensional space or 11-dimensional space, or for some versions of string theory, you are looking at 26-dimensional space. Where did all these extra dimensions come from? Well, they come from the fact that we've got all these symmetries, all these transformations that need to be preserved. And in order to pack all of these symmetries in, we can't do it in 4 dimensions. We need extra dimensions. Now, physicists have a hard time explaining what's happened to these other dimensions, why we don't experience them, and there have been some suggestions that maybe the extra dimensions kind of curl up so we're not aware of them. The explanation doesn't really matter. What does matter is that if we want to preserve all the symmetries we know about, we need this many dimensions. And string theory is interesting because string theory is built on modular functions. And so string theory is really saying that at the heart of all of the universe, the basic building block of all matter, of everything that is in the universe, that basic building block is the modular function. This strange function with this kind of invariance that was represented by Escher's circle limit 3. Now, that beautiful graphic of these fish in this circle that kind of disappear off to nothing as they approach the edge, that somehow that encodes some of the mathematical properties of the mathematics that sits at the foundation of the universe. And at its very foundation, the universe has got to be mathematical. We can only understand it mathematically. Now, there is a good deal of controversy about string theory. When I talked in the first lecture about Wigner's article, Wigner had said that what physics does is to see patterns in the world around us and to look for mathematics that seems to fit those patterns. And that's exactly what's going on in string theory. We see the patterns, the Lorentz invariants, the transformations that are preserved by Schrödinger's equations, and we're trying to find the mathematics that fits those. And string theory, with its use of modular functions, does seem to fit the patterns that we're seeing. But as Wigner said, there's no reason to believe that when I pull mathematics out of one area, it really is relevant. In fact, he said it's quite surprising that so often the mathematics that we pull in because we see some similarities to the patterns of nature, that mathematics actually is appropriate and useful. And one of the unfortunate things about string theory is that we do not have a way of testing it. We do not have a way of knowing whether this particular mathematics is the right mathematics to understand subatomic particles. And there are a number of other ways of explaining the subatomic world, other mathematical models that other people have suggested. But string theory is beautiful mathematics, and I like the point of view of Freeman Dyson. Dyson is skeptical about string theory, whether it really will prove to be the foundation of all of the subatomic world. But he has said that string theory is so beautiful that it must be useful for something. And so it's not a waste of time to pursue it. Maybe that's not the right pattern to apply to the subatomic world to understand it. But mathematics, as beautiful, as aesthetically appealing as the string theory, must tell us something important about something in the real world. And in the next lecture, I'm going to continue and bring you up into the 21st century and give you some idea of the exciting mathematics that is happening right now within my community. We've reached the last lecture, And my job in this lecture now is to try to give you some idea of what mathematicians are doing today. What are the big problems that mathematicians are working with? And obviously, I'm not going to be able to give you much of an idea, but I hope to touch on a few things that'll communicate the excitement and the richness of mathematics today and why people like myself are so excited about working in mathematics. I started out talking about where mathematics comes from, how mathematics really comes from working with the world around us, looking at the patterns around us, looking at the problems that come out of those problems and trying to build on those. And we've looked at how mathematics was created by questions in commerce and in civil administration. We've looked at how mathematics was developed from problems of navigation and surveying. We've looked at how mathematics came about from questions about astronomy and, by extension, other questions about the physical world around us, trying to understand electricity and magnetism, trying to understand the subatomic world. Those also give rise to mathematics. We've seen how mathematics comes out of art and our understanding of symmetries and transformations and how that came to play such an important role in the 19th century. And right up until the present age. And today we have even new sources of patterns that suggest problems for mathematicians to work on. And I want to say just a little bit about those two important sources of patterns for mathematicians today. The first of them comes from information technology. That there are lots of patterns in information technology, lots of problems that mathematicians can really get their hooks into. And they're problems where we cannot just use traditional mathematics. We actually need to explore these patterns and create new mathematics in order to deal with the problems that are coming to us. One of the good examples of this is the public key crypto system developed by Rivest, Shamir, and Adleman at MIT in the 1970s. So this is a way of encrypting information so that it can be sent securely over the internet, where you've got the problem that whenever you send the key for the encryption, somebody might look in on that transmission of the key. And so it's got to be a key that is created in such a way that seeing how to encode the information does not help you with the decoding. And actually, the process that sits behind the RSA public key crypto system is the basic mathematical fact that if I've got two very large primes, it's relatively easy to multiply them together. But it's very difficult to take that product and undo this process, find out what the two primes were that needed to be multiplied together in order to get that number. And this whole public key crypto system has given rise to lots of interesting mathematics and explorations of properties of the integers. There also is the internet, and the internet can be thought of as a graph with billions of nodes. And in fact, as the internet continues to develop, as each individual item in a grocery store becomes a transmitter of information, letting the store computer know where it is and who's picked it up, or whether it's in somebody's shopping cart or whether it's being purchased at that time, the internet is going to explode out to trillions and quadrillions and quintillions of nodes. And how do you deal with all of this information that is out there? How do you make sense of it? If you've only got a few million nodes, then you can actually keep track of them all. But once you're talking about numbers of nodes on this kind of scale, you need some deeper structure. And there are people who are doing fascinating mathematical research into the deep structure of something like the internet. There's a very good team at Microsoft right now, led by Jennifer Tor Chase and her husband Christian Borgs. It's the theory group at Microsoft. And they've been modeling the internet, also looking at problems of social networking and the spread of worms and viruses. And they've been drawing on very deep mathematical techniques, pulling in some of the ideas I've talked about from geometry and algebra and analysis, and seeing how they interact and how you can build new tools to understand what's going on in information technology. And another area that's giving rise to new and exciting problems in mathematics is biology, and especially genomics. Now that we can actually take the human genome and write it out as the billions of letters, the billions of these A, C, Gs, and Ts that make up the menu for how to construct a given individual. The problem is to interpret this now. We've got this huge book, and we need to figure out how to read it. And the reason that this is called a genome is because it contains the genes, it contains the templates for constructing the proteins that are used in the way the body works. And the problem before biologists is to look at this string of letters and try to figure out what pieces of it are doing what. And a given gene is not just a single sequence of letters. A given gene will often be made up of a sequence here and another sequence someplace else. And the problem is to figure out how these different pieces of the sequence combine. Here's part of a gene. Where is the rest of it? How are these related? What is it that they're doing? And this is really a problem about understanding the information that's there, understanding the deep patterns that lie on the genome, and that's a mathematical problem. And so we have brilliant mathematicians now who are looking at this problem of genomics, not just the human genome, but the genome for all sorts of plants and animals, and trying to figure out what's going on. And these are people who are applying techniques from algebra and geometry and analysis and statistics in order to do this. One of the mathematicians who's done a lot of important work in this area is Eric Lander. Eric Lander teaches at Harvard. He has his PhD in mathematics, but he became interested in the mathematical problems behind genomics. And so after getting his PhD in mathematics, he went back to school and learned the biology that he needed. And then he became involved in the Human Genome Project in its very early days. He would become one of the leaders of it. And in fact, he is the first author on the Human Genome Project, on this final classification of the human genome that now is out there. Another person who is working in genomics is Bernd Sturmfels. And he's found very inventive ways of combining ideas from statistics and algebra and geometry in order to identify genes, understand what they're doing, understanding how they are changing over time. Because one of the interesting things about the human genome is it isn't just a list of instructions for how to create a person or how to create a mouse or how to create a plant. But it also is a record of all the different experiments that nature has carried out on the creatures that eventually have become this man or this mouse or this plant. And so contained within the human genome is this record of different experiments. Eric Lander has talked beautifully about this, that once we can decode this, we are going to have millions of years of experiments that nature has been trying out, and we can see what experiments nature has tried and figure out what experiments have succeeded and what experiments have failed. And as we begin to read the genome, we're going to get an incredible wealth of information that will greatly advance our understanding of biology. One of the small results that Bernd Sturmfels and his team has come up with is a particular gene that happens to be 42 letters long that is actually common to all vertebrates. Every single vertebrate has this particular gene, and because it's a gene that is common to all vertebrates and somehow seems to be essential to being a vertebrate animal, they have dubbed it the meaning of life, with an obvious reference to The Hitchhiker's Guide to the Galaxy. It's a word that happens to be 42 letters long. Certainly, that must be coincidence, but 42 does seem to be fundamental in some basic way. Mathematics is not only looking at questions that come from the world around us, from information and biology, but mathematics continues to generate many of its own questions. And I want to say a little bit about the 7 millennium problems of the Clay Institute. The Clay Institute, which exists in Cambridge, Massachusetts, in the year 2000 decided to put out what it saw as the greatest unsolved problems in mathematics in order to spur work of mathematicians. I mentioned that in the year 1900, David Hilbert stated what he saw as the 23 most important problems in mathematics, and they really helped to shape the development of mathematics in the 20th century. The Clay Institute is trying to do the same thing now at the beginning of the 21st century. And I'll say a little bit about the problems and then focus in on one of them that has already been solved. The Clay Institute, incidentally, has offered a $1 million prize for the solution of each of these problems. This requires a good deal of vetting. It is built into the prize that several years will elapse in order to verify that the solution really is correct. So the one problem that has been solved, the $1 million prize, at least at the moment that I am speaking now, has not yet been offered. One of the problems is what's called the Birch and Swinnerton-Dyer conjecture. I can't go into any detail, but it is a conjecture about elliptic curves. I talked about their role in the proof of Fermat's last theorem. There is a lot we now know about elliptic curves. We know that they are all modular, but there's much else that we do not know about elliptic curves. Another important open problem is what is called the Hodge conjecture. This is a problem in algebraic geometry. I talked about how geometry underwent a fundamental change in the late 19th century when people realized that you could understand all of the different geometries just by understanding the transformations that left the geometry unchanged. And so geometry really is tied up with algebra, modern algebra being the study of transformations. And algebraic geometry is looking at the algebra that enables us to say things about geometric spaces. And the Hodge conjecture is something that is tied up in this particular area of algebraic geometry. The third problem deals with the existence and smoothness of solutions to the Navier-Stokes equations. The Navier-Stokes equations are the mathematical equations that describe fluid dynamics. So you've got a boat moving through water, or you've got an airplane wing moving through air. And the Navier-Stokes equations, developed in the 19th century, are the way of predicting what is going to happen. They build on the much earlier work of Leonhard Euler. And though we know a lot about fluid dynamics, there still are many fundamental questions that are unanswered about fluid dynamics, and especially this whole area of turbulence. Again, we understand a lot about it, and yet there is a lot that we do not understand, and this is tied up in the third problem. The fourth problem is the Poincare conjecture that I'll come back to. The fifth problem is a problem really from computational complexity related to developing algorithms to work with computers. It's what's called the P versus NP problem. And so you're interested in algorithms for which the time that it takes to complete this algorithm or procedure is a polynomial in the input variable. In other words, to figure out how long it's going to take, you might take the input variable and square it or cube it or take its fourth power, but you're not going to take the input variable and put it in an exponent. So polynomial time really means it's less than exponential time. Certainly it excludes the possibility of something that grows exponentially, where doubling the input squares the amount of time that it takes. Tripling the input is going to raise the amount of time that it takes by a power of 3. That would be exponential time. Polynomial time means that doubling the input is going to at most double or perhaps multiply by 2 squared or 2 cubed, but some finite power of 2. And the question is whether something that can be done in polynomial time is the same as something that can be done in non-deterministic polynomial time. And that means that if it's possible to verify that a solution is correct in polynomial time, is it possible to actually find a solution in polynomial time? That's the P versus NP problem. There is the Riemann hypothesis, and I talked about that. This is being able to determine the error when we approximate the prime counting function by this logarithmic integral, and the problem comes down to finding the zeros of the Riemann zeta function that lie within the critical strip and determining whether or not they all lie on the single vertical line with real part equal to 1/2. And the seventh problem is finding quantum Yang-Mills theory. This is a problem from mathematical physics. It actually is somewhat deeper than the problem that I talked about in the last lecture of trying to find a physical model that combines Lorentz invariance with the invariance of the Schrödinger equation. Yang-Mills theory goes beyond this, and I'm not going to be able to go into any more detail than that. But I want to come back to the Poincare conjecture now, because that is the one problem that actually has been solved. It was solved by a Russian mathematician, Gregory Perelman, in 2002. Perelman was born in 1966, something of a recluse. In 2006, he was offered the Fields Medal as an acknowledgement of the important mathematics that he had done. I've talked about the Abel Prize, an equivalent of the Nobel Prize offered by the Norwegian government in honor of Niels Henrik Abel. But the other great prize in mathematics is the Fields Medal. This has been offered since 1936, and it is only given to young mathematicians. You cannot be more than 40 years old when you receive the Fields Medal. It also is only given out every 4 years, but when it's given out, it can be awarded to up to 4 mathematicians. And Perelman was offered the Fields Medal in 2006. He declined it. Even though this came with a very nice cash reward, as well as the honor of the Fields Medal, he felt that people should do mathematics for the sake of doing mathematics, and not for awards or remuneration that might come from that. I want to say a little bit about the Poincare conjecture, because that enables me to talk about topology, one of the huge areas of mathematics that I have said absolutely nothing about, and I want to say at least a little. Henri Poincare was born in 1854. He would die in 1912. And one of the big problems that he worked on was a problem left over from Newton's Principia, and that is the basic stability of our solar system. So what we have is the planets going around the sun, basically in elliptical orbits. But of course, the orbits are not exactly elliptical, because not only does the sun pull on each planet, but each of the other planets pulls on it. And so the actual motion of the planets is much more complicated. They're being pulled by all of the other planets, and so there are going to be little perturbations in the orbits. And the question is, will these perturbations ever build up to the point where suddenly one of the planets leaves its nice elliptical orbit and suddenly goes spiraling into the sun? Well, we sincerely hope that that doesn't happen. We especially hope that that won't happen with the Earth. But Newton was not able to establish the fact that the orbits were essentially stable. And in fact, Newton postulated that this was a role for God in the universe, that in fact the orbits really aren't that stable, and what we need is a God who will occasionally nudge the planets back into place so that they will stay in their essentially elliptical orbits. Well, succeeding astronomers and scientists didn't really like this role of God to keep pushing the planets back in place. So they tried to see if they could find an explanation that, in fact, even despite all of these perturbations, these pulls from the different planets, the orbits, though not perfect ellipses, would remain stable. And it's Henri Poincare who eventually was able to show that the orbits, in fact, are stable. And what he was able to do is to show that as a planet such as the Earth goes around the sun, we cannot predict with certainty exactly where it's going to be at each pass, because we can never pin down its exact location. And any small change in that location is going to magnify as it continues to move around the sun. But at the same time, we can put a window out there, and we do know that the Earth will always pass through this window. If the Earth comes along and passes through this window, it will go around, and when it comes back, it will pass through exactly the same window. And every time it goes around, it passes through this window. And so even though we can't say exactly where the Earth is going to be, we do know a small window within which it stays, and that's enough to say that the orbit is going to be stable. And this would be the beginning of chaos theory. Now, many people know of chaos theory as this idea that if a butterfly flaps its wings in China, that creates enough uncertainty in the air currents that eventually it will cause a hurricane over Florida. And in fact, we do have this kind of uncertainty in meteorological predictions. We can never know the state of the atmosphere precisely, and small changes in one place can magnify and have changes, very dramatic changes, someplace else. The idea behind chaos theory is not just saying that we have this unpredictability, but it's actually finding the stability that sits behind this unpredictability, exactly the same kind of stability that Poincaré found. That even when you've got a system that seems to be chaotic, there may be some deep underlying structure that you can find, and that structure will predict something that is actually going on. A nice example of this is a colleague of mine at Macalester College, Daniel Kaplan, who has done a lot of work in studying heart arrhythmias. And a heart arrhythmia is a basically chaotic situation. The heart is beating in a very irregular pattern. And what Daniel Kaplan has been able to do is to mathematically study these irregularities and find underlying patterns. So he's using chaos theory to find the underlying patterns. And he has actually designed and patented a pacemaker that finds the underlying patterns and then uses these underlying patterns in order to bring the heart back into its regular beat. And so this is a very immediate application of chaos theory and the mathematics to a very practical problem. Now, in developing his chaos theory and his understanding of celestial mechanics, Poincaré really begins the study of topology. When I talked about the elliptic functions, I said that the elliptic function really lives on a torus, a donut. And what's important about the donut is that it has this periodicity as we move vertically, and it also has this periodicity as we move horizontally. But it's not the kind of periodicity that you get on a sphere. If you go vertically around a sphere, you repeat. If you go horizontally around a sphere, you also repeat, but not in the same way that you do in a donut. And so one of the things that topology is about is what is the fundamental difference between a donut and a sphere? And one of the ways of thinking about this is to take a rubber band and put that rubber band around a sphere, or put it around a donut so that the rubber band passes through the center of the donut. If I've got this rubber band on the sphere, I can always take it off the sphere with no trouble. If I've got the rubber band around the donut so that it passes through the center of the donut, then there is no way I can remove that rubber band without either cutting it or cutting the donut itself. And so that's the fundamental topological difference between a donut and a sphere. And this property of a donut is something that you also have in a coffee cup with a handle. We've got exactly that property. If I take a rubber band so that it goes around the handle of the coffee cup, there is no way of removing that rubber band without either cutting it or without breaking the handle. So a coffee cup looks very much like a donut in this particular topological sense. Now, the Poincaré conjecture was actually looking at the surface of a sphere in four-dimensional space. Now, the surface of a sphere in three-dimensional space is two-dimensional, so the surface of a sphere in four-dimensional space is going to be a three-dimensional object. And I apologize, but I've got to move us into 4 dimensions. It's very difficult to visualize what's going on there, but I'll ask you to bear with me. And one of the ways of characterizing a sphere in 4-dimensional space is exactly this same idea. If we take a rubber band or we take any closed curve on this 3-dimensional sphere in 4-dimensional space, it's always possible to remove it. Or topologically, what is said is that if you've got a closed curve, you can always shrink that closed curve down to a single point, and then the closed curve disappears at that point. Now, the question that Poincaré asked was, are there any other kinds of objects in 4-dimensional space that have this property that every closed curve can be shrunk down to a point without being topologically equivalent to this sphere? Topologically equivalent means kind of a rubber geometry, some way of stretching and bending it so that you can turn this other object into a sphere. Can you have another object with the property that every closed curve can be shrunk to a point, but it is not in a fundamental way equivalent to a sphere? This is the Poincaré conjecture that, in fact, this uniquely determines the sphere in 4-dimensional space, and this was the big problem that was out there that Perelman eventually was able to prove. The Poincaré conjecture itself is interesting, but of course what's most important in Perelman's work are the tools that he developed, some very deep geometric and topological tools that other people are now going to be able to apply to many other questions in topology and geometry. I've been talking about mathematics as linking the patterns that are inherent in the world around us. I hope you've gotten a picture of mathematics as taking patterns from one area and patterns from another area and beginning to see how they overlap and how you can extrapolate from them, bringing together algebra and geometry and seeing what comes out of that, bringing together questions in algebra and this idea of symmetries and transformations, laying them over each other and seeing what comes out of that. Taking problems in analysis or calculus and looking at them from a geometric point of view, looking at these elliptic functions as living on elliptic curves or living on this particular torus that I had talked about. So mathematics is all about seeing how these patterns interrelate with each other. And the problems of mathematics are something that people from outside of mathematics often see as the focus of mathematics. But in fact, for people like myself who are working in mathematics, it's all about exploring these patterns. And when I take 2 patterns and I manage to combine them and see something that nobody else has seen, that's the great aha moment, when you realize that you really are exploring something very deep about the nature of the universe that nobody else has found. And that's what convinces somebody to be a mathematician and to continue to be a mathematician. I want to conclude by talking a little bit about one of the great mathematicians in the world today, Sir Michael Atiyah. His father was Lebanese, his mother was Scottish. He was born in 1929. He would go on to hold the Savilian chair at Oxford. Again, this is the chair that was once held by John Wallis and eventually would be held by James Joseph Sylvester. Atiyah then would go on and become Master of Trinity College in Cambridge. And he would also become the first director of the Isaac Newton Institute for the Mathematical Sciences at Cambridge. He's somebody who won a Fields Medal. He won the Abel Prize in 2004. He's done important work in geometry, in algebra, analysis, and physics. And I'd like to close with a quote. Back in the 1980s, he was interviewed and was asked, how do you select a problem to study? And his point in response was, I don't really look for problems, I look for patterns. He responded, I think that presupposes an answer. I don't think that's the way I work at all. Some people may sit back and say, how do I solve this problem? I don't. I just move around in the mathematical waters, thinking about things, being curious, interested, talking to people, stirring things up. Things emerge, and I follow them up. Or I see something which connects up with something else I know about, and I try to put them together, and things develop. I have practically never started off with any idea of what I'm going to be doing or where it's going to go. I'm interested in mathematics. I talk, I learn, I discuss, and then interesting questions simply emerge. I have never started off with a particular goal, except the goal of understanding mathematics. And I know that you cannot understand mathematics from these few lectures, but I hope I've communicated some of the excitement of this field and why it's so engaging. Thank you.